Very good morning, Satish sir. Very good morning.
Good morning, very good morning.
Good morning. How are you, sir?
Yeah, fine.
Okay,
Now,
okay. Ma'am, very good morning.
Good morning, one and all.
Thank you, ma'am.
Yeah.
Good morning, Jason teacher.
Good
Good
morning.
morning.
Good morning. Good morning.
Good morning, madam. Good morning.
Good morning, sir.
Now it is the time to start the session.
Yes, sir.
Bhagyalakshmi,
Can I proceed?
please introduce the chair and do the needful. Please.
Okay, sir. Okay.
Yes, sir.
Okay.
Hello, everyone. We are moving on to the 16th technical session of WSTA 2024, which is an invited session that shall be chaired by Professor G. Jayashree. Now, Professor G. Jayashree is a professor and former head to the Department of Statistics, Osmania University, Telangana. Her major area of research is probability distributions. She published a lot of research articles in the reputed national and international journals in statistics, and also presented several research papers in national and international conferences. She is a life member of Indian Society for Probability and Statistics and Society for Development of Statistics. We are fortunate to have you, ma'am, with us sharing the session today. On behalf
Thank
of the
you.
organizing committee, I extend a warm welcome to you and kindly request you to take over the session. Over to you, ma'am.
Thank you for that. I would like to invite Dr. Manoj Kumar, Assistant Professor, Department of Statistics, University of Delhi, to present his presentation. And he is going to speak on Bayesian inference for exponentiated exponential distribution under progressive type 2 censoring with beta binomial removals. Sir,
Okay.
Manoj sir,
Okay,
we
ma'am.
welcome you, sir.
Okay, ma'am. Thank you, ma'am. Thank you, ma'am. Is my slide is visible, ma'am?
Yes, sir. Yes,
Okay.
it's visible.
Okay, ma'am. Thanks. First of all, very warm welcome and good morning to all. And it's my gratitude to Professor Satish and his team to conduct such a continuous this conference. I think from the previous 4 year back, and I think really they have born to all these statisticians on the same on a platform, and once again heartily thanks to his team. So here today I talk Bayesian inference for exponential distribution under the progressive type second censoring with the beta binomial removal. Now the question arises that why I take this exponential distribution, because everyone know about this exponential distribution is most fabulous and very simple distribution uh, in the live testing problems. So that's why I consider here the exponential distribution, and these are the contents which are related to the my talk, and which is likelihood under the progressive type second censoring with beta binomial removal. And this talk goes to be the in the inferential procedure of the Bayesian paradigm. In the Bayesian paradigm, I discuss about the Bayesian and the Bayesian estimation, and for the long run performance of these estimators and all the discussion about the Bayesian and Bayesian verify through the simulation studies. And after that we are taking the secondary data set for the study of this talk. The exponential distribution was this distribution already proposed by Gupta and Kundu in 1998, and where the two parameters alpha and lambda. Here alpha is the shape parameter and lambda is the scale parameters of these exponential distribution. This is the generalization of the exponential distribution when we are putting alpha is equal to 1. And one of the advantage of this distribution has all the estimators are in the closed form. That's why considered this distribution is more fabulous for the study of this in this context. But in the for the time constraints, in the time constraints, the ability of the data are available in the form of the censored. There are basically there are two types of the censoring. So already many authors have discussed about the type first and type second censoring. Type first is related to the time censoring, and the type second is related to the number of the failure censoring. But the question arises that why you are coming to the progressive type second censoring. The question may be the sum of the commodities or the sum of the patient survival in medical and survival studies. Removals of item may occur in the intermediate steps due to this reason, various reasons which are beyond the control of the experiment. For such a situation, progressive censoring scheme is an appropriate scheme as it allows to the removals of item being tested. So this is the reason behind to taking the progressive censoring. And the progressive type second censoring is nothing but and goes to like a type second censoring where the number of the censored observation is W, and this is the surviving units follows. In the second stage, another patient felt they have followed this way, and all these are the doctor has decided to the test has to be removed after getting the M patient. This is the mechanism for the taking this scheme under 20-second CPR with the binomial removals. And in Bayesian framework, in Bayesian paradigm, we all know about that posterior distribution is the basis of the Bayesian estimation. But here, Han 2009 have introduced the idea about the E-Bayesian inference as alternative to the traditional Bayesian inference. And this method has been employed to the several prior illustration for the unknown hyperparameter of the model. So here the E-Bayesian is one of the another way to take to introduce the prior distribution for the unknown parameter for the estimation procedure. Before going to the Bayesian under the Bayes theorem, and the Bayes theorem is directly proportional to the likelihood and the prior. So this is the likelihood under the progressive type second censoring with the binomial removals is given by the idea of Cohen 1963. And this equation 3 gives the likelihood for the number of failures, and here the number of the removals of the units which are the survived, and the RI's number of removals which are survived. So these are the likelihood, and these are the mathematical calculation for the study of this problem. And finally, we get this. This is the expression of the beta binomial in terms of equation 8. These are the calculations which are related to the beta binomial removal, and this is the parameter for the beta binomial removal in epsilon and neta. So these after taking this likelihood under the equation, and we get in equation 9 and putting, and then we get the complete likelihood in this form. This likelihood is the function of the parameters like alpha. Alpha is the shape parameter, and lambda is a scale parameter, and R is the set of the removals, and this is the beta binomial parameter. So this likelihood can be break into the two parts because all of these are independent. So that's why L1 and L2. L1 stand for the likelihood is the function of the given of the removals, and which are the survive unit as alpha lambda, and here is epsilon and W for given R. This is after calculation. This is the mathematical form of this likelihood in the L1 form, and this is the L2 form. Now the one typical question arises to how to obtain the estimate of the parameters, and these parameters are estimated by the help of the idea about the principle of maximum likelihood estimators and getting the two normal equations. This is the two normal equation 13 and 14, and these normal equations have simultaneously satisfy the value of alpha and lambda as a ML estimate for equating is for the normal equation is equal to 0. For this solution of this normal equation is not easily tractable, so we are going to the some numerical calculation methods, and that is based on the Newton-Raphson method to employ to solve the equation iterative methods. A lot of maybe here apply for fixed point iteration techniques, or maybe apply for some other techniques also numerically to solve this problem. And in the classical paradigm, we are also getting the confidence interval for the parameters of the alpha and lambda by the Fisher information matrix simply apply under the under a PT second CBR, that is progressive type second sensing with the binomial removals. This is the expression for the 100 into 1 minus alpha percent confidence interval for the parameters is given under the ML estimate minus Z alpha by 2, and the square root of the standard error of the estimators. And this is the percentile standard normal distribution, also getting this one, this is flow. But in here my total focus on this talk is based on the Bayesian paradigm and E-Bayesian paradigm, because we know that alpha and lambda are the random variable in the Bayesian paradigm, and Bayesian needs some prior information. And here we introduce a prior like a like a conjugate prior, that is informative prior, and in informative prior taken here gamma prior, because gamma is wealthy enough to cover the all belief of the parameters, and our the considered model is also exponentiated exponential model, so that's why consider here the gamma prior. And gamma prior has also belongs to the exponential family, so it is very easy to tackle all these problems related to the exponential distribution and handles on the real problems. This is the mathematical calculation, and this A and beta. The problem is arise that alpha has the some hyperparameter AB and lambda has the some parameter theta and beta. And the question is that how to choose the hyperparameter of that prior. So the introduce this hyperparameter of that prior is introducing in the Bayesian analysis, simply apply for the prior and the likelihood, then we will get the posterior distribution. And in the posterior distribution, we obtain the Bayes estimate of the parameter, and the Bayes estimate of the parameters has been obtained for the decision purpose. We are taking here the squared error loss function. We are very well known that a square error loss function is nothing but it is the simply symmetric distribution function. Symmetric, that means overestimation is more serious than underestimation, and while for underestimation is more serious than overestimation. That means equally importance we can apply this square error loss function for the study point of view. But in the realistic situation, in the real life problem, symmetric is not always overestimation and underestimation are equally important. Maybe in the some situations arise overestimation is more serious than underestimation, while underestimation is more serious than overestimation. So Bahrain in 1975 and Calabria and Pulsini also introduced the two losses, that is the Linux loss function and general entropy loss function for the asymmetric loss function. for the asymmetric loss function, and introducing these parameters like a delta is a loss parameter, and this loss parameter under the Linex loss parameter, this expression theta phi hat L is equal to -1 by delta log of this one minimize the posterior risk. Posterior risk is nothing but this is the average of the expectation of the average loss. Same way, Calabria and Coulson in 1985, they have introduced the asymmetric loss function, and this is the Bayes estimate under this loss function. So this notation alpha hat Bs stand for the Bayes estimate under the square error loss function. Lambda has a Bs stand for the Bayes estimator of the lambda under the squared error loss function. Similarly, for the alpha hat BL, and these are the notations used for the Linex and general entropy loss functions respectively. The question, this is the mathematical formulations for obtain the Bayes estimates of these respective parameters. Now, in the Bayesian framework, now in the Bayesian paradigm, the posterior distribution of the alpha, that is the marginal, maybe we can say that this is the marginal distribution of alpha, and this is the marginal distribution of lambda, and maybe you I ask this is the posterior distribution for alpha, and this is the posterior distribution for lambda. This is the posterior distribution, and this posterior distribution is also not in closed form. So that's why here the some numerical techniques to generate a posterior samples of the alpha and posterior samples of the lambda with the help of the Markov chain Monte Carlo techniques. And already Monte Carlo techniques has been fabulous from the previous, I think, 20 years back to come in the statistics domain to generation of the random sample from the posterior distributions. And then after in 1997, Hahn have give the idea another E-Bayesian estimation is nothing but expectation of Bayesian. Expectation of Bayesian, that means we have to introduce the hyperparameter of choosing the hyperparameter priors for the three types of the priors. For this one, introduce this mathematical formulation to introduce the idea about the choosing the hyperparameter of the prior under the E-Bayesian paradigm. And this is the in E-Bayesian paradigm, expected Bayesian estimation of the squared error loss function for the three of these hyperparameter choice of these three choice of the hyperparameter under E-Bayesian paradigm. And similarly, E-Bayes estimator under the general entropy loss function, E-Bayes estimator under the Linex loss function. In the same procedure, the motivation only is that here taken as a prior distribution of alpha and lambda hyperparameter, how to choose this one. This is the main advantage of this problem, to choosing the hyperparameter of the prior. So this is the importance I get in some numerical results, and this is the MCMC algorithm to generate the samples of the posterior samples, alpha is and the lambda is. This is the expression. This is after getting the posterior samples of alpha and of the size n size, and lambda of the posterior sample size of n, and a Bayes estimator of the alpha and lambda under this loss function is nothing but average of the loss is known as a risk. But here we introduce only the Bayes estimator under the general entropy loss function. Lambda hat G is the estimator for the general entropy loss function. Alpha hat L for the after getting these samples. And here delta is equal to 1, -1, put this one. This is the generalization of the squared error loss function. So after getting this E-Bayes estimator of alpha and lambda under the various loss function, here consider the three losses. One is a self, GELF, and Linex. three losses. Self is a symmetric loss function, Jelf and Linux is a asymmetric loss function. Here the prior parameters u and v, and these are the desired of the c of this one taken, and similarly theta and beta from the uniform distribution, and these are the mechanism used for generation of the sample to obtain the E-Bayes estimator under mentioned loss function. After getting all these things, my main focus is to our study is correct or not to be justified through some simulation studies to conduct here. For the investigation purpose, we take the sample size n is equal to effects out when the paired of the various distinct sample and simulate the risk has been n is equal to 30 and m is vary from 10 to 25 and n is equal to 40 and m is equal to 15 to 35, and these are the choice for this parameters, and obtain the ML estimate, Bayes estimate under considered loss function. And these are the, after getting this one of the risk of the each of the estimators are considered here. This table represent the risk of the risk and different estimators. Different estimators are this one. This is the Bayes estimator. This is the E-Bayes estimator under self 1, self 2, E-Bayes estimators, and for the overestimation and for the underestimations also. Here for delta is equal to 0.5. That means overestimation is more serious than underestimation for the choice of this parameter to obtain the estimate. And finally, n is equal to 30, and effective sample size m is equal to 10, 15, and 20. And also I have to done for the choice of other parameter, other values are also. The similar trend has to be obtained. And after conclude that this is the Bayes estimate and this is the Bayes estimate. This is the risk. R stand for the risk under the Bayes estimate. The risk is nothing but this is the average of the loss. Average of the loss with respect to the posterior distribution, we get this one risk. So in the Bayes risk, risk has the minimum, E-Bayes risk has the minimum risk as compared to the other estimator. So we have to introduce this E-Bayes estimator for the different choice of n and m. Our proposed estimator of the E-Bayesian has been performed better as compared to the other existing estimator for this one, all this choice. Next, this one, the risk of the estimators under the asymmetric loss function Jelf and Linux with the fixed this value, and here is also take delta is greater than delta is greater than 0. That means overestimation is greater than underestimation for the choice of this parameter. Also perform better our estimator of the E-Bayes estimator. And similarly for the confidence interval and HPD interval also under the self. In the self, there is no need to introduce delta. Delta is equal to minus 0.5 I have to taken here, and for the positive value also taken here. And after that, a real data analysis. Can you hear me? Yes. Hello.
Yes,
Hello.
sir.
Yes. Thank you. In real data analysis, the data set we have to consider for the purpose has been taken Lee and Wang book. This is the secondary data set, represent the survival time of 28 patients with the head and neck cancer who did not respond to the chemotherapy. And taking this data set, and this data set is suitable or not, this data set had been verified through the goodness of fit test, and then after goodness of fit test, and after calculate these values. Here consider the three competitive estimators with respect to the exponential distribution. This is the generalized distribution, this is exponential, and Weibull distribution. And after that, we take here AIC, BIC, Akaike information, Bayesian information criterion to obtain this one. So this one from this table we observe that the model exponential distribution is more informative model as compared to the other models, and this has been the idea of the fitting has to be justified through the TTT plot. TTT plot they have give the idea for the cancer patients which are the increasing hazard rate, and my model is also exponential distribution has the flexible, and they have take the increasing hazard rate also. This is the CDA plot. Through the CDA plot, also justified that this is suitable for that one, and this is for the density plot for this one. And the goodness of fit is also verified through the ratio test, likelihood ratio test, and case test also apply for this data set. And after taking this from the case test, is nothing but this is the difference between the theoretical and the empirical distribution function, and getting the values. These are also under the case bound, and this is very suitable for that model for this data set. For this purpose, we have to introduce the cancer patient data set under PT second CBR samples with the different censoring scheme, with the n is equal to 28 and epsilon is equal to this choice of the value 28, 28 all the samples, and 25 these are the progressive censoring with beta binomial samples to be used. This is the Bayes estimate under the Bayesian and e-Bayes estimate under the self and gel for the real data set. These are only the estimates, and this is the SPD interval highest posterior density to be obtained, and this is the length of the interval. All the estimators are lies under that interval, and we so all these studies has to be verified. And one of the also for the ML estimation procedure for the real data set required a initial guess how to choose the initial guess for the taking the solution of that solution of the likelihood estimator, maximum likelihood estimator. For this one, go through the contour plot and take a initial guess and obtain the ML estimate for this one. This is the case bound for the choice of the different of the patients, cancer patients with n is equal to 28 for the all the samples, and m is equal to 25, m is equal to 25 for the cancer patients. This is the TTT plot. There is a here is a also a TTT plot. All where the TTT plot represents the increasing hazard rate. For this one, finally, clearly we can obtain the ML estimate of parameter. Can we already discussed in the previous of the tables, and evidence of the length of SPD interval is consistently shorter than the length of the confidence interval also getting from the tables. Finally, we conclude that E-Bayes method has compromised to the Bayesian estimator for determining the unknown parameter of the exponential distribution under PT second CBBRs, that is beta binomial removals. Most of the papers are to be done on the progressive type second censoring with binomial removal, but here introduce the PT second CBR, and also introduce the E-Bayes estimator for the another paradigm for this mechanism. These are some references which are related to my talk. Thank you. Thank you.
Thank you, Manoj Kumar sir.
Yes, sir.
For a nice presentation on how you have used the Bayesian inference methods on the cancer data, application of it on the cancer data. It's a good presentation. Any questions from the audience? Any questions from the participants? If no questions, let us thank the speaker.
Okay, thank you, ma'am.
Thank you, Manoj Kumar Garu.
Thank you, ma'am.
Now let us invite the next speaker of the session, Masihuddin. He is from Indian Institute of Information Technology, Guwahati. And sir is going to speak on estimating the selected treatment mean under a two-stage adaptive design. I
Hello,
request you, sir, to present.
am I audible?
Yes.
Yeah, so good morning and welcome you all in this webinar. So
Good
first of
morning.
all, I
We
would,
also welcome you to this webinar, sir.
yeah, so first of all, I would like to thank the organizers for inviting me in this webinar to present my work. Okay, so let me share my slides. Think- Okay, so can you see my slides?
Yes, yes, it is visible.
Okay, so the title of my talk is Estimating the Selected Treatment Mean under a Two-Stage Adaptive Design. So here is a brief outline of what I'm going to present in this talk. So I will start with the introduction and general framework of ranking selection and related estimation problem. Then I will introduce the idea of adaptive design, which is basically an extension of the ranking selection and estimation problem.
ఇదేంటి ఇది
I also then I will move on to our setup of estimating the selected treatment mean under a Gaussian distribution setting and the results obtained under this setup. Finally, I will conclude my talk with some future problems. So let us look at an real life example just to have a motivation of the ranking selection and estimation problem. Suppose there is a company that produces electric bulbs, and this company has K manufacturing processes. And the manager of the company is interested in knowing the effective production process among the K processes. So here, by an effective production process, we mean the production process that yields the largest mean lifetime of the electric bulb produced by it. So the goal is to select the most effective production process among the K processes. So for this purpose, the experimenter produces n electric bulbs corresponding to the K manufacturing processes, and he or she selects that production process that yields the largest sample mean of lifetimes of electric bulbs that is produced by. So this is the process of developing a selection rule for selecting the most effective production process or treatments in many real life problems is basically known as ranking selection problem. So once we select the most effective process, the customer may be interested in knowing an estimate of the mean lifetime of the selected bulb. So this is called estimation of the selection problem. So here is the general statistical working framework of dealing with ranking selection problems. Suppose we have k different populations, pi 1, pi 2, pi k, and whose PDFs are given by this f theta 1, f theta 2, and f theta k. So here, the density function is same except that they differ in terms of the parameters theta 1, theta 2, and so on theta k. So these parameters are unknown to us. And we want to rank these population in terms of these parameters. So what we do, we basically have these x1, x2, xk as the minimal sufficient statistics corresponding to the random sample taken corresponding to the k populations. Then we order these minimal sufficient statistics. So these x sub box i's are the ordered values of xi's. Then theta sub box i's are the ordered values of theta i's. So a priori, we do not know the correct pairing between the ordered and unordered theta i's because they are unknown to us. So in ranking selection problem, our goal is to select one of these populations using a predetermined selection rule, x1, x2, based on the data x1, x2, xk. So here we may be interested in selecting the population that is associated with the largest theta I, which is I am denoting here with theta k. So here, the selection rule is basically characterization of the k-dimensional sample space corresponding to these k populations in such a way that if your sample belongs to the partition AI, the population pi I is selected. So this is the characterization of selection rule. So initially, there are basically two classical approaches in the formulation of ranking selection problems. The first one is by Bekofer, which is indifference zone approach, and the second one is subset selection approach of Gupta. So under this indifference zone approach, we basically select one of the population as the best or the worst population. Under the subset selection approach, we select a subset that contains the best population. So I will not go into more details of the selection rule because my topic is on estimation. So if you want to have a detailed discussion on this ranking selection problem, one may refer to the monographs by Gupta and Huang, Gibbons et al. And Gupta and Pang's publication. So generally in ranking selection problem, people used to propose natural selection rule, which is basically as generally defined as the select that population which correspond to the largest minimal sufficient statistics or the smallest order minimal sufficient statistics. So in estimation after selection problem, our goal is to estimate a parameter of the selected population, which I am denoting here with theta Sx. So this theta Sx is a random estimate because it depends on parameter as well as the data. So this is a random parameter. And now so this was all about single stage estimation after selection problems. Now we move to the idea of adaptive design, which is basically some sort of an extension of the single stage estimation problem. So with these adaptive design have application in clinical trials and in many other real life problems. So adaptive design basically allows certain pre-planned modifications to the clinical trial study design without compromising the original research goal. So here, adaptive designs are basically flexible designs. So in clinical trial, basically developing a new medicine is a very time consuming and also a costly process. So this adaptive design provides flexible, efficient and fast study design to any clinical trial process. So here basically an example of adaptive design is two-stage drop the loser design, in which basically the first stage we select best among the key treatments and we drop the loser ones and we proceed our study with the selected treatments. So here is the setup that we have used for our problem. So suppose we have two treatments, tau 1 and tau 2, characterized by Gaussian distributions having different means mu1, mu2 and a common variance sigma square. So initially we assume sigma square to be known. Here we define the treatment associated with the largest mean mu1, mu2 as largest of the mu1, mu2 as the effective treatments. So for selecting the effective or the better treatments in stage 1 of the design, we have basically assigned N1 treatments to the N1 subjects to the two treatments tau 1 and tau 2. So here these x1 bar and x2 bar are the sample means corresponding to the two treatments tau 1 and tau 2 based on these data. Now so for selecting the effective treatment, we basically use the selection rule, which is the natural selection rule that says select that treatment which correspond to the larger of the two sample means. So we here S is basically the index of the selected treatment, which means that if S is 1, then population treatment 1 is selected. If S big takes the value 2, then treatment 2 is selected. So once we select the better effective treatments, we drop the loser one, and in stage 2, we basically assign N2 additional subjects to the selected treatment. So this tau S is basically a random treatment because initially we do not know which treatment is going to be selected. So here, this y1, y2, yn2 are the observed treatment effect at stage 2, and y bar is the selected sample mean corresponding to this sample. So our goal is to estimate the selected treatment mean, effect of the selected treatment mean, which is denoted by mu s. So this mu s is a random parameter. We will be using the squared error loss function for estimating this mu s under disease and theoretic setup. So a natural way to start this estimation problem is to use the two sample mean in 2 stages and take a weighted mean of this. So this weighted mean, or we call as the naive estimator. So we will see that this natural estimator has many interesting properties. You will see later. So we have also studied in one of our papers, and initially, Peter and Robinson, when under the known variance setup, they have proved that there does not exist any unbiased estimator for the selected mean. And we have extended this result to the unknown variance case and proved that there does not exist any unbiased estimator for this selected mean. So we basically use this idea of conditionally unbiased estimator. So what is meant by conditionally unbiased estimator? It is defined like an estimator delta x is said to be conditionally unbiased for mu s if expected value of delta x given the index of the selected treatment is same as mu s for all s. So initially, Cohen and Sakrovitz utilized this idea of conditionally unbiased estimator, and they have derived basically UMVCU, which is uniformly minimum variance conditionally unbiased estimator, considering a single observation in stage 2. Later on, Bowden and Glim, they have derived this UMVCU for N2 observation in stage 2. So now what we have done in our work, basically we have restricted the class of estimators using the idea of invariance, and we have tried to obtain better estimators under the mean square error. So here the script even basically denote the class of all location and permutation equivalent estimators, which is of the type delta psi x. Here psi is a function from this to this. So here the naive estimator, and interestingly this naive estimator and the UMVCU that has been proposed by Bowden and Glim, these two estimators are included in this class of estimator that we have considered. So what we will try to obtain improved estimators, better estimators in terms of mean square error within this class of estimator. So in this direction, basically we have obtained the first result, which says the naive estimator is minimax for estimating the selected treatment mean under the mean square error criteria. We have also shown that for estimation of the selected treatment mean mu s under the mean square error criterion, the naive estimator is admissible within the restricted class. So we have not been able to prove globally the admissibility of this estimator, so it is still an open problem. The next and the interesting result that we have derived is basically a sufficient condition for inadmissibility of any location and permutation equivalent estimator. So the result says if we have any estimator of the type delta psi x, which is basically weighted average of the 2 stage sample means plus some function of d1 d2, where d1 d2 have been already defined. So the result says if you have any estimator of this type which satisfies this probability condition, then any estimator of this type is inadmissible, and we get a dominating or the improved estimator over this, which is given by delta psi ix. So it is a sufficient condition for inadmissibility of any arbitrary location and permutation equivalent estimator. So as a consequence of this result, we will see later that this UMVCU proposed by Bowden and Glim becomes inadmissible, and we obtain a dominating estimator over the existing estimator. We have also obtained the uniformly minimum variance conditionally unbiased estimator for the selected mean when the common variance sigma square is unknown. So this is the estimator in the case of unknown variance. So here are some important remarks that I would like to mention. So as a consequence of this result 3, the sufficient condition for inadmissibility, we have shown that the UMVCU proposed by Bowden and Glim becomes inadmissible, and we have provided an dominating estimator, which is delta BGI. We also proved the inadmissibility of the naive estimator under the single stage setup. We denote it by delta naught IX. Further, we have also used the idea of Rao electroization to obtain an improved estimator over this X bar S. And we see that we can further improve this delta naught RB and using the Rao electroization, we denote it by delta 1. So these are the various estimators that we have derived and proposed for this estimation problem. But still, for the known variance case, we are not able to prove the inadmissibility of the UMVCU. That is still an open problem. Let us look at the numerical comparison of the performance of the various proposed estimators that we have derived. So as I have said that the naive estimator delta M, which is the weighted average of the two stage sample mean, is admissible within the restricted class. So you can see here that this has the lowest risk or the mean square error among the class of location permutation equivalent estimator. But this also has the constant risk, which is basically 1 over n1 plus n2, the two sample mean in the two stages, n1 and n2. One more thing you can notice from here that the mean square error of the different estimators is highest when we have, so on the x-axis we have the treatment effect difference, the difference among the two treatments, and on the y-axis we have the mean square error. So you can see that when the difference is 0, the mean square error is highest, and as we increase the difference, this mean square error is decreasing. So these plots are for basically for different configuration of theta and sample sizes n1 and n2. So in the first plot we have considered n1 to be 5, n2 to be 3. So n1 is greater than n2. Second plot we have considered equal sample sizes in both the stages, and we have this type of performance. So here when we have equal sample sizes, we observe that the Rao-Belak-wise version of the single stage estimator and the uniformly minimum variance conditional bias estimator proposed by Bowden and Glim, they have basically similar mean square error performance. Next, when we have the n1 to be less than n2, then we have this type of mean square error performance of different estimators. We have also compared the bias of the various estimators, and here also we see that the bias has the highest value when we have the treatment effect difference to be the smallest. And then we have, so here these bias plots are also for different configuration of sample sizes. When n1 is greater than n2, n1 and n2 are equal. Then n1 is less than n2. We have this type of bias performance of various estimators. So these are the observations using the simulation study. So that I have already defined. And so the important thing to note here that under the MSc criterion, the naive estimator, which is the weighted average of the two stage sample, performs reasonably well compared to the all other estimators. So what we see that when both bias
of the day, Mohammad Faizan. Sir, are you there?
Yes, ma'am.
Okay. I welcome you, sir, to this particular international webinar.
Thank you, ma'am.
Mohammad Faizan is from Aligarh Muslim University, Uttar Pradesh, and sir is going to present his talk on characterization of some continuous distributions by conditional variance of record values. So I welcome you, sir.
Thank you, ma'am.
Thank
I'm
you, sir.
audible, ma'am?
Yes, you are audible.
Okay. Just I want to share my screen.
Yes.
Just just a minute, ma'am.
No problem. No problem.
Mm, is visible? Screen is visible, ma'am?
Yes, it's
Is it
visible.
visible?
Yes.
Okay. My talk is on characterization of some continuous distributions by conditional variance of record values. This presentation is basically on record values, and we all know that records are very important for us in most of the cases. And this records values given by China in the late 1952, and there was very much was on in this topic. And characterization of distribution by order statistics given by many authors, and many ways are given. And characterization of distribution, especially exponential distribution by conditional variance given by Beg and Kirmani in late 1978. And after that, this Beg and Kirmani shows that the exponential distribution, that means conditional variance of adjacent order statistics, are constant. And this result was extended by Khan and Beg for a Weber distribution. But in literature, there is no results for record values. So here we are given three distribution consider exponential, Pareto, and power for characterizing this distribution using adjacent record values, the conditional adjacent record values.
Sir, sorry to disturb you. We can see only half of the screen.
Um, what's the reason?
Are you presenting it through the cell phone, mobile?
Yes, yes, ma'am. Actually,
Uh,
ma'am, I'm out of station in my workplace due to
okay,
some
no
urgent work.
problem. What you have to do is please put it in the other way around, like not the lengthwise, put it in the breadthwise.
Okay, ma'am.
Uh,
Okay, okay,
uh,
okay.
now I think we can be able to see.
Now it is okay.
Yes, yes. Now it is visible.
Okay, thank you. So these are the characterization results, which are here we consider three distribution: the exponential, Pareto, and power. In exponential distribution, we can see that this conditional or record values give the constant results for exponential distribution. For showing these results, we use these are the mathematical way we use here for showing these results simply, and we get as this one as a exponential case. And the second result is for a Pareto distribution. And the conditional distribution for conditional variance of adjacent record for Pareto is given by this way. And here must be P is greater than 2. This result is true when the P is greater than 2. And this is for a Pareto distribution. And before that, the Pareto and power distribution not characterized by anyone for any way. So here we consider for showing these results too much time, and this is shown by using a differential equation. The necessary part is easy, but the sufficient part is giving a time to showing this result by using a differential equation. This result is characterized by a Pareto distribution. This we use here some differential equation for showing this result, and this is given, and we use this book which is given by Bayan and Premia, where we have this which helps us for showing these results. And we are working this paper in last too many years, but now we are able to show these results. So these two, and the third one is third result is for a power distribution, and this result is for power distribution. Simply, this paper is for a conditional variance of adjacent record for exponential Pareto and power distribution, and this is a mathematical work only. And here we are doing some verify these results by using some calculations. These results you can verify using exponential and Pareto distribution. And these are some references. Hello.
Hello, hello.
Yes, ma'am. May I audible?
Yeah, audible. But your screen is not visible properly.
Sorry, sir.
Sir, your screen is not visible.
Oh. Hello.
Hello, sir.
Yes, ma'am.
Sir, your screen is not visible.
Sorry, ma'am, for inconvenience.
Please try to make it visible so that you can resume your presentation.
I think there is some network problem in between, maybe.
Mm-hmm. As you said, you are traveling, right?
Yes, ma'am.
So, what to be done? Satish, sir?
Yes,
Satish,
person.
sir.
Yes.
Sir is unable to present because there is a network issue as he is traveling.
Okay, okay.
So, what should be done?
Whether he's the last speaker?
No, sir. One more speaker is also there.
If he is ready, we can allow him the other speaker.
Okay, sir. Okay, sir. I will see.
If he is not ready, we can wait some more time for him.
Okay, sir. Is Subhash Kumar Yadav present? The next speaker, Subhash Kumar Yadav. Sir, I think the next speaker is not there, sir.
Yeah, I think he already contacted me to get the link.
I think
he is waiting for his time. That's maybe. Anyway, just a minute. I have to check whether he is available.
Okay. Okay, sir. Thank you, sir. Faizan, sir?
Speaker has some issues, so would you please join and present your? Okay, sir. Okay, please. Yeah. Okay. I noticed. Okay.
Sir has joined. Subhash Kumar Yadav.
Yeah.
Namaste, sir.
Namaskar.
Sir, shall we start?
Yeah, sure.
Okay. I welcome Subhash Kumar Yadav Garu. He is from Baba Saheb Bhimrao Ambedkar University, Lucknow. And sir is going to speak on statistical and machine learning techniques for the prediction of monkeypox incidences. Sir, I request you to present your presentation.
Thank you.
Thank you for presenting little bit early as we face a problem.
No issue. Okay, so I am already prepared for that one. So first of all, very good morning to all of you, and I must thank to Professor Satish sir and his entire team that they have organized such a very beautiful event, and they have put together all the from small to big statistician at a single platform. So I am very happy to be part of that. So let me share the screen without delaying. I will be delivering the lecture, and we will be discussing some machine learning tools and.
Thank you, Professor Yadav, for your nice words. Please, okay.
Thank you, sir.
So let me share the screen, and then we'll be discussing the things.
Yeah, please.
Is it visible, sir? Is it visible?
The screen is now we can see the multiple screen. So you can move to the slide, or otherwise you can stop this sharing and start it once again. Before sharing itself, you have to open the slides. That's better.
Entire screen only.
Yeah, entire screen.
Why it is multiple showing multiple?
Sometimes due to the network issues or some other problems, that's usual. But you can move to the slides so that it may adjust.
Okay, sir, let us see.
Yeah.
What happens. So whether this is visible now?
Yes.
Okay. So let me put it on slideshow mode. So it must be visible now.
You move to the slides, I think. So for me, you can see your desktop only.
So this is not, I mean, slides are not moving here?
Yeah, yes. Whether the slides, is it possible to see the slides?
No, sir. No, we can see only the screen, sir.
Only the screen. Why is it so? I am sharing the screen, the entire screen, but why it is so?
Sir, have you opened your PPT, sir?
Yeah. Just let me share the entire screen. Let me share the entire screen. Now I have opened this, slide.
Now we could see, sir.
Now it is fine. Yeah.
Okay.
Yeah.
So now it is on slideshow mode, na? Okay.
Yes.
Okay. So today we'll be discussing about some statistical and machine learning techniques for the prediction of monkeypox cases. So the first question arises that what is statistical modeling? So we all know that statistical modeling is nothing but it is a establishment of the functional relationship between the dependent and the independent variable. And some more elaborative way we can put it as that statistical modeling is a simplified mathematical structure, method of approximating reality, which generates your data and potentially making predictions based on this approximation. Basically, we establish the relationship between a dependent and one or more independent variable so that we may be capable to establish the relationship between the two so that for the new observation of the independent variable, we may be able to predict the dependent one. So statistical model is a mathematical equation, obviously, that is used. So we know which one is dependent and independent variable or explanatory variable. The variable under study or the main variable is known as dependent variable, and the variable associated with that, which may be positively associated, maybe negatively associated, but that variable is independent, and the study variable is dependent on that. So that variable is known as independent variable, or sometimes we call it as explanatory variable. Say here the incidences are dependent variables, and say the time is independent here. Or if we are establishing the relationship, say between production and area, so area is independent and production is dependent on the area. So this is the way we can check which one is the independent variable and which one is the dependent variable. So always we predict the dependent variable on the basis of the values of the independent variable. So what are the model parameters? The constants are say some characterizing scalars which are being used while making the functional relationship between the dependent and the independent variable are known as the parameters of the model. And model may be linear and non-linear in nature, so we are not going into the detail of that linearity and non-linearity of the model under consideration. So for a straight line, say y equal to a plus bx, so we don't know what is the actual relationship between, say, dependent variable y and independent variable x, but here we are establishing a relationship. We are putting x somehow the function of x to equal to y, that we are assuming here that it is linearly related, so y is equal to a plus bx. So here a and b are the model parameters. Maybe if you are fitting the second degree parabola, then a, b, c will be the parameters for the model y equal to a plus bx plus cx square, like that. So what is the model residual? We know that c, this is the actual value of the model, and this is known as the fitted value or expected value of the model, and sometimes we call it as y cap if we put here the error term, that is residual. So residual is nothing but it is the difference between the observed and the estimated or predicted value of the dependent variable by the model which we have fitted. So it is the difference between the observed and the expected value of the variable under consideration by the model. Now we can fit several models. We can establish various relationship among or between the dependent and independent variable. But now the question arises, which one is the best one? Which is the best fitted model? So we must have some measures to check which one is the best fitted model. But let me put here that the model, we have to keep in mind one thing, that the model with the least residual, or say they are so designed that sum of the residual equal to 0, because some points are overestimated and some points are underestimated, so the sum is 0. So what we used to use that we take the square of the residuals and get its sum, and the model with the least residual sum of square, sometimes we call it as error sum of square, is the best fitted model. So we search for the model, and then we have some measures to check which model is having this least residual. So there are so many fitting measures, say R square, AIC, BIC, and MAE, mean RMSE. So there are so many fitting measures, but somewhere you will find that every fitting measure is a function of the residual. So that is why I personally accept that or assume that the model to check which one is the best one, we should check the model with the least residual sum of square. all other parameter fitting measures are also the functions of the residual. So we can take into consideration as well that measures, those measures as well. So AIC, AKK information criteria, Bayesian information criteria, root mean square error, and mean absolute error. So there are, and see, there are some situations where some say MAE is most appropriate and like that. But residual is okay for the data if the data is homogeneous. If it is not homogeneous, then in that case, some outliers or extreme observations are there. Then we go for some robust measures, and that MAE comes into the category of that robust measure. So we'll be seeing the different fitting measures to check which model is the best fitted. Now, what is infectious disease modeling? This is very important, and this is the point of discussion here. The infectious disease modeling is a tool that has been used to study the mechanism by which this disease or diseases spread, to predict the future course of outbreak, and to evaluate a strategy to control that epidemic, pandemic, whichever it is, the spread of the infectious disease under consideration. Now, these are some statistical and machine learning models which are being used for the analysis and prediction of the outbreak of any infectious disease under consideration. And we have considered here the monkeypox cases. So there are mainly 4 types of infectious disease modeling methods. The first one is the distribution fitting method. Another one is the time series regression modeling. Then the machine learning models and the epidemiological modeling, or sometimes we call it as compartmental modeling. But here we are not considering the fourth one case, because we don't have information in terms of different compartments. So I think we have not applied that in case of this monkeypox. Okay, let us discuss about some monkeypox virus. The global population has experienced the profound epidemic. That is, COVID-19, which has impact on economic as well as medical facilities. Or say we have seen the economic and medical consequences of that pandemic, that is COVID-19, and along with increasing concerns about the emergence of new viral diseases. So by that emergence situation, we have faced some more, new viral diseases, and this one is one of them, that is monkeypox virus. So one such emerging viral threat is monkeypox, a zoonotic disease caused by monkeypox virus belonging to the orthopox virus genus. Initially discovered in monkeys in Copenhagen by Preben Christian Alexander van Magnus, monkeypox virus has since crossed over into human population, from monkeys to humans, with the first documented case reported in a 9-month-old infant from the Democratic Republic of the Congo. So subsequently, over 3,000 cases have been confirmed across 15 countries, including unexpected outbreaks in Singapore, Israel, United States, and UK as well. So the re-emergence of monkeypox in various regions has raised concern about its potential to fit the biological and immunological gap left by the eradication of the monkeypox or smallpox. So we have also faced the problem of smallpox as well. So now we have to see the gap which is between the biological and immunological situation of the bodies. Typically, monkeypox symptoms last for 2 or 4 weeks and are self-limiting. Those severe cases are more common in children and individuals with compromised immune system. So it was, more effective on the bodies with weak immune system. So this is the word cloud of the symptoms for the monkeypox virus. So we can see most of the patient were having fever, ulcer, genital genital and skin rashes. So these are some, I mean, very common symptoms of the patients of the monkeypox. But there are sore throat and fatigueness and say headache. So these are also the symptoms of that. But most of the very common symptoms are fever, skin rashes, and genital and this ulcer. So these are the incidences, confirmed cases of the monkeypox virus over the globe. You can see here the cases are shown as per the. So you can see here this one is showing a little bit more in comparison to all other countries of the world, and you can see different countries are facing different. And we have discussed that Singapore and Israel are having, UK and US is having a little bit more cases in comparison to other parts of the other countries of the world. So now we come to discuss different 4 methodologies, or say among 4 we have discussed 3 methodologies for this incidences. So first one is distribution fitting. So what we have done in this case, we have fitted 123 distributions which are I mean parametric, non-parametric, theoretical, and sampling distributions, and in that continuous and discrete cases we have fitted 1 to 3 case distributions to all the top countries in hand, and we have seen that some 4 or 5 or 6 distributions are found to be best fitted for almost all top countries under consideration. So we have found that these Burr, Gompert, Gilbert, Lomax, Genimpox, these are the distributions, Fold Cossi, these are the distributions which are fitted to the different countries under consideration for the explanation and fitting of the monkeypox virus for different countries over the globe. So see here, these are the best fitted distributions that Burr distribution, Gompert, and these are the PDF of that distribution with the parameters, and Gilbert sign, Lomax, Genexpon, and Fold Cossi distributions. And see here, these are the best fitted distributions for different countries. You can see here for Brazil it is Burr distribution, for Canada it is Gompert distribution, and for Colombia it is Gilbert distribution. So this way we can see for all top 10 countries we have fitted, and we have found different theoretical or say distributions, best fitted distributions. So on the basis of that we can get the average, we can calculate the parameters of these models, and so on the basis of the that outputs or inferences, we can make some robust measures to check this spread of this disease. See here, these are the countries, they are these are the best fitted models, and you can see these are the location parameters. If having 2 parameters, and if it is 3 parameters, then say parameter is also given here. So on the basis of that we can forecast as well as, and we can make some robust policies to check the further spread of the incidences of this monkeypox. Since this phenomena has developed over time, so time series modeling is an essential part to be fitted over the phenomena, to analyze the phenomena and predict the phenomena, so that we may make some robust policies. So we know that in time series modeling there are 2 very famous methods, very well known method. One is known as exponential smoothing, and another one is known as ARIMA. So we have fitted both the models to the given incidences of top 10 countries of the monkeypox virus, and in exponential smoothing we have considered these 3-4 methods, that simple linear trend, Hall's linear trend, and Brown's linear trend, and damped linear trend. So we have fitted under the umbrella of that exponential smoothing, and we have fitted the ARIMA as well. So let us see which one is the best fitted time series model for the cases. Let us consider the another one method, which is machine learning, that is random forest machine learning algorithm. As we know that this random forest uses the decision trees, and we take the averages of that decision trees here in random forest. And what is the advantage of this random forest? That it offers offering advantages such as it reduces overfitting, robust against outliers, because if outliers are there, then regression estimates of the regression coefficient may be not of good statistical properties. Maybe it may have some large variance. It may not be blue at all. So this faces the problem. So this problem will be overcome here in case of this random forest method. So it is robust against outliers, and scalability of high dimensional data. It will deal with the high dimensional data as well. So it has found extensive application in classification, regression, modeling, and forecasting tasks across various domains. The algorithm's ability to handle complex problems, big data, along with its efficiency and parallelizability, has contributed to its widespread adoption in the field of machine learning. So here we have also applied this machine learning technique to establish the best possible relationship, and so that the forecasted will, and we can forecast very close to the reality. So here we have also applied this random forest machine learning method to analyze and forecast the monkeypox incidences. You can see here this is concerned with the time series model only. ADF and this augmented Dickey-Fuller test is used to see the stationarity of the time series model. And so we have graph of say this ACF and PACF, autocorrelation function and partial autocorrelation function. This tells about the estimated or optimum values of PDQ. What is P? P is the number of lag observations of the variable under consideration, and D is the number of differencing, that is integrated number of integrations to make the non-stationary series stationary, and Q the number of lag values of the error function. So through these graphs, we calculate the optimal values of PDQ for the ARIMA. So here you can see these are the fitting measures, the KK information criteria, Bayesian information criteria, and these are the best fitted ARIMA models, and these are the MSC for the ARIMA as well as random forest. So you just compare for the different countries, top 10 countries. You can see here through ARIMA the root mean square error is 386, and while it is 282. So you can see here that this random forest is best for this country, United States, and this way it is 80, it is 64, it is 63. But here you can see for Spain the ARIMA model is best fitted. So this way we can, but overall we can see that here that random forest is going to be good for the analysis and prediction of the monkeypox incidences. Now this is the summary statistics for the monkeypox cases for the country over the period, for the whole top 10 countries over the period which we have considered for the analysis. So here you can see the mean cases for US. These are the mean cases of monkeypox cases, and these are the mean cases for different top 10 countries. These are the standard deviation, and this is 95% confidence interval for different countries under consideration. So this is the actual diagram, actual figure for the different countries, how the phenomena has happened. You can see here that it is most of the cases are for the United States, and then this green one, that is Spain. So this way we can see the different cases for different countries, how it happened in different countries. So these are the forecasted values through ARIMA, that these are going to be median cases and mean cases for the month, as we have taken the cases per day, but we have taken the forecasting for the month. So all 30, we have not given here the 30 forecasted values, but we have taken the median as well as mean. Both median we have given, since the cases may have we have taken the random forest, so that is robust against that outlier or say extreme observation. That is why we have also given median as it is robust in comparison to mean for the outliers or say extreme data where outliers or extreme observations are present. So you can see here these are the average cases for next month for the concerned countries, corresponding countries. And here these are the graph you can see here. This is the fitted one, and the green one is the forecasted one, and this is tested. So here we have taken the data as 80-20 ratio for testing as well as for fitting and testing. So training and testing. So this was for the training of the model, and this was for the testing. So you can see here this green is forecasted value and this one is the tested observation. So this way we can see for different methods. So here this is for the forecasted case for the random forest method. So you can see here these are the mean cases and these are the median cases, and let us see through the graph that this is going to be forecasted observations and these are the tested observation for all 10 countries. So this way we can fit the different machine learning or statistical models to establish the relationship over the ongoing phenomena, to model that phenomena, and if we have modeled it well, then we can predict it very well, so that we may make some effective and robust policies to have control over the further spread of this infectious disease, maybe some other disease as well. So this was today's discussion. If you have any query, any question, then please ask.
Thank you, sir. Thank you, Subhash Kumar Garu. Any suggestions or questions?
Hello, Dr. Subhas. It's Parmil.
Sir. Hello. How are you, sir?
I'm fine. So very well presentation.
Thank you, sir.
And you have done a very wonderful job. So which algorithm you have used of the machine learning for this forecast?
Here we have used that random forest only, sir. But we have used some other and we have used that algorithm at say in Python.
Okay. So any special reason for considering the random forest model, or other than the other supervised and unsupervised models?
We have only used since we have different cases. So we have here in study we have used only supervised machine learning methods, and not only that we have also used support vector machine as well, and some more machine learning methods. But here we have due to time constant we have taken only the first one, that is random forest. We have also considered that this decision tree as well, since it takes the averages of that. So that is how we have presented here only the random forest.
Well done, Dr. Subhas. Well done.
Thank you so much. Thank you.
Good presentation, sir.
Thank you, ma'am.
Thank you for the work. Thank you. Satish Kumar, sir.
Yeah. What about the other speaker who has some network issues?
Yes. Okay. Shall I ask, sir? Is Faizan, sir, there? Faizan, sir? Sir, I think sir is not there. Hello?
Okay. If he is not here in the group, since we have to wait some time, wait for him, because there's a technical issue, not his fault. Let us wait and But we can't give more than the adequate.
Yes, because the schedule is already prepared and the other speakers will be waiting for their turn.
Yeah. Uh, he's the only speaker in this session, isn't it? Or Masuddin, whether he presented, isn't it? Muhammad Faisal, isn't it? Yeah, he's the only speaker remains, isn't it? Okay.
Yes, sir. The other three completed their presentations.
Very good.
We are left out with only Faizan, sir,
Okay.
who had network issues.
Okay.
So shall we wait for sir or?
Yeah. Let us wait some time. And by the
Okay.
time, let me to try to contact whether is it possible to contact you.
Okay, sir. Okay.
He will join the meet and he try his best to do something and then we can conclude this.
As sir said, he is in traveling, so there must be problem.
Okay. So as far as our country, there are different place and different atmosphere,
Yes.
weather conditions.
Yes.
That's why. Hello, Kumaramash. Yeah.
Hello, sir.
Hello. Yes, we can hear you.
Yes, I'm audible, sir.
Yeah, audible.
Yes.
Sorry, sir, for inconvenience. I have some issues in presenting my whole paper. I tried to present my paper completely, but it is some network issue. That's why I'm not able to present this paper. This is my some urgent work. I plan this paper presenting at the evening, first of all. And morning we see our presentation is morning. Hello.
Hello.
Yes,
So,
am
Yes.
I audible, sir?
Uh,
Dr. Faisal,
Yes,
what
sir.
about, to what extent you presented, whether you covered?
My presentation is characterization of conditional distribution through record values. And
Okay.
there are three distributions. We consider exponential, power, and Pareto with
Okay.
conditional variance.
Okay. So you can give any clarifications if it requires by the
Yes, sir. Yes, sir. May I?
Madam, you can interact whether the participants have any questions raised to him and other speakers. Please utilize the time for that.
as Mohammad Faizan was planning to talk on characterization of some continuous distributions by conditional variance of record values. So, sir could present only some part of his presentation. Anybody who wants to ask sir any queries or any questions, please, you are welcome to do that. As sir is traveling, he is unable to present his whole presentation, his whole paper. So anybody who wants to interact with sir or ask any questions, please do that. You are feel free to do that. He is
Welcome.
on the call. So to find out this conditional variance of record values, what techniques you have used, Faizan?
Using adjacent record values, and just simply we do a necessary part using a conditional expectation, and then using the variance. The sufficiency part is difficult by proving this using a differential equation technique.
Okay.
Okay. The exponential result is easy, but for Pareto and power, it is difficult to show that sufficiency part. We use for showing this result by a differential equation.
Okay. So sufficiency part is a problem.
Yes. The main
Okay.
problem is that
Okay.
we are working this paper in last 2-3 years, but we're not able to do it. Right now, it is completed this paper.
Okay. Maybe you can use some other techniques like iterative methods or something like that.
No, ma'am, it is not easy.
Okay.
But simply it is we try to do it, but it is not able to
Or
calculate the
any
result.
machine learning technique which you
Yes,
can
it's
use.
maybe. It's maybe.
Yes. You can try on that.
Okay, thank you, ma'am.
Any questions or suggestions? If no, okay, Faizan, now all the best for your work.
Okay, ma'am. Thank you considering my problem.
Thank you. No problem.
Okay. Thanks so much. Thank you, sir. Thank you, sir.
Since we have a few more minutes in this session, let us conclude even that and interact other type of interactions. What about you think, the chair, madam?
Yes, sir.
Anything you is it okay? Let us conclude the session, isn't it? Any other
Yes.
questions to the other speakers, reminds, or to any interaction requests for the other speakers?
Any interaction or any suggestions or any questions from the other speakers or audiences? Please feel free. Sir, I think we can conclude the session.
Okay. Now let us conclude the session. And in fact, the next session scheduled at 11:15, I think so, isn't it? 11:15. So by that time, we can take an interval here in this platform, and the other platform B is going on. The talks are. So on this occasion, on behalf of the organizing committee of this international conference, I wish to extend our gratitude to Professor Jayashree Madam for chairing the session, and all the speakers for their excellent talks. Let us give a clap to the speakers, and thank you, Madam.
Thank you, sir. Thank you for giving me this opportunity. Thank you.
Thank you.
Thank you all.
Thank you. Are requested to remain here because next talk is in this next session. Professor Jayashree and Professor K.S. Banu are the speakers, and Professor Parimal also already joined here to chair the session. So anyway, please stick on, remain the session, and those who have interest, you can just shift to the other platform, and also no problem. Okay. After a while, let us meet again.
Morning, sir.
Professor Parimal is also here in the group, isn't it? Okay. Rubina. Hello, Rubina.
Good morning, sir. Good morning, Professor Satish.
Good morning. Good morning.
Good morning.
Good morning. Rubina. Yeah.
Good morning, all.
Good morning. Good morning.
Good morning. Good morning, sir.
Rubina, please introduce. Rubina, can you hear me, Rubina?
Yes, sir. Yes, sir.
Okay. Please introduce the chair and support the chair for the smooth run of the.
Okay, sir. Hello, everyone. We are moving on to the 17th technical session of WSTA 2024, which is a specially invited session that shall be chaired by Professor Permil Kumar. Dr. Permil Kumar is a distinguished academic serving as professor and head of the Department of Statistics at the University of Jammu. He holds a PhD from CCS, Haryana Agriculture University, Hisar, with a specialization in entropy optimization principle applied in statistics. With extensive educational qualification and significant research experience, he has published in renowned national and international journals. Dr. Kumar's teaching career spans several years at the University of Jammu, where he has taught a range of courses in statistics and statistical computing. He is also actively involved in academic societies and has contributed as an editorial board member for various academic journals. We are indeed fortunate to have such an eminent person. Without further ado, over to you, sir.
Welcome. You have to unmute the mic. Unmute the mic.
Thank you, Rubina, for the nice words. And thank you, Professor Satish Kumar, for giving me an opportunity to be associated with the 9th International Webinar on recent trends in statistical theory and applications. You have been organizing the conferences and webinars every year, and mostly you do it in the month of December, but now you're doing in the middle of the year. But you are a inspirational force for all of us working in the field of statistics to stay connected and to be active in the research areas. Thank you so much, sir, for this opportunity. So today we have two presentations. The first one is by G. Jayashri from Osmania University, and second one is of Professor K.S. Bhanu from Institute of Science and Science Nagpur. So the total minutes that we have is 80 minutes. So we'll spread this session into two presentations. The first presentation will be of 30 minutes, and similarly, second presentation will be also 30 minutes, and 10 minutes will be for the discussions. So first I invite Professor G. Jayashri from Osmania University. So Professor Jayashri has a long career in teaching and research. After completing her doctoral thesis in 2003, she joined the Osmania University in 2007. And she has officiated the office of the chair of the head of the department, and she has published research articles in the journals of repute, international as well as international. So she will be presenting on the topic, a study on properties of Pearsonian family of distribution. So Professor Jayasri, you are invited to present your talk.
Good morning, one and all. Thank you for giving me this opportunity. And I thank the organizers for conducting this particular international conference every year. And you have given us the platform so that all of us can exchange our views on research and proceed further. If there are any doubts or anything, we can discuss and we can proceed further. Thank you for giving me this opportunity, sir. Thank you. So just a moment.
Yeah. Yeah, presentation is come. Yeah. Yeah. Okay, fine.
I think all of you can see the slide. Is it visible, sir?
Yeah, it's visible. It's visible.
Okay, thank you, sir. So my topic is a study on properties of Pearsonian family of distributions. As all of us know, we have many distributions defined in the literature, and among these particular all these distributions are whatever are the distributions we have discrete probability distributions as well as continuous probability distributions, which are divided depending upon the continuous and discrete random variables. So on the similar basis, we have the division of the distributions depending upon their nature as Pearsonian distributions, TX family of distributions, power series family of distributions, and so on. So this particular Pearsonian family of distributions has been initially introduced by Carl Pearson in the year 1894, who made an attempt in proposing a family of distributions and identified as four types of distributions, which he named them as type 1 to type 4. In addition to the normal distribution, which was initially identified as type 5. The classification depends on whether the distributions were supported on a bounded interval or on a half line or on the whole real line, and whether they were potentially skewed or necessarily symmetric. So depending upon their boundedness condition and depending upon their symmetricity, all the distributions were divided into the Pearsonian distributions. Later, Carl Pearson in 1901 defined the type 5 distribution, which is the normal distribution. But now for it, we have even the inverse gamma distribution added to it, and also introduced the type 6 distribution. Rind in 1909 devised a simple way of visualizing the parameter space of the Pearson system and Pearson system. And Pearson in 1916, in his third paper introduced some special cases and subtypes from type 7 to type 12. The Pearson types are characterized by two quantities commonly referred to as beta 1 and beta 2, which we already know that they are nothing but the skewness and kurtosis of any distribution. So Normal Johnson in 1949 introduced certain curve systems that were created using the translation method. Nock in 1950 derived certain power series distributions that can be used to construct a wide category of random variables with discrete probability distributions. John in 1960, in his thesis on some contributions to the evaluation of Pearsonian distribution functions, gave a report on the construction of extended tables of percentage points of the Pearson system of distributions. So he constructed the extended tables, and Odd in 1967 developed a system of discrete distributions using difference equation. Mitra and Romnick in 1973 developed new procedures for estimating parameters of the Pearsonian type 1 curve, which are particularly adaptive to factors influencing the pattern of age-specific fertility rates. So the application of this particular type 1 has been done on age-specific fertility rates. Sankaran and Unnikrishnan Nair in 1998 characterized the Pearsonian family of distributions by finding the relationship between the failure rate and the higher order moments of residual life. So application of these particular Pearsonian distributions has been done on the failure rate as well as on the residual life. They also presented a characterization theorem for failure rate class of distributions in the Pearson family. Mahanta and Dilip in 2007 estimated parameters for type 2 of Pearsonian system of distribution curves by using the method of maximum likelihood. Mohammad Shakil and et al. In 2010 and 2011 derived a new family of distributions based on generalized Pearson differential equation, which is a natural generalization of the generalized inverse Gaussian distribution. Some characteristics of the new distribution was obtained. Plots for the cumulative distribution function, probability density function, hazard function, tables with percentiles, and with the values of skewness and kurtosis were provided. As a motivation, the statistical application of these results to the data on forestry has been studied. It was found that this newly proposed model fits better than gamma, log normal, and inverse Gaussian distributions. They developed some new classes of continuous probability distributions based on the generalized Pearson differential equation and studied the distribution relationships also. Mohammed et al. In 2012 also used a Pearsonian system of frequency curves for the analysis of stock returns. Mahanta and Dilip in 2012 applied the Pearsonian type 3 curves and its potentials in the analysis of insurance data. Rai Kundalia in 2013 applied Pearsonian type 4 distribution to improvise the confidence limits of coefficient of variation of the data on the yield of wheat crop. Lehecin in 2013 proposed a new extended model of a Pearsonian distribution and named it as the extended generalized distribution. Various properties of this family were studied by them. Shakil and et al. In 2016 studied the expanded Pearson system of differential equations and derived a new types of continuous probability distributions. In another study, several characterizations of a new type of generalized Pearson system and their truncated moments were also studied. Honji, Van et al. In 2019 estimated the parameters of an autoregressive model and a Bayesian model which was constructed using the Pearson type 7 distribution as the noise model. Tegos et al. In 2020 provided new results for Pearson type 3 distributions and applied them to look at the statistical behavior of wireless power transform for the first time in literature. Provost in 2022 introduced a moment-based density approximation method based on generalization of Pearson system of frequency curves. So this particular applications of the Pearsonian family gave me a trigger that I should study about this particular family of distributions. So before studying this particular family of distributions, we had gone through the 10 families which are important in the statistical distributions. Carl Pearson, that is Pearsonian family, Johnson, which is Johnson's family, and Koopman introduced exponential family, Noak introduced power series family, Alzer introduced TX family, Shaw and Buckley introduced transmuted family, Merovi and introduced generalized transmuted family, and Al-Kadib and Mohammad introduced cubic transmuted family. Cordero and D. Castro introduced Kumaraswamy G family. Mahadavi and Kundu in 2017 introduced alpha power transformation family. These are only some of the families of distributions mentioned. Pearsonian family of distributions, as all of us know, are defined based on the differential equation f of x dx plus b naught plus b1x plus b2x square by a plus x df equal to 0. And the Pearsonian distributions are characterized by two quantities, that is the skewness and kurtosis, beta 1 and beta 2, where a is nothing but it is b1 and it is defined given by this particular formula, and b naught is given by this and b2 is given by this. Johnson family of distributions, which was introduced in 1949 by Johnson based on the transformation of the standard normal variable, and he proposed a system of distributions which are generated by using the normalization transformation. If f dot is the transformation function and gamma, delta, and lambda and xi are the parameters where delta and lambda are positive, then the general form of z is equal to gamma plus delta f of x minus xi by lambda. The distributions possessing this transformation or translation are said to be a Johnson system of distributions, which satisfy the distributions which satisfy this equation. They come under Johnson system of distributions, and the distribution can be bounded on the lower end, upper end, or both the ends. The Johnson family is further divided as SB, SU, and SL families depending upon their curvature. SL is the first transformation proposed by Johnson, defines the log normal system of distributions, and it is defined by as it is given here. SL curves cover the log normal family, and SU is the unbounded system of distributions. It is defined as given here, and SU curves are unbounded and covers the T and normal distributions. SB is the bounded system of distributions defined by this particular equation, which the distributions which satisfy this condition come under the SB system of distributions, and SB curves cover bounded distributions. The distribution can be bounded on the lower end, upper end, or both the ends. Exponential family of distributions. Koopman made an attempt to express the probability distribution in the form this, where theta is the parameter. Then the distribution is said to belong to exponential family of distributions. The exponential family is practically convenient and widely used unified family of distributions on finite dimensional Euclidean spaces parameterized by a finite dimensional parameter vector as f of x theta equal to exponential a of x plus b of theta and summation over ci of x di of theta, where theta is the vector of k parameters with the axis of k real valued functions d1, d2, dk, and b defined on the parameter space, and Borel measurable functions c1, c2, ck, and a on the n-dimensional real space. So as we know, where if k equal to 1, then it is one parameter exponential family, and k equal to 2, two parameter exponential family. And here are some of the examples of univariate and bivariate exponential families. And normal, multivariate normal is one of the examples of k parameter exponential family. So for an exponential family of distributions, we can see the distributions and then a of x, b of theta, c of x, d of theta, and their curvature. Power series family. Noak in 1950 introduced a family of power series distributions. A probability distribution f of x theta is said to belong to power series family if it satisfies this probability function condition, that ax theta power x by f of theta, where f of theta is nothing but summation ax theta power x. And some of the power series distributions are binomial, Poisson, etc. And for a power series family of distributions, in the table given, we can see the distribution, probability function, what ax is represented for them, what theta power x, and what is f of theta, and their curvature. Tx family of distributions. Let f of t be the probability density function and f of t be its cumulative distribution function of a random variable t defined on the range minus infinity to infinity. In between, we have a, t, and b. Be a function of f of x of some baseline continuous random variable x. Then the tx distribution function is g of x equal to integrals a to c f of t dt, and density function a of tx is given by this. Distributions possesses which satisfy this particular property come under tx family of distributions, and several known continuous and discrete distributions are special cases of the first generated distributions. In case of T is discrete, this is the density function, and this is the distribution function, where P of T is nothing but it is the probability mass function of the baseline distribution. And Tx family of distributions, we can see in the table, Weibull exponential, that is the density function. And then what is C? G of x, the distribution function, the density function. F of t is the baseline distribution, and g of x is the density function of Weibull and exponential taken together. And this is the curvature. Similarly for Weibull, Rayleigh, and Gumbel and Weibull. Transmuted family of distributions. Shaw and Buckley in 2009 pioneered another prominent family of distributions by including a parameter lambda. If f of x theta is the distribution function, then the transmuted family of distributions is defined as g of x lambda theta. If lambda equal to 0, then it reduces to the baseline distribution. Transmuted family of distributions. Transmuted Burke, transmuted Gompels, and transmuted Weibull, and transmuted gamma. So for which this is the distribution function, and this is the distribution function of the baseline, distribution function of the transmuted family and their curvatures. Generalized transmuted family of distributions. And in this particular case, if f of t is the baseline distribution, then a function of the distribution function of the random variable x, such that if it lies, C lies between A and B, and C is differentiable and monotonically non-decreasing, then the generalized transmuted family of distributions is defined as this. And generalized transmuted normal, exponential, and Weibull. Their density functions, the distribution functions, baseline, as well as the resultant transmuted family. Cubic transmuted family of distributions. Al-Qadim and Muhammad in 2017 proposed cubic transmuted family of distributions by taking the value k equal to 2 in a general transmuted family of distributions. So this is the distribution function. And by setting k equal to 2, a cubic transmuted family of distributions is defined like this. And the general transmuted family reduces to the baseline if lambda equal to 0. Cubic transmuted family of distributions. Examples are cubic transmuted normal, logistic, Pareto, and Rayleigh, and their distribution functions, baseline, as well as the resultant, and then the curvature. Kumaraswamy G family of distributions. It was proposed in 1980 and proposed for a two-parameter distribution on 0, 1 called Kumaraswamy distribution, whose density function is this, with a distribution function this. For any baseline distribution G of x, Corderio and Castro proposed a Kumaraswamy G family of distributions with two additional shape parameters A, B, which will be positive. And the examples for Kumaraswamy G family of distributions are K Weibull, KW Weibull, and KW exponential, and KW Gumbel. So baseline, and then the resultant and their curvature. Alpha power transformation of distribution. Mahadavi and Kundu in 2017 proposed alpha power transform class of distributions with an additional parameter theta. The distribution function of this transformation class defined on baseline distribution function g of x is this, and the corresponding density function takes this particular form. Alpha power transformation of distribution. So examples are alpha power exponential and Weibull, alpha power transformation Lindley, alpha power transformed Pareto, and f of x, the density function and the distribution function. Pearsonian family of distributions. So as already I introduced this. As already I made a note that these are dependent upon the skewness and kurtosis nature of them. So um, these parameters describe the nature of the curve of the distribution and the properties of centrality of the data, variance in the data, symmetricity or skewness and peakness or kurtosis of the curve. Pearson initially classified the distributions into 7 types of distributions named as types 1 to 7 based on the values of the parameters. Later identified totally 12 types which are variants of 3 basic distributions, beta, gamma, and normal. The 12 types are described as Pearsonian family of distributions are defined based on the differential equation this. The Pearson distributions are characterized by 2 quantities, and it can be expressed as this. And Pearsonian family of 12 types of distributions, type 1 to type 12 is given in the table. Their density functions, the range, the support of the distribution, parameters, and the distributions which come under each particular type of Pearson distribution. Examples. And the distributions of Pearsonian and its parameter values. We can see how the distributions are distributed as type 1, type 2, type 3, etc. depending upon the value of k. K is nothing but it is 1 by 4 b1 square b0 b2 whole inverse. So here in the table we can see types 1 to 6, their density function, condition on the parameter, distribution curve, general, and curve properties are given here. If we observe type 1 is given by this density function, and the condition is k should be less than 0. K is nothing but 1 by 4 b1 square b0 b2 whole inverse, and this is the distribution curvature, and curve properties are limited in range, skew, usually bell-shaped, but maybe U-shaped or J-shaped or L-shaped, depending upon the distribution. And applications of the distributions is consumer behavioral analysis. And the properties of this type 1 are non-central moments are given by this mu1 dash, mu2 dash, mu3 dash, mu4 dash, and central moments are given by this, and skewness and kurtosis are given by this. This is the case of type 1. Similarly, for type 2, this is the form of the density function, support of the system, the graph curvature, and approximated by type 1, limited range, usually bell-shaped, but U-shaped when beta 2 is less than 1.8, and symmetrical. And this
Professor Jayashri, sorry to interrupt you. Can you focus only on the important properties of the distributions? Because we are running out of the time.
Okay, thank you. So like this, the various distributions of the Pearsonian family of distributions has been studied. And these are the properties: type 1, type 2, type 3, type 4, type 5, type 6, and then the table from type 7 onwards to type 12. their density functions, conditions, distribution curves, and the conditions on the curvature, and properties and applications in various fields. So these are the properties of type 7, type 8, type 9, type 10, type 11, and type 12. The Pearson distributions and its parameters values. So for type 1 density function conditions, distribution is beta 1, and beta 1 density function and its properties and the curvature. Similarly, it is given for all the types of Pearsonian distributions. Moments of truncated Pearson's family of distributions. They are defined like this by Shankaran and Nair in 1988. They have studied the truncated moments, and they are given by this. So distribution for gamma, the density function A0R, A1R, A2R, and DR. For each example, these are studied. And relationship between Pearson's discrete distributions. So the above where the Pearson distributions consists of discrete as well as continuous. So the discrete Pearson system is formed by those distributions F with probability mass function Fr over a regular lattice T of width 1, which satisfy the difference equation this. It can be equivalent to this also. And relationship between the discrete distributions. So under type 1, we have 4 density functions, formations, and these are the examples and the criteria, conditions on the parameters, their ranges, and their curvature. Similarly, for other types of the discrete Pearson system, and relation between the factorial moments was studied by Odd in 1967, and they considered the differential equation and they got the relations. Values of the parameters in terms of the first 4 moments are this. Generalized mean and variance for discrete Pearson distributions of type 3. So type 3 distributions are formulated from this particular differential equation, and this particular generalized mean and variance are derived for these particular distributions by me. So in this particular theorem, we have obtained the general mean formula for all the Pearson type 3 distributions. And this is satisfied by all the Pearsonian distributions, type 3 distributions. Similarly, for variance, we have obtained a formula. And the members of Pearson's family of distributions, type 3, discrete and discrete. So we have binomial, Poisson, negative binomial, geometric. We are adding 2 more distributions into this particular list, that is binomial derived power series distribution and Poisson derived power series distribution. These 2 also come under this type 3 Pearson family of distributions. And these are the density functions. These are the Pearson differential equation, and A value, B0, B1, B2, mean and variance. And all this mean and variance, we could derive them from using the generalized formula, and we found out that they are the same. Applications of Pearson family of distributions. These models, as I already presented in the starting, they are useful in many applications. Financial markets, they are used in biomedicine, demography, environmental, ecological, lifetime data, reliability, etc. So On the whole, we have studied the common properties of Pearsonian family, discrete and continuous. And also we have included two new distributions into the list of type 3 Pearson family of distributions. And also we gave a generalized formula for finding out the mean and variance for type 3 Pearson family of distributions. And these are the references. Thank you for giving me the opportunity. Any questions or suggestions, please?
Thank you, Professor Jayashree, for presenting this a thought-provoking and having the very rich information, not only in terms of the theoretical results that you have presented, but also you have talked about the applications of these Pearson family distributions. And congratulations for adding two more distributions to the type 3 Pearson family of the distribution. I'm sure that your contribution will enrich the existing literature in this family of distribution. So the session is open for questions. If any of the participants has any question, please feel free to ask. So any question? So I think there is no questions, and you have such a good presentation that I believe that all of the participant has learned and understood each and every concept. So that might be the reason for no questions there. So thank you, Professor Jayashree, for this insightful presentation. Thank you so much.
Thank you, sir. And I thank the organizers once again for giving me the opportunity. Thank you.
So next presenter is Professor K.S. Bhanu. Ma'am, are you present here?
Yes, sir. Namaskar.
Namaskar, ma'am. So Professor K.S. Bhanu has served the Department of Statistics, Institute of Science, Nagpur, and she is the former head of the Department of Statistics. And ma'am, let me know you years before I have read an article by you in Resonance.
Yes,
that
sir.
is the surprising results on the correlation coefficient.
Yeah.
So I think that you were, apart from being in academics and in the core statistics, you are writing the articles on the popular aspects of statistics as well.
Yes.
And this is the huge contributions, because most of the time we confined only to the theoretical results, which is understood only by the scientific community. So we need to expand our wings and need to make the common people aware how strong is the statistics and how in the different areas of our day-to-day life they have applications. And I was just scrolling the Google about you, and I get to know that you have initiated this track program also in the department,
Yes, sir.
which consists of the quiz kind of programs, and which is very helpful in not only learning the basic concept in statistics, but also popularizing the statistics among the students.
Yes.
So we are we feel honored to have you in this session, and I invite you to present your research, which is titled as Activity-Based Teaching Learning Approaches in Statistics.
Thank you very much, Dr. Pramil Kumar, for your nice, kind words. It has been our endeavor all along to make statistics teaching interesting for the students. I have been a teacher of statistics for more than 3 decades, and I retired recently. During my career, I have often found that students have struggled to understand the basic concepts of statistics. If we directly jump to the theoretical part or start with theorems, big theorems, and so on. And I have also been on the selection committee of some teachers, and I have found recently that when I take practical viva or when I go for an interview, and when I ask simple questions to the teachers of statistics, young teachers, they are not able to explain the concepts properly. That set me thinking. Recently, since I have retired, I have plenty of time. So I started some review work on how to use activity-based how to teach statistics using activity-based work. In the process, I came upon many papers, and I'm in the process of writing a review article along with one of my students, Dr. Mukta Deshpande. So when sir asked me to present, I thought, why not talk about some innovative ideas? Why not present some innovative ideas that have come across? This is not my original work, but this is part of the review work that I'm carrying out. So let me first of all share my, try to share my work. Oh. Are you able to see the screen, sir?
Still not, ma'am. It's
How should I? Okay. Now
it's coming up. It's coming up. Yeah, you can do it in the full view.
Yeah. Is it okay?
Yeah, it's fine, ma'am. It's fine.
So as the title indicates, it is an activity-based teaching learning approaches in statistics. So I will not be speaking of pure statistics, but the way to teach statistics in the class. And I'm sure this will be useful for young faculty members and young students who are in this audience, and maybe the seniors also may get some idea. So my outline of this talk will be only on the approaches. What are the approaches in teaching statistics? And this talk is based upon some papers with an emphasis on hypothesis testing, particularly this talk, because that way I cannot cover all the aspects of teaching. So I've just concentrated on hypothesis testing. We all know that statistics is a core subject in many universities in India and abroad, and it has been included as a major and minor subject in many degrees offered in our country and elsewhere. The new education policy of UGC has just come into force, and it has been adopted by all universities, and many also have started implementing them. With the NEP coming into force, we know that students are expected to choose different subject combinations and are at liberty to try various combinations. In this context, our subject has gained special significance as it is an integral part of many interdisciplinary subject combinations, and more so now with data science entering the field, study of statistics has become all the more important. Learning statistics is important. We all know that as teachers and students of statistics, as it provides the capacity of conducting logical reasoning and critical thinking, enhancing interpretation and evaluation skills, and facilitating dealing with highly abstract concepts. However, as I said earlier, many students, both from science as well as non-science backgrounds, find learning of statistics difficult, which leads to a high level of statistical anxiety in them. Now, to facilitate the understanding of different statistical concepts, several methodologies have been proposed. Among them are the two popular approaches. One is the active learning and the flipped classroom model. We are all familiar with the active learning model because we do it all the time. The active learning actually involves engaging students in hands-on activities. We do that when we give problems in the practical class, group discussions, case studies, data analysis, and interactive exercises. That I think is adopted by all of us everywhere. Now, what are the benefits of this active learning? It increases. There is an increase in the student's confidence in understanding statistics as the student directly takes part in the hands-on activities and group discussions and interactive exercises. Increased knowledge retention because he or she does the actual work, and so he or she understands what he or she is doing. And so there is an increased knowledge retention. And there is an improved students' performance. Naturally, the performance of the students gets increased. There is a saying in English that if I hear, I forget. If I see, I remember. And if I do, I understand. So that applies to our active learning. Now, what is flipped classroom approach? The flipped classroom approach involves students learning the course material outside the class through pre-recorded lectures or online resources and using the class time for interactive activities, discussions, and problem-solving exercises. I think the flipped classroom approach is being now slowly being adopted in all Indian universities also, because now there are plenty of videos available online and students are encouraged to use this approach to supplement their knowledge. What are the benefits of this flipped classroom approach? Learning at their own pace. The students can open their videos at any time they want to and learn at their own pace. And knowledge acquisition takes place outside the classroom so that class time can be devoted to more interactive activities. If we incorporate these two, I think teaching can become more effective. Now, researchers have actually found, they have done this exercise and they have found that there was a positive impact in the students' attitude and performance when they used this flipped classroom approach. Particularly Wilson and Winquist and Carlson. The reference numbers are 4 and 5. I do not know how they have not come. They have been listed in the reference. They found that students who took an introductory statistics course using the flipped classroom approach outperformed the ones that took the same course in the traditional lecture-based approach. So this was one major advantage they found out. Now, along with the flipped class learning, if we introduce gamification, games also inside the teaching learning process, then this promotes students' cognitive engagement better than the other two approaches. So there is a third aspect now, introducing games to learn statistics. Now, as I said earlier, that during my teaching career, I have taught many different courses, both at undergraduate as well as postgraduate levels. And I found that among other topics, hypothesis testing was probably one of the most misunderstood and confusing of all topics, especially at the undergraduate level. And I found that if the students did not understand the concepts of hypothesis testing at the undergraduate level, they carried this misunderstanding, I'll say, to the higher classes. Then they were always weak in other aspects as well connected to hypothesis testing. So that is why I started searching for articles, and I have come upon this presentation today is based upon 3 such work which I found interesting, and so I wanted to share it with all of you. What are the misconceptions? We all know that the misconceptions related to hypothesis testing include there is always a confusion between sample and population. I think all of us will agree that many of the students do have confusion regarding sample and population, failure to recognize the population parameter to be tested. When you give a problem, this is always a problem with the students, and whether more than one population is involved. Difficulty in specifying the null and the alternative hypothesis and determining the rejection region. Misinterpretation of the significance level as well as the p-value. It's not restricted to this only. There are other there is a lack of understanding of hypothesis testing procedure itself. Students often struggle with the step-by-step procedures involved in hypothesis testing. It starts right from setting up of null and alternative hypothesis. If we give them a null hypothesis, they will simply say that the opposite of the null hypothesis is always the alternative hypothesis, without actually thinking what is the null and what is the alternative hypothesis in that particular situation. Selecting an appropriate test statistic, determining the critical region, calculating the test statistic, and making a decision. Somewhere, all these the students find it difficult. Of course, if you give the formula, if you give a formula for T, they will put in the values, plug in the values, obtain the calculated values. Then they do not know whether they have to look in for a two-tailed test statistic, two-tailed alternative, or a one-tailed alternative. The table values differ, we know that. So right from the setting up of the hypothesis stage to the decision-making stage, there is always some confusion in the minds of the students, especially at the undergraduate level. The misconceptions also include misinterpretation of the p-value, failure to reject or accept the null hypothesis, misunderstanding of type 1 and type 2 errors, lack of statistical power, etc. So most of the concepts require, there is some misconception in the minds of the students. These misconceptions hinder students' understanding of hypothesis testing and lead to errors in interpretation and application. Addressing these misconceptions through effective teaching strategies and interventions therefore becomes crucial for improving the students' comprehension of hypothesis testing. With this aim, I have reviewed 3 papers here, and I have reviewed the first paper that I'll be discussing today is by David Gomez et al. It was published in Mathematics in December 2020, and it's titled Improving the Teaching of Hypothesis Testing Using a Divide and Conquer Strategy and Content Exposure Control in a Gamified Environment. So what is this article all about? And I'm sure that once I complete this presentation, many of my young faculty members present here will get their own ideas to add to that when they start teaching this particular topic. So this particular approach that the authors have discussed, it is based upon 6 pillars. The first pillar is the divide and conquer. This involves analyzing the subject of hypothesis testing to identify the main concepts and their dependencies. By understanding the sequential progression of concepts, the approach allows for a progressive acquisition of knowledge, step by step, ensuring that students build the necessary scaffolds to master the subject. So the entire topic is divided part by part, and understanding of that particular aspect is given importance. That is why the term divide and conquer. Second, they use the flipped classroom methodology. The approach that they have proposed incorporates the flipped classroom model, where students learn the foundational concepts outside the classroom through short videos. This allows students to watch the videos at their own pace, facilitating self-directed learning. That is the need of the hour today also. The videos cover key concepts of hypothesis testing, ensuring that students have a sound understanding before understanding the master class. The master class is the usual class that they are going to attend every day. Then they have incorporated the content exposure control. In most of the traditional learning platforms, we are at liberty to move from one concept to another. In this particular approach, in hypothesis testing, we have to know that we have to move step by step. Concepts are often built upon one another. So if students move freely from one concept to another, it will lead to complication. So the approach proposed controls the exposure of new concepts, ensuring that each new concept is not presented until the student demonstrates sufficient knowledge of the current concept. This sequential approach prevents misconceptions from being carried forward and ensures a solid foundation of learning. The next one is the feedback, formative assessment and feedback. After once they have started building the approach, in this, the students' knowledge also has to be evaluated. So this approach evaluates the acquired knowledge and incorporates formative assessment and feedback throughout the learning process. Students are informed about their mistakes, and appropriate feedback is also provided to them. The feedback provided assists in narrowing the students' knowledge gap and facilitates learning through scaffolding. We have already discussed this active learning part. This is also incorporated in the proposed approach. It adopts a problem-solving approach where students, after each video, they receive a set of questions related to the concept explained in the video. These questions prompt the students to apply the knowledge analyze data, and make connections. So this active learning has been found to enhance the students' understanding, retention, and performance in hypothesis testing. And lastly, games have been introduced in this approach. So incorporating the game elements to increase the student motivation and engagement is also part of this approach. Students receive points because they have introduced games here. So naturally, some awards have to be given if the student completes that particular aspect. So students receive points as they complete the problems, and their scores are displayed on a leaderboard. The inclusion of game element enhances the students' motivation and attitude towards learning hypothesis testing. By incorporating these pillars, the approach aims to facilitate the understanding of hypothesis testing and improve the students' knowledge acquisition. Though these pillars have been written for hypothesis testing, I feel that it can be used for other topics as well. Now, how does this work? These are the learning tools that they have used: main screen, buttons. I'll show you the main screen right now. There are buttons, circular buttons, which lead to video lectures, square buttons, which the students for test, stars. The students are given stars if they complete some level. There is a ship, boy, and flag bearer. It represents the student's progress and position of the most advanced student. Score and leaderboard display the student's score and the ranking of the top 10 students. Video lectures are part of this application, and problems and questions are also part of this application. So this is how the application looks like. You see the green buttons. When you press any button, the type of contrast, say sample and population, these are the 5 concepts of hypothesis testing that they will study, they will learn using the flipped classroom approach. So as soon as the student presses the type of constraint, the mean or the variance, etc., there will be a video for this type of constraint. Once the student gets once the student studies or gets a knowledge about this type of constraint, there will be 6 tests given to him, 6 questions. So he or she has to press the test button and solve the problems given here. Once the problem is solved, the student scores the point. Once he completes this, he will go to sample and population. Once he completes this, he may go to the null hypothesis, the alternative hypothesis, the p-value, and so on. And the position of the student is displayed in this leaderboard. So this application has been devised incorporating all the 6 pillars that we have just now discussed. So what are the steps in the application? It is made up of video lectures. Each video has one concept of hypothesis testing and a small video, duration of only 5 to 6 minutes. Students can watch the video as many times as desired, and if they are unable to answer, they can watch the video again. But students can only watch the videos that they have unlocked. The other videos will not get opened automatically. The approach is based on problem-based strategy. And so keeping the difficulty level, keeping the level of the students, the difficulty level of the problems is designed in such a way that they can be easily understood by the students, but they have to be challenging enough because they are based on the concepts included in the videos. In all, there will be 6 questions related to the 5 concepts. For each concept, there will be 6 questions. And some of the concepts that they have included are the contrast, the sample, population, p-value, the null hypothesis, the alternative hypothesis, etc. So these questions evaluate the students' knowledge about each concept, and they are responsible for determining if the student can advance to the next concept or not. So if the student scores all the 6 questions correctly, he solves all the 6 questions correctly, he gets 2 stars. If he scores 4 and 5, if he solves 4 or 5 correct, he gets 1 star. In both the cases, he is allowed to move forward to the next concept. Otherwise, the next button will not open. Less than 4, he doesn't get any star. So he has to redo the questions again. So if he has to redo the questions, that means he has to go through the video again. Feedback regarding his mistake is given so that student can identify and rectify the error and move forward. This formative feedback allows students for better understanding and to correct their misconceptions about various aspects of hypothesis testing. For every question, he gets 10 points, he or she scored at the first attempt, of course. So a maximum of 60 points can be collected. For questions answered at the second and subsequent attempts, the student gets 5 points. Students who answer less than 4 have to repeat a level. They can, of course, improve their performance and bag the 2 stars and increase their scores as well. Scores are displayed on the leaderboard so that students know their position as well as the student who is at the top of the leaderboard. So this application seems to be very interesting in teaching hypothesis testing. Now an experiment was conducted actually to see the efficacy of this application. An experiment was conducted with 89 first-year students of industrial engineering who had enrolled in a statistics course. And it was conducted to evaluate the benefit of the proposed method with respect to the traditional method of teaching that is taking place. Now, what is the experiment and what are the findings? Sorry. In order to assess the students' knowledge acquisition, 2 questions were prepared based on each of the 5 concepts, 5 or 6 concepts. Each of the problems scored either with 1 if it was totally correct, half partially correct, or 0 for an incorrect answer. And this is one question. This is the usual type of question that we usually give in our practical class. And the students had to, the question posed was, provide your answer by identifying the type of contrast, the sample data, the null and alternative hypothesis, assuming a p-value of 0.003. Similarly, there was a second question. Okay, that question, like this, I told you that there were 6 questions. So they prepared this also, and the student had to just choose the type of contrast. If he was studying the type of contrast, only the question based on the type of contrast would be given to him, would be open to him, and he would click at one of this. If he is studying data sample, going to the next concept, he will be given questions related to data sample, and he has to choose the second column and press what is n, what is x bar, if it is based on sample, if it is based on proportion, and so on. Then if the problem is related, if the third concept is related to the null hypothesis, then what are these values here based on the questions? This is a second type of question, similar type of question. Here also the student has to provide an answer to the type of contrast, sample data, null and alternative hypothesis, assuming a p-value of 0.06 and significance level of 0.05. Remember that these are all based on the videos that they have been given. Now, what is the experimental design in the study? It involved 3 groups of students, G1, G2, and G3. Group G1 consisted of 10 students who used the developed application. So they used the app before they attended the master class. They had no prior knowledge of hypothesis testing. After using the application, they also attended the master class where hypothesis testing was explained. So they had dual advantage. Group G2 served as the control group and comprised 60 students who attended only the master class. They did not use the application. And group G3 consisted of 19 students who attended the master class first and later had access to the app for 1 hour. They experienced both the master class and the application, but the order of exposure varied. Some of them attended the master class, but they didn't use the application. In the first case, some of them used the application, didn't attend the master class. That also happened here. Now, 2 comparable questions were designed. So group G1 received question 1 immediately after their session with the app, and the second question after the master class. G2 and G3 received only question 1 after the master class because they attended the class first, whereas group G3 answered question 2 after using the application. In addition, now this design allowed for comparisons between the application and the master class G1 and G2, and also the comparison between students who use the application before or after the master class. So this is how this class before the class, that means before the master class, they learned it through the app. They answered question number 1. Class 2, they all attended, and then they were given the questions, and there was a comparative study carried out between from the scores. These are the findings. Now I'll just sum up the findings. First, the student scores in the scenario G1, Q1 were compared with those obtained in G2 and G3 question number 1. T-test showed a significant difference of significance. T-test showed that the differences were significant, indicating that the proposed approach was more effective to teach hypothesis testing than the simple lecture class. Similarly, a t-test between G2 and G3, that also, and G3Q2 was also found to be significant, indicating again that the proposed approach using the application after the master class significantly improves the knowledge. G2 did not use the application, G3 used the application after the master class, and that also was found to be significant. Similarly, the scores between G1 Q1 and G1 Q2 were compared. So the corresponding t-test provided a p-value close to 0.05, which seems to indicate that the lecture class reinforces the knowledge obtained from the flipped classroom. Though they studied using the flipped classroom, this group did better when they attended the lecture as well. So in conclusion, a new approach has been proposed for teaching of hypothesis testing, and it has taken into account different elements such as inclusion of video lectures, problem-based learning approach, and the approach included the mechanism for content exposure control also. The application incorporated games also, and so this was found to be very effective in teaching hypothesis testing. This is one paper that I found interesting. The second paper that I would like to share some of the points, I do not know how much time I have, but this is the use of jigsaw in hypothesis testing. This is a paper by Evangelistica and Hemingway from the University of Wisconsin. It was published in JSE in 2002. We know what is a jigsaw puzzle. We have all played jigsaw puzzles in our childhood, and we know that it is a fascinating game. And how it is used in hypothesis testing is also fascinating. So jigsaw is a cooperative learning technique that involves dividing the class into expert groups. The entire class is divided into expert groups, and then new home groups are formed consisting of one member from each expert group. So I divide the class into 5 expert groups, then I will draw one member from each of these 5 groups and make a new group that is called as a home group. The jigsaw techniques is particularly useful in understanding the concepts of like sampling and hypothesis testing. It involves dividing the class into expert groups and forming new home groups where each member shares their expertise. The approach helps students to compare different examples because they all come from different groups and develop their own generalizations. It's a great way to reinforce learning and improve their comprehension. How it is implemented? You divide the entire class into expert groups depending upon the class size. Each group learns a concept or different aspects of the same topic. In our case, of course, hypothesis testing. Then home groups are formed consisting of at least one member from the original expert group. Each expert group is assigned a specific hypothesis testing problem. In that expert group, students will work together to carry out an in-depth study of the assigned topic and become experts in their assigned topic. Each student becomes responsible for mastering a particular piece of the puzzle. So naturally, we'll treat each of them as a puzzle, and once they they join the home group, they complete the entire puzzle. That looks like completing the jigsaw puzzle, which they later will teach to their home group members. In the home groups, each expert teaches the rest of the group about their problem, procedure, and results. That is, in other words, they share their expertise and also learn from their peers. This collaborative approach enhances communication skills and encourages students to learn from each other. So this is a wonderful new way of teaching. The jigsaw technique requires the students to analyze, synthesize, and apply the knowledge. As they work on their assigned tasks and teach others, students engage in critical thinking and problem solving. There is a lot of brainstorming session also in the home groups, and so they emerge out with the complete puzzle, the puzzle completed. They learn to make connections between different pieces of information that they have gathered from their expert groups and develop a broader perspective of the topic that is being currently taught. By studying a single problem in their expert groups and then sharing each other's work in the home groups, the students are actually guided to recognize that they are procedurally doing the same kind of task but in different settings, thus actually focusing on the structure rather than the technical details. So their understanding is reinforced when they communicate their knowledge to other members of the group. This is a major advantage of this jigsaw technique. Now, how do we teach hypothesis testing using jigsaw? The class is divided into expert groups of 3 to 5 people each, depending upon the class size. Each group is given a worksheet with a story that involves a claim. So you can work with the worksheet and give them the story and then ask them to write about the claim. The claims may vary in 3 aspects. They can be the parameter to be tested, maybe about the proportion or mean, the rejection region, the conclusion of the test. These are things that they will have to write in their worksheet, discuss among themselves and come out with the solution. After completing this part of the activity, the teacher actually teaches hypothesis testing procedure. So the students are taught a summary of the hypothesis testing procedure. The terminology, the symbolic representation, they have not yet been taught that. They have been simply given the worksheet. And the step-by-step procedure are now introduced, except that till now, the significance level or type 1, type 2, this is not yet introduced. Now the students translate their earlier observations into the formal framework of hypothesis testing, H0, H1, and so on. To put the pieces of the jigsaw together, the class forms new home groups with at least one person from each expert group. Each expert teaches the rest of the group about the problem, procedure, and results. To complete the picture of the jigsaw puzzle, statistical jigsaw puzzle, students are asked to synthesize the results by noting the similarities and differences in their various tasks. At the end of the group activities, the teacher leads the students in a class discussion to summarize their findings and address any misconceptions or missed conceptions, any misconceptions or any conceptions that have been left out. So this is a new innovative way of teaching any topic, particularly hypothesis testing, in the classroom. So this is a worksheet that is present here. I'm not going to through the entire worksheet, but this is the problem is given here. Okay, the problem, I'll just read out the problem and then I'll quickly skip through the rest of the slides. Paul and Joshua are squabbling over which TV show to watch. Their mom suggested that they flip a specific coin. If it comes up heads, Paul would choose the show. If it comes up tail, Joshua would decide. Both boys were hesitant to agree, thinking that the other had an advantage. So the mom says that it's a new coin, so I'm sure it is a fair coin. With this story, the question asked here is, what is the mother's claim and what is the boy's claim? If the boys have a different viewpoint, what is their claim? What is the experiment design? So the instructor asked the students to design an experiment that the boys can perform and write the procedure. Then the questions are framed for the decision criteria, and then what the students have to conduct the experiment to gather the evidence, and they have to write the results based upon the decision criteria, ultimately answering these two questions. So this sort of worksheet can be prepared in our classes, and this can be circulated, and the jigsaw technique can also be adopted in our classrooms, provided we have the time and the availability to teach this particular topic. The third one, of course,
can we conclude it, because
okay.
session is to be ended at 12:35.
Okay. I'll just show the third one quickly in 2 minutes.
Yeah, sure.
This is a very simple exercise that can be taken in a introductory statistics course. You can see two ducks. One, the usual male duck has a neck which is green in color, and this duck, the green color, usually is to attract the female. Now the question, the purpose of the green coloring of the male heads is to attract the females. So can this be used in the statistics? How is this used in a statistics class? A student of biology class had come, and the question is, in a certain species, male ducks have green heads and females are all gray. The purpose of the green coloring is to attract the females. The question here is, are female ducks also attracted to the green color in food, for example, in bread? So if this is the question, how do they tackle the question? You can, this also can be taught. The concept of statistical hypothesis can be taught using the worksheet procedure. So the questions can be translated in this way: write the statistical hypothesis, and then ask the students to translate this in terms of P. Once they have translated, tell the students to gather the evidence, if that is possible. The student goes to the lake near the campus and selects 10 randomly female ducks. Each duck will be offered 2 pieces of bread, one plain and one dyed green. The student writes down which piece of bread each duck approaches first, and then she or he summarizes her information. So now is the time to define the random variables and ask for N and P. This is gathering evidence to make the decision. Then the next part is about arriving the conclusion. If female ducks were truly indifferent between green and plain duck, how many ducks of the 10 that would you have expected to choose the green bread first? Like this, we have to frame the questions to introduce the concept of probability and binomial distribution and p-value. Prepare a worksheet in this manner and ask them to answer each one of them step by step. So this is a very simple example that can be taken in the classroom. Identify the research, which can be used for identifying the research question, identify the parameter of interest, and then write the statistical hypothesis, actually collect data, find the p-value, and decide whether the p-value is small or large. And then some more things can be introduced with this small example, the type 1 and type 2 errors. If you prepare a worksheet, then this type of worksheet can be used for even explaining significance level, type 1 and type 2 error, and then what happens as the sample size changes. what happens to alpha, if you fix the level of alpha, how does beta change, and other things. And then ask them to write a short statement about the behavior of beta with respect to the sample size. So these are the three things that I wanted to share with you. These are some of the references where innovative methods, you will find some innovative methods for teaching statistics. And hopefully we may come out with a review article soon. Thank you very much for your patient hearing. Thanks, all of you.
Thank you so much, Professor Bhanu, for sharing these wonderful thoughts and igniting the minds of the teacher of statistics. And I'm sure that these are the days and these are the hours we need to implement the learning of statistics through examples and through self-doing. And you have rightly mentioned that in this era of technology, we need to rely more on the flip-flop kind of classroom learning rather than being the classroom teaching. So we need additional efforts to create the interest of the students. And the approach that you have nicely summarized, that gamification and formative assessment and the
content exposure, content control and exposure.
So I'm sure that these kind of tools will help in making the statistics popularizing.
And so much of software technology available, this can be easily done nowadays.
Yeah,
like our days, we had to depend upon chalk and talk and only textbooks.
Thank you so much, ma'am. And if you have any if any of the participants has any query or the questions, then they are most welcome to ask. I think there is no question. And since ma'am has been a wonderful teacher in these years, and I'm sure that every word of her has straight away been into their mind and the heart. Thank you so much, ma'am, for this wonderful talk and sharing your insightful learning.
Thank you very much, sir, for giving me this opportunity to present this work. And I thank the organizer, Dr. Satish Kumar, and all his organizing team for making me a part of this conference every year. Thank you again.
Thank you.
Thank you, madam, and both the speakers. Let us give a big clap to both the speakers, Professor Jayasri and Professor Kesari. And excellent talks, different way, in fact, very interesting too. And there is a very valuable talk to, in fact, the teachers.
For the young faculty members.
Yeah.
Food for thought.
Sure, yeah. And also, we are grateful to Professor Parimal Kumar for chairing this session. And once again, thanking you, professors, all the professors. And let us, we have now at 12:38. We have some more time for the next session. 12:45 is the next session. So, few minutes are there.
Ma'am, can I request you to send me your presentation through email, because
sure, sir.
This is wonderful.
Yeah, okay, sir. Thank you.
My mail ID is simple, parmil@yahoo.com.
I'll just note down. All small case letters, sir?
It doesn't matter, small or uppercase. They are
parmil@yahoo.com. Okay, sir. I'll just do it.
PARMIL.
Okay, sir. Thank you.
Thank you so much.
Thank you, sir.
So, Professor Satish, can I exit?
No, sir, if you are busy, okay. And in the meantime, you can also join with the session.
12:45. So please join.
Okay, Professor.
Okay,
thank you. Thank you so much. Thank you.
It's up to you whether you can remind and or attend other session.
Okay, thank you so much.
And name and the title are also sent it through. Send it
Hi, Professor. Namaste. Gidu is in the group.
Yes, sir. Can you hear me?
Gidu, please wait.
Okay, sir.
Sir. Shall we start, Professor?
Now it is time. Yeah, Gidu, please introduce the chair and help the chair to run the session in a smooth way, please.
Okay, sir.
Okay,
Sure.
Hi, I am Ayan. I am supposed to speak now, right?
Professor,
Just 1 minute.
the first speaker, you please wait. Yeah.
Yeah. Good afternoon
Good afternoon, all.
Just a minute. Student will just introduce the chair, Professor. Just a brief introduction. Gidu, please.
Okay, sir. Good afternoon, all. We are moving to the 18th technical section of WSTA 2024, which is a special invited section that shall be chaired by Dr. M.C.H. Batcha. He is working as head of Department Statistics, Osmania University, and Director, Center of Quantitative Methods. He has made significant contribution to both teaching and research, shaping the field in profound ways. We are really lucky to have you, sir, chairing this section today. Over to you, sir.
Okay. Thank you for the nice introduction. Now, in this session, we are having the 3 talks. So total the 90 minutes is there, and I request the speakers to complete within the stipulated time that is assigned. And so for each speaker, the 30 minutes. Now, I request the first speaker, Ayan Bhattacharya. Professor Ayan Bhattacharya joined the Department of Mathematics at IIT Bombay in 2020 as an assistant professor. Prior to that, he spent 1 year in Poland and 2 years in Netherlands for postdoctoral studies. So Ayan Bhattacharya has obtained his doctorate in statistics from ISI in 2017. His research work mainly focuses on the probability and statistics. He mainly interested in the problems related to the branching random walks and extreme value theory and non-parametric and semi-parametric statistics. Now I request the speaker to start the session, and out of the 30 minutes, so give the input about the contribution to 20 minutes and 10 minutes that you give for the discussion time. That what was suggesting it. Thank you, Professor.
Thank you, Professor, for a nice introduction. And let me share the screen.
Yeah.
Can you hear me? Am I audible?
Audible.
Yeah, you are audible.
Okay. Can you see the screen? Can you see the screen?
Yeah, now it is sharing it.
Okay.
Yes, it is visible.
Okay. 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 Hello, everyone. So, first of all, I would like to thank Professor Satish Kumar for inviting me here and giving me an opportunity to present my work in front of you. So today I'll be talking about minimum distance estimation procedure for power law data. This is a joint work with Bohan Chen, Remco van der Hofstede, and Beth Zwart. So first, my aim should be to introduce what do I mean by power law data, and then slowly towards the minimum estimation procedure. So that will be the plan. So first of all, we are going to say that X is a random variable which exhibits power law behavior if its tail is decaying as x to the power minus alpha for some alpha bigger than 0. Okay, so now what we are doing, we have a random sample from this x. Okay, so we have a random sample, and now we are interested in basically estimating this alpha. Okay, in this talk, we'll be mostly focus on non-parametric or semi-parametric techniques for the estimation procedure. So, of course, we need to assume that the random variables or the samples are continuous random variables. Otherwise, there are usual troubles. We have some way out towards that, but let's not focus on that. That we have done that in our paper, but let's not get into that. So, our aim would be estimating alpha, and this is the thing that we have at our hand. This is the physics definition of power. Okay. So a mathematical definition would be a little bit different that I'll come to later. But let's first see that how we can visualize, given a random sample, whether we can, whether it shows the power law behavior or not. So suppose we have IID or a random sample from the distribution function f. What we are going to do, we are going to order them. Okay, and from this ordered sample, what we are going to do, we are going to look at this plot. Here, what we are doing, we are plotting this I by n, and here I am plotting the log value of the observation, which is, or kind of the order statistic, and here I am plotting how many observations are in the right hand side of this observation. Okay, log of that ratio, and y minus to make it positive. Nothing else, because this is a ratio, so it will be negative, and this makes it positive. So overall, what you have observation, and then what you are doing, you are plotting in y-axis how many observations are. So in x-axis, we are plotting this log values, and in y-axis, we are plotting log of the fraction or minus log of the fraction, how many observations are bigger than this. Okay, so that's what it's going to do. We call it log-log plot. Once this log-log plot looks linear, then we can kind of convince ourselves, or kind of, this is a visualization of this power law behavior. Is it clear? And the main idea behind this is this. We have said that probability x bigger than x is something like x to the power minus alpha. So if I take minus log, then it becomes almost linear like relation between between this probability and the values x. Is this clear? And this can be thought of as a kind of sample or estimate of these probabilities. Okay, so let me move on. So here is a more mathematical definition towards this power law. So in mathematics, the name is regularly varying tail. What is regularly varying tail? Regularly varying tail says that probability x bigger than x is x to the power minus alpha times a function Lx. So if you remember in the first slide, I have not used this equality sign. I have used something like sim, which means approximately or roughly like x to the power minus alpha. Here I am making it precise. I am adding a function Lx. But here, this Lx will be something which is growing much smaller than this x to the power minus alpha. We will see some examples of this function L in later slides. For the moment, to move on or to give you the problem, let's assume, if it seems abstract, let's assume that this L is a constant, nothing else. So if this L is 1, then you will get Pareto. Okay, so with that understanding, let's move on. So suppose I have a sample from this random variable x, or from the distribution of the random variable x. Then what we are doing, we are looking into some estimator of alpha, which is proposed by Hell in a fundamental paper. What he is doing, he is giving, or he is saying that we fix a number k, or fix an integer k. What we are going to look at, we are going to take the x n minus k, so that is the n minus kth order statistic, or n minus kth largest order statistic. Now we are going to compute the ratios of the order statistics which are above this n minus kth order statistic, and then we are going to take, of this logarithmic ratios, I am going to take average. So for a fixed k, there are k many observations above this xn minus k, so I am taking this ratio and dividing it by k. As simple as that. So it means intuitively here, I'll get more into it slowly in the later slides, but let's just to make it more clear, what I am trying to say, that for each k you have an estimate for 1 over alpha. So of course the choice of k will matter, and we will slowly see that how much, or what are the kind of nice values of k. And this also makes this estimation procedure troublesome, because it's very difficult to statistically choose k. That's a major problem, because if you choose this k to be too small, then this ratio may not converge, because this will not rely on the many of the observations. On the other hand, if you choose this k to be large, then there is a very subtle problem. The problem is that then you are using much more observations which are not giving you enough information about the tail. So there will be some sort of there has to be some sort of way out. And what this PL fit procedure, or PL fit estimation procedure, or minimum estimation procedure does, they provides a choice of k in a data adaptive or a data driven procedure. Okay, here it is. So what they are doing, as I said, that for each choice of k from 1 to n minus 1, you have one estimate for this alpha. So what they are saying, that compute all this Hill estimate. Now what we are going to do, we are going to compute this Kolmogorov-Smirnov distance. But here one has to be very careful. The standard Kolmogorov-Smirnov distance usually relies upon the sample, the random sample, and just compute this empirical distribution function to the true distribution function. Here we are doing something completely different. What is the difference? First of all, once we choose this k, we have a choice of alpha. So what we are doing, we are taking y to the power minus estimate of alpha, because alpha is unknown. So the true distribution in our case is unknown. So I am making my truth, or I am telling my true distribution is somewhat like y to the power minus alpha hat. And then here what I am doing, here I am not using the empirical distribution function, but I am using conditional empirical distribution function. So I want to look at those ratios of this order statistics. They are not IID. This is completely different from the standard empirical distribution function. This is called tail function. Okay, empirical tail function, or actually the right name for this is tail empirical measure. Okay, so here we are dealing with much more complicated random variables here, which is ratio of order statistics. There are k many of them. I am averaging over k, and this is this. So for each fixed k, I have one value of this distance. Okay. Now what I am doing, I am trying to minimize this, the distance between this and this, and I am trying to minimize the distance. So I am finding out for which k value of k this distance is minimized. Now there are also some subtleties. What are the subtleties? Because this is a discrete sort of optimization problem, there may not be a unique choice. Okay, there might be many choices. So in such a case, what we are going to do, we are going to take the smallest value of k possible, because if you sorry, the largest value of k possible, because if you remember, I am using k observations. So the idea behind choosing the largest value of k means that I am going to use as much observations as much possible. Okay, that's the idea. Okay, sorry. And then I am going to define my estimate to be that value of k n inverse. Okay, that's the idea of this PL fit estimation, and this has been proposed in 2009, and the name of the paper is Power Law Distribution in the Empirical Data. This is a hugely cited paper for the practitioners. And why this is so useful, let me explain. So usually the subjectivity, as I explained, the subjectivity of the choice of k makes it very difficult for the practitioners. Now, if you look into this procedure, then, and sometimes I will show that how this k is chosen. This is based on some visualization technique and etc. But in this procedure, if you think of, you don't have to use any visualization or anything. It's more or less automated procedure. Okay, so you give me the data, I will perform this, and it will give me a k. It will give me a choice of k. It will give me a unique estimate of this alpha. Okay, so in that way, or not unique, we can make it unique. So in that way, we have some sort of automated algorithm for getting to the value of alpha rather than relying on other things. Is it clear? Anyone have any question regarding this? Then I can move on. Can I move on? Okay. So the question that we have asked, or in general the practitioners wants to know, is that whether the PL fit estimation provides a consistent estimate or not. So as I have defined what is the PL fit estimator, the question is that whether it is consistent or not. In our work, what we have tried to show is that this PL fit estimator is consistent if we make some assumption on the distribution function f. So what we are assuming for the distribution function, that the f, so the distribution function and the inverse of the distribution functions are continuous. Of course, these assumptions will be satisfied once the distribution function f admits a density. Okay. So, but there are some other cases where it does not admit a density, but f and f inverse both are continuous. Okay. So we have given some examples in our paper, but let's not get into that. So let me explain this problem in a more broader perspective, or in more words. So I have given you, so let me explain what do I mean by consistency. It's not very standard in the, this is a part of extreme value theory where this is not a very standard thing for getting consistency, because one needs to do two things. As I said, remember this kappa n star is the number of observations that I am using to get and to estimate this alpha. So I want this number of observations used to go to infinity in order to get a consistent estimator. On the other hand, this kappa n star I want to grow in such a way such that it doesn't get into the body. I want to be in the tail all the time. Otherwise, it will provide some sort of misinformation, or it will feed some misinformation in my estimate. So I don't want it to be somehow linear in n. So these things is assured by this, that this kappa n star grows with high probability sublinearly, something which is smaller than linear. But this is what we have proved, and this makes this whole thing work. And from these two kind of claims, consistency of PL fit estimator follows. Okay, this is what actually we have done. And here this kappa n star, let me explain a little bit more. This kappa n star is data adapted, so it is not trivial to use some sort of renewal technique immediately, because there will be no renewal, or this kappa n star will not be even a stopping time. So some martingale technique that cannot be used to get to the or to get the consistency of this estimator. Okay, those things will not work out because this kappa n star strongly depends on the data. Okay, so let me explain the model a little bit more. I don't want to go very far from here. So there are two competing models on this extreme value theory regarding this tail. One is this eventually Pareto, that is this probability x bigger than x, c x to the power minus alpha, where the c is a constant, and this behavior is after some large threshold xl. So in general, the form of the tail x less than xl may or may not be specified, so we'll call it a semi-parametric assumption. The main problem will be to estimate alpha and xl. And of course, this is a kind of auxiliary parameter. This is the main parameter. Okay, so this is what Hill's work is. As I explained, that usually this is what he has suggested, that we can take this to be the estimate. And now you can check that if f is a Pareto, then HNN, it's going to be MLE of 1 over alpha, because you can check that this log of these ratios are basically going to be, so x n minus n, if you put, because I am using this k equal to n, so I'm taking x0 n to be 1. Okay, so if you look at this logarithmic ratios, then it will be standard exponential, and this will be a sample average of standard exponential, and it's not standard exponential, exponential with mean 1 over alpha. So sample average estimates the population average. That's what this statement is for. In general, if it is not Pareto, but it is, we called it eventually Pareto in the previous slide. If it's an eventually Pareto distribution, then we can choose this kn in this way. Okay. Okay, now let's look at some plot. So this is for Pareto alpha equal to 1. You can see that this log-log plot almost looks like linear. Now this is a log gamma distribution. Log gamma means if you take log of the distribution, or log, so y follows log gamma distribution, if log of y follow gamma distribution. Okay, so this is how it looks, but this is completely different from Pareto, but they look almost linear. Okay, and here it's a absolute Cauchy distribution with alpha equal to 1. Here you can see the idea of threshold. So if you go up to this point, something like 0, okay, so if it is up to 0 or something like that, then you can see that there is a 0 means here 0 means 1, right? Because I am plotting log of mod of x. Okay, so if mod of x is bigger than 1, then you can see there is almost a linear plot. Below that, it is not. Okay, so it's a concentration near 0, and this is the tail behavior of this absolute Cauchy. So in order to put all of these things together, so what is proposed in statistics is this semi-parametric model. Okay, this semi-parametric model does what? This allows this function, it allows to include a function Lx, and we call this L to be slowly varying. What do I mean by slowly varying? It can be described in this way. Okay, but this is a bunch of functions. This is a class of function. It's not one or two functions. It's a class of functions, which makes this parameter space kind of semi-parametric. So we have an estimate alpha, which is in something positive, and then there is a class of functions which satisfies this, which makes it semi-parametric problem. And then, then you can choose this Lx. So I have given some choices of Lx, which you can verify that they satisfy this equation, and hence they are working all right. But the main point is that all of these functions grows or decays much slower than x to the power minus alpha. That's the whole idea. So you can include any such function, and you can you have to estimate this alpha, and it's statistically very difficult to distinguish with same alpha and with these choices of Lx. You can do some visualization and you can see yourself. It's very difficult in general. If you plot them in the same graph, it's very difficult to distinguish the behavior of. Okay. So how much time do I have, Professor? Hello.
10 minutes.
10 minutes. Okay. Okay. Thank you. Thank you. So here, what I wanted to show is that the thing that I have said, that this kappa n star going to infinity, so it's increasing and it's also behaving sublinearly with high probability. So this idea came from this theorem of Mason. So in the paper of Bruce Hill, he derived the estimator HKN as a maximum likelihood estimate, but he doesn't provide the proof of consistency. Okay. So here the proof of consistency is there. Here this under the regularly varying assumption. So what this paper offers? So this paper offers that the consistency of the Hills estimator under the assumption that Xi's are regularly varying. It says that if we choose Kn such that it is increasing to infinity, but in a sublinear way, we call it intermediate sequence, then this HKNN turns out to be a consistent estimate for 1 over alpha. But again, the choice of kn is subjective. You can choose, let's say, for example, you can choose n to the power beta, right? Where beta is any number between 0 and 1, and then you can have this consistency. Okay. So the classical thing is what will be the choice? So there are, for practitioners, the choice is through some visualization, which is known as Hill plot. And for theorists, the choice is given by some sort of bias variance trade-off, which is given in this paper, Huesler and Trivels. But this kind of optimal choice needs the knowledge of this slowly varying function Lx, which is very difficult to get once you have a sample. Okay, so from the sample, it's very difficult to guess what is going to be the slowly varying function, and hence this theoretical optimal choice is not amenable to the practitioners. Okay, so let's look at this Hill plot, what it is doing. So what I have done, I have taken absolute Cauchy random variables 10,000, and then I have plotted this Hills estimate. Now you think of, or you can kind of easily guess that the absolute Cauchy random variable is kind of regularly, or it's of order -1. So if you look at the tail, you can show that it is roughly like x to the power -1. Okay, because there is 1 over x square at the denominator, and if you integrate on the numerator, it looks like x. So it's not very difficult to be convinced that it behaves like x to the power -1 Lx, some function Lx, which I don't want to describe. So the whole point is that Hill's estimate, if I use, that should give me the kind of, should be very close to 1, this number 1. So now if I plot this Hill's estimate for all choices of k, then you can see that this curve or this plot is touching this line alpha equal to 1. In y-axis, I am plotting the alpha hat. In x-axis, I am plotting the number of observations that I have used to, or number of order statistics that I have used to calculate this alpha hat. So now you can see if I use 2 small observations, then it's not that close to 1. If I use too many observations, if I use almost all observations, then I am very far away from this value 1. So it shows that I should not use all the values of 1. Now, if I go back to the absolute Cauchy picture, then you can also see that the small values of x, when I showed you that when the mod x is bigger than 1, then it looks linear. If I use smaller values of x, then that is not going to be linear. And that's why these two pictures are kind of complementing each other. So that is quite imaginable. So now here I am taking exact. So I'm using this xi's or Pareto with alpha equal to 10. So now you can see I'm plotting 1 over alpha. That's why I have plot 0.1. So 1 over alpha is 0.1. Now you can see that if I compute this Hill's estimate, then it behaves very nicely once I have taken large number of observation into account, or large number of upper order statistics to get to this value of alpha. So maybe there is not enough time. So this is another this is a mixture of uniform and Pareto, and there it looks very different, this plot of Hill's estimator. So for the interest of time, let me go to here. Let me go to this picture and let me stop. So the whole idea here is that if you use this sort of Hill's estimator when f is log gamma, that sort of distribution, then you will get this blue curve, which is going far away from the actual value of alpha. And here, if you use this PL fit estimator for this estimation of alpha, you will see that it is very close to this actual value of alpha, however large the observations. That motivated us to prove the consistency. To prove the consistency, we need some sort of tools and techniques from asymptotic statistics. I'm not going to use this. Just let me go to the last slide. Yes. So these are the tools, or these are the ingredients for our proof. So we have to use the Glivian-Quintela theorem, quantile process convergence, and maybe a kind of some sort of Vapnis-Renkovich bracketing number in order to get that, and we have to show some tightness of some process. Okay. So that's more or less our contribution, and using this we can prove that this is consistent. Okay. So this is where I would like to stop. And if you have any question, I'd be very happy to answer them.
Thank you. Any queries from the participants or clarifications? Any queries? Thank you, Professor Ayan Bhattacharya. And just can you specify the real-time application of the minimum distance estimators and whatever the way, when the hill estimators that you are suggesting in the real-time situation for any of the simulation studies or any other?
Yes. Yes. So here, this PL fit estimator, let me go back to where I'm doing this PL fit estimator. So this PL fit estimator is more known because of its AI, artificial intelligence, or automated structure. So it's basically automated. Once you feed the data, you don't have to do anything. Computer will do everything. You don't have to touch it. But when you go for this Hill's estimate, then you have to look at this visualization. You have to look at the values of K where this estimate stabilizes. And that choice of K is basically an eyeballing technique, and it depends, or it varies on person to person. So if we see the same picture, we can come up with different values of K. Whereas if I give this to the computer, then it will give me a unique choice of this alpha, and there will be kind of no confusion or no sort of subjectivity into it. So in that way, this PL fit estimator is preferred over this Hill's estimator. That's the main reason why practitioners like this. And you can
generally in the real-time application, the situation of the physical conditions.
Yes, there are many such conditions, because if you look at any sort of profit distribution or any sort of how to say this, there is a huge literature on networks where they talk about scale-free networks. So you want to know how many edges the superstars have, or in a Facebook network, there it has been used like in a everybody uses this sort of estimate. So that is if you search this, you can get it. So it's there.
Thank you, Professor and Bhattacharya, for wonderful talk on the minimum distance estimation procedures. Now I request the next speaker, Anjana Mandal, and Madam, are you present?
Yes, sir, I am present here.
Yeah. It is a great pleasure to introduce Dr. Anjana Mandal. She is presently working as the postdoctoral fellow, Department of Mathematics and Statistics, IIT Kanpur. She worked as an assistant professor at Kharagpur College of Faculty, and also taught the honors graduation in mathematics during the period 23 to 24, and Institute of Postdoctoral Fellowship she received in 2024. The research papers in her credit. Now I request the professor to introduce on the give a talk on the testing of homogeneity of location parameters of several exponential population against ordered alternatives. Professor, I'm handing over to you and
Thank you, sir. So, is my screen visible?
yeah, it is visual, madam.
First of all, I want to thank Professor Satish Kumar for inviting me. Today, I am going to present on testing homogeneity of location parameters of several exponential populations against order alternatives. This is a joint work with my PhD supervisor, Professor Somesh Kumar, and Professor Marcos Poli from TU Dortmund, Germany. So these are the outline of my presentation. So we all know that among skewed distribution, the exponential distribution is one of the most widely used model with applications in reliability, queen theory, survival analysis, etc. So we consider a sample observations of size ni from ith group which follow two parameter exponential population with location mu I and scale parameter sigma I. We consider both these parameters are completely unknown and unequal. Here, basically, mu i's represent the minimum guarantee times for the response variable in the ith group, and the scale parameter sigma i's represent the mean times in addition to the minimum guaranteed times. So, in the literature, we see that generally in testing, hypothesis testing problem, the homogeneity of location parameters is considered against natural alternative. That means homogeneity of mu i's against the alternative hypothesis is taken as mu I not equal to mu j for at least one pair. However, situations may arise where the location parameters follow a natural ordering, like in dose-response experiments. An increased ingredient dose either increases survival probability and guaranteed effective duration, or may have an insignificant increase. Also, in quality control, new technologies are introduced so that the guaranteed lives of components increase and so the quality of product improves. Also, there are many examples like in 2017, Gill et al. Have considered data on the number of days of survival for the inoperable lung cancer patients classified into four groups such as squamous, small, adeno, and large. So now, based on the medical experiment, it is expected that the minimum survival times for patients with these four groups will be in increasing order. Also, the observations from these four groups are shown to be exponentially distributed. Also, in the investigation of the number of positive cases of COVID-19 patients, it is desirable that the minimum number of positive cases be in increasing order according to the population density of states. Here also the number of COVID-19 patients in specific states for a certain period is seen to follow exponential distributions. So in such cases, testing the hypothesis H naught, that is mu1 equal to mu2 equal to mu k, against the order alternative H1, that is mu i's are in a monotonically increasing order with at least one strict inequality is appropriate and informative. So, in the recently, Mondal et al. Have proposed several test procedures for testing homogeneity of means of normal populations against other alternatives when variances are unknown and unequal. And in the exponential populations, Dhawan and Gill 1997, Singh et al. 2006, Moira et al. 2011, they have proposed testing procedures for order restrictions among the location parameters. However, they have considered that the scale parameters are homogeneous, either known or unknown. But in real life situations, these known scale parameter or homogeneous scale parameters may not arise every time. So, and then in 2017, Gill et al. Proposed test procedure for testing homogeneity of, that means testing for the testing problem H0 against H1 when scale parameters sigma i's are unknown and unequal. That means the problem that we are considering. So that problem has been considered by Gill et al. In 2017. However, we have compared our proposed test procedure with those of Gill et al. And we have seen that the test procedures of Gill et al. Are quite conservative. And however, our test procedures achieve the nominal size very satisfactorily, and also these are very powerful than the test procedures of Gill et al. So therefore, in this paper, we consider this problem of testing homogeneity of location parameters of exponential populations against order alternative when scale parameters are completely unknown and unequal. And for these testing problems, we have proposed likelihood ratio test and two other tests based on pairwise comparisons of the minimum effects. So for developing the likelihood ratio test statistics, at first we have defined the null parameter space and the full parameter space. So null parameter space is denoted by omega naught and the full parameter space is denoted by omega, and these are defined here. And now to get the likelihood ratio test statistic, we need the MLEs of the parameters under omega and omega naught, and these values are obtained, and these are given in 3.1, and the MLEs of mu i's and sigma I are given in 3.2. One can see the paper of WSTA et al. There they have evaluated these estimators. That means the maximum likelihood estimators of mu I and sigma i's when there is a order restriction among mu i's. Now the likelihood ratio test statistic is denoted by capital lambda and it is given in 3.3. Now we reject the null hypothesis at level alpha if lambda is less than small lambda or small lambda is alpha quantile of capital lambda under H naught. Now for k, that means for k equal to 2, our problem becomes a 2 sample problem, and for that case, Pearson et al. Have proposed some exact test. However, for k greater than equal to 3, finding the exact distribution, that means the null distribution of lambda cannot be calculated in a closed analytic form. Therefore, for obtaining the critical point, we have used the parametric bootstrap approach. So what we have to do in the bootstrap approach? So basically, we have used the classical parametric bootstrap approach. That means here we first choose an estimator of the parameters and then samples are generated from the distribution, replacing the parameters by their estimators. So here basically we are using the parametric bootstrap approach for finding the critical point. That means for approximating the null distribution of the test statistics. Now you can see that under H naught our test statistics is location invariant. So that means that's why we can take the common location mu as 0, and so we generate bootstrap sample from the distribution X. That means bootstrap samples are denoted by Xij star, and as our test statistics is location invariant under H naught, so we generate bootstrap samples Xij star from exponential distribution with location 0 and scale Si, where Si is an unbiased estimator of sigma I, and which is defined in 4.1. Now, using this bootstrap sample, we need to calculate the MLEs of sigma I, mu I under omega and omega naught, and these values are given here. Now, the parametric bootstrap version of the test statistics is denoted by capital lambda star, and it is defined in 4.2. Now, using these test statistics, we can calculate the bootstrap critical point. So, for that, I have given here the procedure. Basically, here I have given the procedure for finding size value or power calculation. So, it's basically inside the size calculations, we need the critical points. So, for finding size or power values of the LRT, we need to perform two-step simulation. So, in the outer simulation step, suppose we want to calculate the size value for LRT. So size value means we need to generate samples under H naught, and under H naught all the mu i's are equal. So we generate for a fixed configuration of mu and sigma i's, we generate original samples from exponential populations with location mu and scale sigma I. And for this sample we calculate the test statistic value. And now for finding the size or power, we need the critical point. So for finding critical point, we make one iteration step, that is called a bootstrap iteration, and inside that, after performing that iteration, we calculate the critical points. Suppose those critical points are denoted by lambda star, and after repeating the outer iterative steps a large number of times, a capital H number of times, then after H times we will have H number of test statistic value and H number of corresponding critical points, and then we calculate the size value alpha LR, which is denoted by alpha LR as the proportion of times the null hypothesis, that means the test null hypothesis is rejected. Now this is the procedure for finding the size or power value. That means now for so how we are calculating the critical point using bootstrap approach. That means we are generating xij star from the estimated distribution exponential with location 0 and scale si, and using this bootstrap sample we are calculating the bootstrap test statistics lambda star, and we are repeating this procedure a large number of times, say capital H equal to 5,000. Then after capital H times we will have H number of test statistics values. Then we will suppose those are capital lambda 1 star, capital lambda 2 star, and capital lambda H star. Then we will calculate the alpha quantile of those values as the bootstrap critical point, which is denoted by small lambda star. Now for finding this power value, we need to take the original samples from under H1. That means we have to take the location parameters under order restrictions. Now as we are using the bootstrap approach, we need to show that the critical point which comes from the bootstrap approach converges to the original one. So that's why here we have proved that the conditional distribution of the bootstrap statistic lambda star converges to the null distribution of the test statistic original test statistic capital lambda. So for proving the convergence of this thing, we needed some result. So that's why we have proved some result in lemma 1. And then in theorem 2, we have proved the results. So basically, it states that the Kolmogorov distance between the conditional distribution of the bootstrap statistic lambda star and the null distribution of the original test statistic lambda converges to 0 as sample size increases. Basically, this theorem ensures us that the critical point which comes from the bootstrap approach converges to the critical point which comes from the null distribution of the test statistic. Now, other than LRT, we have also proposed two other test procedures which are called min-t and max-t test. So for that, we have defined pairwise hypothesis. Those are denoted by H0I and H1I. Now, our null hypothesis H0 can be written in this way: intersection of H0I and H1, which is the mu1 less equal to mu2 less equal to mu k. So that can be written as a union of H1I. Now, if we take a particular form of H1, that is H1 star, where mu's are in a strictly increasing order, then H1 star can be written as a intersection of H1i's. Now, based on this assumption, we have proposed these two test statistics. For that, at first we have defined a Barish-Fisher type test statistics for the pairwise hypothesis H0I versus H1I. So that is denoted by WI and it is defined in 6.1. Now we have proposed the test statistics min-t and max-t, and min-t is denoted by T1, and this is nothing but the minimum of the components W1, W2, and so on, Wk minus 1. And T2 is the max-t test statistic, which is the maximum of the component mu1, mu2, W1, W2, Wk minus 1. Here also we don't have any closed form, that means we don't have the null distribution of Wi under H0I. So that means it is not easy to get the null distribution of the test statistic T1 and T2. So for finding critical point, we use the bootstrap approach. Here the procedure of finding the bootstrap critical value is same as the LRT. So that's why I'm not discussing about that thing. So now these two test statistics reject the null hypothesis for that means if D is the critical point, then min-t test rejects H0 if T1 greater than T, and max-t test rejects H0 if T test statistic T2 is greater than the critical point, where E is the 1 minus alpha quartile of T2 under H0. So it is basically quite observable that LRT takes information from the whole sample. So therefore, it is desirable that LRT will be more powerful than the min-t and max-t. Still, we are proposing these two tests because LRT cannot give us information after rejecting the null hypothesis. So for post hoc analysis, MaxT can give us the simultaneous pairwise confidence interval for the successive differences between mu1s. So that's why here we have also derived the simultaneous confidence interval here. So simultaneous confidence interval for the successive differences between mu-i's, and that is given in 8.1. So here is the original critical point. However, we don't have the original critical point. So the bootstrap version of the confidence interval is given in 8.2. So as here also we have used the bootstrap approach. We need to show that the critical point which comes from the bootstrap approach converges to the original one. So that's why we have proved this theorem 4. And for that, for proving this theorem, we needed some results. So that's that thing we have proved in theorem 3. Basically, in theorem 3, we have shown that that means if x1 star, x2 star, and xn stars are bootstrap samples generated from exponential distribution with location 0 and scale s, where s is the unbiased estimator of the original population. That means the scale parameter of the population. Then this SS and then the bootstrap version of S, that means SS star, converges to the scale parameter sigma in probability. Now here, through an extensive simulation study, we have compared the size and power values of our proposed test procedure with the existing tests of Gill et al. So we have here, by taking several configurations for sample sizes, scale parameters, and location parameters, we have calculated power values, size values of the proposed test procedures. We have also computed the that means coverage probability of the simultaneous confidence intervals. So in table 1, we have reported the size values of our test procedures and the existing test of Gill et al. So for k equal to 2, mean t and max t becomes a two sample test, that we call t-test. So now from this table, here we have taken the nominal size, that is level of significance alpha is equal to 0.05. Now from this table, you can see that the size values of LRT is quite close to the nominal level 0.05. And also the size values of mean t and max t are close to the nominal level and close to the nominal level. However, for the Gill test, that means the size values are very much less than the nominal level. So that means Gill test is performing conservatively. That means their tests are very conservative. For k equal to 2, also you can see that the size values of our proposed test procedures are very much close to the nominal level 0.05. However, the size values of Gill's test are not close to 0.05. These are very much less than the nominal level 0.05. Similarly, in table 3, we have reported the size values for k equal to 9. However, here the size values of Gill's test are better than the cases of k equal to 2 and k equal to 3. Although these are not very close to the 0.05, however, these are better than k equal to 2 and k equal to 3. So from table 2 and table 3 and table 1 to 3, we can see that the size values of our proposed test procedures are close to the nominal level. However, the size values of Gill's test are very much, that means Gill's tests are very much conservative. Here we have plotted the power curves of our test procedures and Gill's test. Here you can see that the power values of LRT is that means more than all other test procedures. That means LRT performs better than all other test procedures, and the Gill's test is not good. And here also you can see. So here also we have tabulated power values of all the test procedures. Here also you can see that LRT performs better than all other test procedures. So, and here we have tabulated the coverage probabilities of our simultaneous confidence interval, which we have obtained using the MaxT test and those of Gill's test. Here also you can see that here the coverage probability of our confidence interval is close to the nominal thing. Now here I have noted the observations. So that means for k equal to 2, size values of LRT and the t-test achieve the predefined level 0.05 with a few exceptions. For k equal to 3 also LRT min-t maintain the pre-assigned 5% level. From the size values of the test procedure, we see that the power values of all the tests increase as the difference between the mu i's increase. Also, power values of test decrease if any sigma increases. Power values increase as sample sizes increase. Therefore, all the proposed tests give expected power behavior. And we have also seen that irrespective of sample sizes and parameter configuration, LRT is better than all other test procedures. Among max T and min T has higher power values when mu i's are in a strictly increasing order, and max T perform better than the min T when there is one equality among the mu i's. However, it is seen that Gill's test has less power value than all the parametric boosted test. However, for large sample sizes like 70, 80, 100, Gill's test is observed to give better power values than the max T test, but less than those of LRT. So now here we have taken 3 numerical examples. So in the first example, we have considered the tumor dataset of Gill et al. So here we take survival times of patients with tumor types squamous, small, adeno, and large. Now it is quite expected that the minimum survival times of these 4 groups are in an increasing order. And after calculating the test statistic values and critical values of our test procedures, we have seen that the null hypothesis is rejected. That means the minimum survival times of patients for the 4 tumor types are in increasing order. Now here we have considered a data set consisting the duration of remission by 4 drugs, and the observation corresponding to each drug are 2-parameter exponential distributed. It is noted that the scale parameters are different. Suppose mu I denote the minimum duration of remission time for drug I, then our aim is to test H0, that is mu1 equal to mu2 equal to mu3 equal to mu4 against order alternative hypothesis H1. And by calculating the test statistic and critical values of our test, we have seen that the null hypothesis is rejected. Here we have taken data sets that means the survival that means number of positive COVID-19 patients from of patient for March, April, and June 2020. We have considered the states of Orissa, Karnataka, and Delhi. And suppose mu1, mu2, mu3 denote the minimum number of positive cases in these states, then the QQ plot is that the observation in the 3 cities follow a 2-parameter exponential distribution. It is checked that the scale parameters are unequal. And our aim is to test this null hypothesis H1 against this order alternative hypothesis, H0 against H1. Now here I have reported the size values and the test statistics and critical values and the decision. And it is seen that the null hypothesis is rejected by LRT and min-t. However, max T and Gill's test cannot reject the null hypothesis. This is because there is very small difference between the that means minimum number of COVID, that means the estimators of mu I. So that's why max T test, Gill's test cannot reject the null hypothesis. However, LRT and min-t reject because these are powerful than these 2 tests. Now these are some of my references. Thank you.
Thank you, Professor Anjana Madam. Any queries or clarifications from the participants? A small question about the efficiency. Have you examined or compared the asymptotic relative efficiency with any other?
No, sir, I have not done those things, but later I will do this one.
Okay. You are reaching to the 0.05 nearly.
Yes.
Yeah. Some of the tests that what you told.
Yes, that means our test procedures. So here you can see table 1, table 2, table 3. So that means there is
Have you examined the asymptotic distribution of this non-parametric?
No, these are basically parametric tests. That means we have not derived the asymptotic. That means the asymptotic distributions are not considered here.
Because exponential specifically that you mentioned. Yeah.
Yes. We have just considered LRT and two other tests which are called mean T and max T based on the pairwise differences between the minimum of the, that means the estimators of the mu i's.
So these are the parameters also the multivariate.
No, sir, these are not multivariate. Here we have taken univariate exponential populace.
Only univariate. No, in some cases because you can also extend the same thing for the multivariate.
Yes, sir. Yes, sir. This is a good idea.
Thank you, Professor Anjana Mandal, for a wonderful talk on the homogeneity of the testing of the location parameters when the distribution is an exponential and for the non-normality. Thank you, madam. Now I invite the next speaker, Alicia Inyang.
Yeah, thank you.
Yeah.
Thank you.
Now I am inviting the Alicia Young. It is a great pleasure to introduce the Alicia Young. He received his national diploma in statistics from Aqua IBOM State Polytechnic and graduation from University of Iowa and MSc Statistics from University of Ibadan and doctorate received from River State University, Port Harcourt, Nigeria. He presently working as the faculty in the Department of Statistics, University of Circa since 2019. He is a member of Chartered Institute of Statisticians of Nigeria and also a member of Professional Statistician Society of Nigeria. He is a young researcher with great passion for research, data scientist, and a data analyst. He published more than 11 research articles in reputed international journals, and more than 7 papers are currently under review. His main research interests are time series analysis, modeling and forecasting, intervention analysis, impact analysis, event studies, regression analysis, time series econometrics, and health statistics. Now, I request Alicia Young to deliver the talk on intervention model based on exponential smoothing methods and ARIMA modeling of Nigerian Naira exchange rates. So now I am handing over to the speaker.
Okay. Thank you. Thank you. Hello, please. I'm coming. I'm on it. Good morning.
Yeah.
Hello.
Any problem?
Please, I'm trying to share this.
Share the PPT first.
I'm trying to connect. It's not connecting. Please, sorry. Give me some time, please.
Yeah. It is visible. Go to the starting page. Move to the starting page.
Please, are you able to see it, please? Am I on to you, please?
Yes, it is visible. Now you can start.
Okay. Okay, have you seen the starting page, please? Can you see the starting page? Hello?
Yeah. Hello.
Please, can everybody see the starting page?
Yeah, first page that you.
Okay.
Yeah, it is in the first stage. We can see that.
Okay, you can see that, right? Hello? Oh, we can see the first page. Yeah. Can you see the first page? Okay, fine. Thank you. Good morning from here, and happy new month to you all. I count this a great privilege to be part of this prestigious event. I'm by name Elisha John Iyang. Now, the world have a lot of intervention problems. Such in this presentation is the case of the economic downturn on the Nigerian Naira exchange rate. Thus, the topic of this presentation is titled Intervention Model Based on Exponential Smoothing Method and ARIMA Modeling of the Nigerian Naira Exchange Rate. Now, Nigeria's poor handling of the economic crisis has made exchange rate the country's main issue. This is made worse by our near total reliance on import for consumption and our need for foreign exchange from export of crude oil. Consequently, Nigeria's economic success is heavily reliant on the fluctuation of other global currency. The study is aimed at modeling exchange rate between Nigeria and Pakistani rupee during a financial slump, using an intervention modeling approach constructed on the exponential smoothing method and ARIMA model, with a view of making comparison. The data set used in this study is the daily exchange rate of Pakistani rupee to Nigerian naira, spanning from January to December 2016. The result revealed that the 2016 economic downturn had a negative impact on the naira, with a percentage change of 47.51. This implied that the rupees appreciated over the naira, such that 1 rupee was exchanged for 1.9524 naira compared to the period before and after the intervention. The economic recession was considered a step function with a delay of 1 period and a gradual permanent effect with a decay rate of 0.6. Comparatively speaking, nonetheless, the ARIMA intervention model outperformed the ETS model. Now, numerous predictive and seasonally adjusted mechanisms can be attributed to the concepts of Box and Jenkins, therefore becoming an exceptionally widely recognized technique in usage. The late 1950s saw the development of the exponential smoothing method, that's ETS, which serves as the foundation for some of the most effective forecasting technique. Now we can see that in Brown, Hot, and Winter. However, the ETS framework has been perceived as a technique of filtering and forecasting rather than a model built around statistical distribution. ETS has recently become designated as a statistical framework centered around statistical theories and rebranded as as an inventive state space algorithm. Now we can find that in Seung and Lee. A structure for evaluating the impact of an event on a time series of interest is provided by intervention model building, which was first developed by Box and Taylor. The process is thought to be affected by the intervention by changing its mean level. An illustration, extreme climatic shift have led to low animal populations. Another illustration that is relevant to this study is events of economic downturn on the comparative value of the naira with respect to Pakistani rupee. Exchange rate is one of the tools used to assess a nation's economic standing. It gives insight into the strength of a nation's economy, which explains why it is closely examined and kept track of. Foreign exchange has lately become Nigeria's vital nutrient because of her dependence on oil for foreign trade, in spite of the falling crude oil prices on the global oil market, and her utter reliance on import for a majority of consumption. In consequence of this, her wealth is strongly influenced by changes in various currencies across the globe. ARIMA model has been the cornerstone of intervention modeling for a long time. And among authors who have applied this technique include Rigmord et al., Moffat and Ian, Etuk et al., Ian et al., and there are a lot of scholars that have worked on this. Now, among the authors that have enhanced the intervention model through its integration with the exponential smoothing method are Terpero et al., Seung and Lee, Jakanathan, Ian et al. Therefore, this work seeks to explore the flexibility and adaptability advantage inherent in the exponential smoothing method by broadening the intervention modeling, which is primarily applied with ARIMA model to ETS model with a view of making comparison. Dataset and methodology. The dataset analyzed is the daily Pakistani rupee swap for in a unit of the Nigerian naira, spanning from January to December 2016, obtained from the CBN, Nigerian CBN. There's Central Bank of Nigeria website. The dataset was split into data point prior to intervention, that is from January 1st to June 20, 2020. After the intervention period, that is June 21st to December 2020. The statistical package for the analysis of this work is R language. Now, let YT be a time series. Suppose there's an event occurring which changed the trend in the series. This event is referred to as an intervention. If it occurs at time t equals to capital T, Box-Taylor 1975 proposed that the pre-intervention observation of n subscript t be modeled following the Box-Jenkins ARIMA model. Now, the ARIMA intervention model are given in equation 1. Now, equation 1 with a post function type, equation 2 with a step function type. The intervention analysis with ETS model is given in equation 3 to 5. Now, the first equation is what? Is with a step function type. Now, with what? With an ETS model that has an additive error, no trend, and no seasonality. Also, equation 4 is what? Is a step function type with an ETF error path that had multiplicative error, no trend, and no seasonality. Then equation 5 with a post function type and with ATS model that had what? That had additional additive error, no trend, and no seasonality. Where YT is a response variable at T, B, the small b is the delay parameter, the omega is the impact parameter, delta is the slope parameter, which range in this range, which are in this range. Now we have the Phi, the non-seasonal autoregressive parameter, theta, the non-seasonal moving average parameter, and now the ET, which is what the white noise term. Now, the indicator variables are defined in equation 6 and 7, which are the first one, equation 6 is the step function type, and equation 7 the pulse function type respectively. Result and discussion. The time plot showing the daily Pakistani rupee to Nigerian naira exchange rate span from January to December 2016 is given in figure 1, and we can see the figure 1 here. Now we will see where the intervention took place, just like it would define it down here. Now the graph of the series shows an upward trend, which was marked in June 21st, 2016 as point of intervention with value 1.9524 naira and keep increasing. From the plot, we can observe that the lowest exchange rate of 1.8923 naira on Monday 23rd May 2016, while the highest exchange rate of all time, 3.3217 naira, was witnessed on Monday 22nd August 2016. Now, the average exchange rate in 2016 is what? Is 2.4607 naira. ARIMA model in equation, sorry, this is on equation 12. ARIMA model in equation 2 and the ETS model in equation 3 described earlier are used to model the exchange rate data set. The suspected point where the intervention took place on the series were labeled by indicator function as given in equation 8, where T is where the intervention took place June 21st, 2016, and the intervention type is a step function type. Sorry, thank you. Data set on the daily Pakistani rupee to Nigerian naira exchange rate from January 2016 to June 20th, 2016 in figure 2 is used to calculate the parameter of the error part of the intervention model, and data set from June 21st, 2016 to December 31st, 2016 in figure 3 has been used to compute the parameter of the transfer function of the intervention model. And we can see here, these are the plot figure 2, we set figure 3, the post intervention plot, and this is the ACF and PSCF of the pre-intervention series. Pre-intervention plot against time shown in figure 2. The graph of the sequence exhibit a characteristic of a non-stationary series, also seen in figure 5, 4, and 5, with peaks at interval of unequal length, indicating the absence of seasonality. The series was difference ones to attain stationarity. The graph of the different series in figure 6, 7, and 8 indicate that the series is stationary. The series stationarity was further verified by a unit root test at phase difference because the augmented Dickey-Fuller test p-value is less than the alpha value of 0.05. The series is therefore determined to be stationary, as shown in table 1, which you will see soon down, rejecting the null hypothesis that the series contain a unit root. And this different series, graph of this different series, ACF and PSCF. This is a unit root test that shows that that the series is stationary since the p-value is less than 0.05. Applying the concept of box and checking, 3 models were tentatively identified and estimated ARIMA framework with their statistics are summarized in table 2. After the model has been determined and the parameter have been calculated, diagnostic checking is carried out to determine whether the fitted model is adequate. Utilizing the information criteria such as the AIC and BIC. When comparing to other estimated model, as table 3 shows that the ARIMA 111 model has the least BIC and AIC values, which are given as we see. By exploring the ACF and PACF of the residual of fitted ARIMA model, it is observed that all the coefficients of both the ACF and PACF residual are within the confidence bound, which will have it as well as plus minus 0.1525. Also, still on checking the adequacy of this model, we explore the box the Elgin box Q test Q36. It's also used to assess the adequacy of the fitted model. Table 4 shows that the model has no autocorrelation with a p-value of 0.4638, which is greater than the alpha value of 0.05. As such, the model fits the data well and is statistically significant and sufficient. To calculate the impulse response function, table 5, forecasting using the fitted model is applied to the initial few post series data. Now, figure 10 impulse response function suggests that B is equal to 1, which is what the delay parameter, meaning that even though the intervention took place on June 21st, 2016, its impact wasn't felt until June 22nd, 2016. And these are the impulse response function figure 10. We can see that a delay of one period, it was felt after a delay of one period, which is from 2. Now, the impact parameter with value of 0.3887 was significant with p-value of 0.000. That's in table 6. The positive sign of the intervention parameter indicates that there was an increment in the exchange rate. This implies that Pakistani rupees appreciated over the naira in the exchange rate market on Tuesday, 21st June 2016, such that one Pakistani rupee was exchanged for a unit of 1.9524 naira compared to the period before and after the intervention occurred, with a percentage change of 47.51 computed from the percentage change formula, with a percentage. Sorry, sorry. I have a little cough. Thank you. Huh? Sorry. Thank you. With a percentage change of 47.51 computed from that equation, the 2016 recession caused a 47.51% fall in the Nigerian naira against the rupees in the exchange rate market. The ARIMA intervention model is represented mathematically in equation 9. Now, the model was found to be statistically significant, adequate for the data set when diagnosed, which is seen in table 7 and in figure 11. Confirmed by the plot of the ARIMA 111 intervention model, an actual value fitted mirrors the actual value. You can see that in this is the actual value and fitted value. It mirrors themselves. That shows that this model, the arrived model was adequate for the data set. And now, a provisional specification of the simple exponential smoothing model, having additive error is presented in the light of the series lack of trend and seasonality. The model bears the initial, such as which is written as ETS bracket open A, N, bracket close, which stand for additive error, no trend, no seasonal component. The smoothing constant alpha, which control the flexibility of the level, is estimated as 0.7503, corresponding to intervention parameter. The intervention parameter, which is what omega was given as this, and also delta was given as that, with a delay of 1 period after the intervention. That can be seen in table 9. The estimates are all significant at 5% level. The impact parameter implies a negative change. That is, the 2016 global economic recession caused a fall in the value of the Nigerian naira in the exchange rate market, as with the Pakistani rupee. The ETS intervention model is represented mathematically as in equation 10. Now, the model in 27. The model in equation 10 was found to be statistically significant and adequate for the data, and this can be seen in the plot. We have the plot here. There's a fitted value and the actual value. They both mirror each other. That shows that the model fit the data well. Now, to assess the impact of this intervention, in conclusion, to assess the impact of this intervention, two approaches to intervention modeling, which are the ARIMA intervention model and intervention model based on the exponential smoothing method, were adopted in studying the influence of these external events on the comparative value of the naira with respect to the Pakistani rupees. Interestingly, results from the two approaches confirm that intervention, which is what the economic downturn of 2016, depreciated the naira value in favor of the rupee, such that 1 unit of the Pakistani rupee was exchanged for 1.9524 units of the naira. Models from the two methods passed diagnostic tests and were judged adequate for the series, with a perfect fit to the actual value when plotted. That is, the actual value and the fitted value mirror each other. Sorry. Nevertheless, the ARIMA 1-1 intervention model outperformed the ETS model, that ETS ANN intervention model, since it had the smallest estimated variance error, the AIC, and also performance metrics such as the MAE, the RMSE, than the ETS model, which contradicts the conclusion of Seong and Lee. Now, Seong and Lee in their work, they find out that exponential smoothing method with intervention model outperform the ARIMA intervention model. But in this case, it is the reverse. ARIMA intervention model outperform the ETS intervention model in this very work. Now, the ARIMA intervention 1-1 model produced in-sample forecasts that were found to be extremely close to the actual value, suggesting that the model is sound and that the method is suitable for the data set being studied. Now, we can find that, we can see here, let's go to table. These are the plot, the actual value and the forecasted value using the ARIMA 1-1 intervention model. We see that the value are close, the forecast is close. And also they are within the the prediction 95 precision interval. Now, this study backs up the arguments made by Stark-Wagin and Stashman that researchers should avoid using a single methodology that works for all situations. Instead, should alternate between many methods as warranted. Consequently, the impact of the 2016 economic downturn on the Nigerian naira and the Pakistani rupee exchange rate is characterized as having a gradual start but a long-term effect. Accurate focus from the models developed will help financial authorities, professionals improve their planning and decision-making process, as well as the value of the naira, since exchange rate projection is one of the most challenging uses of contemporary time series. Thank you for listening.
Hello, Dr. Nyan.
Yes, sir.
Any questions from the participants? Okay. Give one of the data that the efficiency is 46%.
Hello?
Yeah, is the efficiency is 46%?
Hello, I don't get that, please. Can you come with a question, please?
What is the efficiency that is evaluated for the data model when you are fitting it? I use the different the criteria. Am I audible? Hello?
Criteria, being the diagnostic criteria.
Yeah, for one of the data that I found that there is some 46% nearly the model is fitting that you have examined.
Sorry, I can't hear you clearly, please. Can you be audible, please?
No, the efficiency. What is the efficiency of the model? Or you are using the various efficiency criteria?
Yeah, the efficiency of the model. Now we explore the adequacy of the model. In terms of for adequacy of the model, we explore criteria such as the AIC, BIC, the algebraic text, and also the ACF and PSF of the residual LCF.
How much that you got?
So, sir?
How much the efficiency that you are getting?
Yeah, it's from here. Let me go down.
Yeah, in the previous table, yeah.
Oh yeah, this is a base table, you know. So yeah. You should. I remember one model give us the least BIC and AIC compared to other model in the pre-intervention series. Yes. And also now we can come down to the Edgeon block test. It shows that it gives us a p-value of 0.4638.
Sorry, you are getting the values as negative values.
Yes.
So AIC and BIC.
Yeah, AIC and BIC, yes. And I remember one model shows that it perform is lower. You know, the bigger negative value understand, kind of shows that is lower than the small negative value. Like for example, now -10 is smaller than -9.
No, you
And
have
and,
to.
and,
I think it is better
and
to verify it once the ASC, BASC values, maybe the lower, may not be this much of negative for the fitting of the model. And another also that you got some 46% is the efficiency that you are getting, which shows that the model is not the appropriately that is fitted for the data that what you have chosen. Okay, thank you, Young. Now I thank Professor Satish Kumar and Professor Riaz for giving us this opportunity and be as a part of this international workshop. Thank you, sir. Thank you for giving up this opportunity.
Thank you, Professor.
Thank you.
Bhattacharya for chairing the session. Thank you so much.
Thank you.
In fact, we are very much grateful to you, Professor.
Thank you.
And also, you have done a very good work. And in fact, there are 3 speakers. All the speakers are given excellent talks. Let us give a clap to all the speakers. Okay, and conclude in time. So we have to next session at 20. So, okay, thank you all. And once again, thanking you all. I hope Meenakshi is there in the group.
Yes, sir.
Okay, Meenakshi, please introduce the chair of the next session and do the needful for running the session.
Shall I start, sir?
Yeah.
Good afternoon, Professor Satish Kumar.
So, good afternoon, everyone. We are moving on to the 19th technical session of WSTA 2024, which is an invited session that shall be chaired by Dr. C. Vijayalakshmi. Dr. C. Vijayalakshmi is a faculty at the Department of Statistics and Applied Mathematics, Central University of Tamil Nadu. She has published 131 research articles in reputed journals and has also published 77 papers in conference proceedings. She is also an active member in Board of Studies PhD Doctoral Committee and also acted as PhD Viva Voice Examiner in various states and central universities. She is a recipient of many awards entitled Best Professor by ASTF, Pondicherry Government, VIT University and Bharat Jyoti Award in New Delhi. We are really lucky to have you, ma'am, for chairing the session today. So with great pleasure and honor, I invite Dr. C. Vijayalakshmi to chair the session. Over to you, ma'am.
Thank you. Good afternoon, Professor Satish. How are you, sir? How are you, sir? Am I audible, sir?
Yeah, audible.
Okay. Thank you, Professor.
Okay, welcome.
At the outset, I would like to extend my humble thanks to Professor Satish Kumar sir and Professor Riaz sir for giving opportunity to share this session. And we have in this session, technical session number 19, we have 5 speakers. And let me just list out the names of the speakers. Professor K.M. Shaktivel sir is here. Professor G. Sirisha ma'am. Are you here, ma'am? Hello.
Hello, Madam Shaktivel, first speaker is available.
Yeah, thank you, Professor. Sirisha ma'am, I'm just checking also. 1 second. Okay. Professor Ritam Grover. Professor Sambasivaram. Okay, yet to enter. Professor M. Ramakrishnan sir. Okay, it's okay. We'll just.
Others will join in the meantime.
Okay, no problem, sir. Good afternoon, Professor Shaktivel sir. And we welcome you to deliver your lecture on the topic Automated Thresholding Procedure for Extreme Value Analysis of Non-Stationary Precipitation Data. Sir, please, over to you, sir.
Thank you, Madam.
Oh my God. இது full screen எதுமா shortcut key? Control diagram. Okay, sorry. Okay, good. Sorry for the inconvenience.
It's okay.
Good afternoon. Good afternoon to all of you. So it's a great pleasure to joining twice in a year with Professor Satish Kumar sir and his team. So now I take up this opportunity to thank Vijayalakshmi madam. Now the topic of my talk is automated thresholding procedure for extreme value analysis of non-stationary precipitation data. So in my presentation, first I would like to give a talk about EVT, that is extreme value theory, and in which we have two prominent procedure adopted conventionally, and they are nothing but block maxima or otherwise called annual maxima, and the second one is a peak over threshold. These two are emerged from a two landmark theorem called Fisher-Tipper theorem and Pickens-Belham-DeHaan theorem. And by using these two, we have developed a new procedure called proposed another method, which is named as a dual pace threshold selection method. And we have used one real-time application and adopted these three methods and find the efficiency of this particular data set, and we observed some good result. So that is our conclusion. Now to start with, extreme value theory is nowadays one of the important field in statistics, which focus on predicting a rare event such as extreme value, market crash, and any natural calamity or anything. It's every day any common man is come across this kind of situation. So to studying such an extreme event is a very important task. So since these events are occur very rarely, but still extreme value theory provides a technique to estimate their probability by extrapolating them from a limited observed data. Why this field is important? Because one rare event will create a irreplaceable damage to this society. So therefore, predicting them well in advance and making an adequate measures will prevent us from such an undesirable outcome. So therefore, it is specially designed for extrapolating rare events. So extrapolation means the events which going to happen in future and rely on some asymptotic analysis formula extreme value models. So therefore, estimating these extreme values focus solemnly on the tile of the probability distribution. So therefore, the objective of extreme value analysis is to estimate how likely these rare events are, and even if they have not been seen ever before. So such a hard event, how we can predict well in advance. And I already told you there are the two classical approach which we usually adopt. One is a block maxima, another one is a peak over threshold method. When modeling using the first one method, that is called block maxima. So this modeling this block maxima, we have considered the entire data in a single stroke, and we convert them as each block mutually exclusive block, and we choose a maximum among in respective block and consider this as our observation for further study. So here the extreme value theory does not the same purpose of the central limit theorem does. That means central limit theorem will be used for average measure, but here we using sum of random variable in the place of average. So therefore, the theory indicates it's a limiting distribution. So the first theorem which evolved in this EVT is Fisher-Tipper theorem, which starts the rescaled and rescaled sample maxima converge in a distribution to variable having a distribution of a generalized extreme value theorem. So therefore, this approach discovers extreme value by taking a maximum value from each of this block and constitute a new sample. So this method divides observation period into a non-overlapping segment of equal size and restrict the focus only on the maximum observation and ignore the rest of the observation in each period. And this theorem states it will give you a limiting distribution. And if you see the statement of this theorem, this is derived in the year 1928. And from this equation, you can observe this is a limiting probability on the left-hand side. And it is same as a form of maximum x1, x2, dot, dot, xn minus bn divided by an, which is less than or equal to some value x, which converts to a some limiting cases, which is function of n. And when the large value of n, it will converge to a some limiting distribution. So it has three different forms. This conversion is possible only when the condition in the last line of this slide is satisfied. So it will reduced into three different parameters. One is location, scale, and shape parameter. And the cumulative distribution function of these three parameter generalized extreme value theorem is given in equation 2. And whenever this shape parameter approaches 0, then it reduces to two-parameter model, and the form of the model is given in equation 3, and which is none other than a Kumbal distribution. And whenever psi is 0, then it reduces to a Kumbal distribution, and the value of psi is strictly positive, then it is a pressure distribution, and it takes the negative value. This is nothing but short-tailed Weibull distribution. This is the density pictorial representation is given in this picture. So these three are the shape of this three distribution. And the second prominent method used in extreme value theory is Pico threshold method. What is all about is nothing but it is otherwise called a method of excess. That means what you mean when you have a random sample and you fix some threshold and you consider the value above the threshold and ignore the value below the threshold. The value above threshold is named as a exceedance. Okay. And the main concept of this framework is to select a suitable threshold because it is randomly selected. So the value will differ person to person. So this is one of the challenging tasks. And it can be shown that some sufficiently large value of threshold, the distribution values exceeding the threshold is approximately a generalized Pareto distribution. And this is confirmed by the theorem, Beckman theorem in the year 1975. And it reduced to a generalized Pareto distribution with two parameter called shape and scale parameter. And it is limiting and approximated distribution. And if you see, this is the distribution function of the generalized Pareto distribution with the two parameter is given in equation 4. And it is a generalized distribution. And if you see the particular value or particular distribution is ordinary Pareto distribution whenever the shape parameter psi is greater than 0, and whenever it is 0, it is an exponential distribution, and whenever it is negative, it is a short-tailed Pareto distribution. And the main problem involved in this Pico threshold method is setting the right threshold. And because if you are fix the threshold very high, the number of observation will be very less, and the increasing uncertainty, and it causes it reduces sample size, and it also is prediction or accuracy level will go down. Whenever you do it otherwise, you are fixing a threshold very low, many observations will come into picture, and it unable to distinguish between which is needed, which is extreme and which is not extreme, it unable to identify. So therefore still it is a open problem in research Pico threshold. Setting an optimum threshold is a challenging task. And therefore, in order to avoid such things, there is a fine-tuned mechanism in this parameter, scale parameter is taking place, and there are many other approaches. Here you can change this scale parameter of generalized Pareto distribution. You can convert the to new value of this threshold V and for given value of U, and you modified a new threshold, and you can do the similarly for the shape parameter. So therefore you will get a new modified scale and shape parameter. And another proposed third, we proposed another method by which you can get extreme values. So the main objective of this study is to, you will get a random sample, then you have to distinguish between which is exceedance, which is not exceedance. So you are considered the good exceedance, your model will be better enough. So in order to do it, we do this process in our proposed method in two phases. In phase one, we are fixing some trimming value as follows. For example, in phase one, suppose we have let x1, x2 dot xn be a IID random sample of size n, and we will perform Kolmogorov-Smirnov test. What we do here is we take minimum value as a initial threshold, and we compute a model for this using two different goodness of test, namely Kolmogorov-Smirnov and grammar of one mouse test. And we observe these values and keep on doing this by enhancing from the minimum value and increasing the value from 0.01, and we go up to 100% of the value. And we perform this two goodness of fit tests at 5% level. And keep doing, we are for each test we will get a different value of p values, and keep on we are observing those values and keep changing the threshold by increasing 0.01 from the initial threshold, and whenever you are increasing the threshold you will get a different values. And for each test you will get a different p values, but we consider only for this two pair of goodness of fit values, we consider only the maximum, and which value of maximum p value, the threshold value is corresponding threshold is considered, and that threshold value is we say delta, and we name it as this is called a DRIM value. Okay. And in phase two, what we are doing, we consider only the points above this trim point is considered, and the value below this trim point is terminated from the further study. And we further fine tune the threshold value by using entropy based threshold selection. So in order to do it, we consider again from the obtained or updated this trimming point to, we consider up to 19% of the value, and again we are performing this goodness of test and observing the value of p. And whenever we are doing it, and we will have two measures, and the same concept can be extended to many other goodness of tests. In case if you are extending more than two, then then we will come across a decision matrix, namely it is in the form of matrix given in equation 5. So here we are using two criteria. In case if you are using more than two, then you will get different criteria. In the row you will represent a threshold value, and in a column you represent the criteria of the or value of the goodness of measures. So this is how we will get a decision matrix, and we will pool all these values into a single measure. So by pooling these decision values as a single measure and normalizing this value, so this can be possible by using a relation given in equation 6. Then from this pooled value, we are computing the entropy by using equation 7. So you will get a different entropy. Then using the entropy, you will find the weight equation given in 8. Then you put together each evaluation criteria, and you give a different weight level, and you constitute a single measure called evaluation indicator criteria. So this will accumulate all the results and pooled all these results, and you give as a single value. From this value will be a better measure for obtaining a optimal threshold. So therefore, in order to get a optimal threshold, you have compute the value of Vj from the equation 9 and put all those procedures mentioned in this two-page method in a nutshell. You will come across this kind of flow chart. Okay, so this is how we will do it. In phase 1, we get the value and get the sequentially keep test and find the value of p, and keep on updating a threshold and find the value of obtain the value of p, and among this value, which value of p is maximum for two different criteria, and you will get the trim point. By using the trim point, you get the new concentrated sample. Again, you use different measures and keep going until 99 percentile. Then you normalize the value, and you can extend the concept in case it's more than 2 or 3, and constitute a decision matrix. From this, you can evaluate as a evaluation indicator that will help us a single measure to obtain the optimal threshold. So this is how we will go about and do the things. And whenever we are studying extreme value theory, your data may be stationary or non-stationary data. Okay. So this can be dealt accordingly. In case of stationary data, you can go with a conventional procedure that will give you a better result. In case of non-stationary, you have to proceed as follows. For example, you have non-stationary and stationary data. If you have a parameter of generalized extreme value, and the first number in this model represent the location, and second one represent the scale. So what we do, we are fine-tuning the parameter in 3 different transformation. One is called linear, second one is a quadratic, and third one is a cyclic. Okay. So of course, all of you are familiar with this. In the first model, the GEV00 represent all the 3 parameters in this model is constant. Okay. In case 10, the first parameter location 1 will be having a linear relation, other 2 will be, remain as a constant. So likewise, we will proceed. So here you can see GEV20, it represents a quadratic model, and it goes up to 2 values. And similarly, you can do it for next GP model, that is Pico threshold model. You will do all the 3 transformation. First one is a linear, second one is a quadratic, and third one is a cyclic. So these 3 model will be formed by using these relations. Now we apply these 3 method. One is a block maximum, second one is a Pico threshold, and third one is a dual phase method. We use it one real data set, namely we have daily maximum precipitation data obtained from flood affected regions in Tamil Nadu for 33 years, that is from the year 1991 to 2023 on daily basis, and maximum values observed along with the COVID called wind speed. And it is an the source of data can be obtained from NASA satellite, and it is given here. And we have categorized this data into 7 different categories based on the past experience. 7, we are classifying this total Tamil Nadu region as 7 different regions, namely R1 is Chennai, R2 is Chengalpattu, R3 is Thuthukudi, R4 is Tirunelveli, R5 is Ramanathapuram, R6 Virudhunagar, and so region 7 is Kanyakumari. And we use 2 different MK test and KPSS test. One is for the trend, and the second one is for a stationarity. You can use even decubicular test for using a stationarity. And to check this 7 region whether data is present or not. So in order to do it, the null hypothesis, there is no monotonic trends in the series, and alternative will be there is a monotonic trend in the series. From this, we conclude that there is no monotonic trend in the series. And further, we observed 3 different regions shows a stationarity, and the remaining regions shows a non-stationarity. However, the trend tests are not always effective in detecting the non-stationarity, and you can use KPSS test. And we form these models, say GEV00, and these are the parameter in each of this model. So here we obtain the estimate of this model, and within the parenthesis, what is the sampling error, the standard error of this estimate is given, and we compute the information criterion AIC, VIC, AICC, HQICC. From these applications, the objective study is a conditional distribution of daily maximum precipitation as a function of a wind speed. Okay, so therefore, this study attempts to examine the characteristics of precipitation extremes in Tamil Nadu by using the past 33 years of data. Okay. Then, in order to find the modified scale parameter, we use this parameter stability plot. So this is a 3-dimension plot. In x-axis we have a different threshold, and y-axis we have modified scale parameter, and in the top you can see the number of x's for each value of this threshold and this modified value of this modified parameter. And whenever this curve is stabilized, that value is considered as a threshold, as well as the number of x's you can get it from this plot. So we can't assure whether this plot is always work. So therefore we go for our 2L pace power proposed method. So that is an idea. Now, as I said, we evaluated new evaluation indicator because we pulled all the goodness of measure criterion as a single pole, and using that one, by using entropy concept, we evaluated one single measure, and this will help us to find the optimal threshold. So therefore, if you see the graph A, this is a 2 curve. So you're finding it which one is best, because it is zigzag, so uneven, and this is for a small, relatively clear, but there are some data which is very difficult to distinguish which is a maximum, and therefore whenever you use 5 or 6 measures, so this will not appropriate to use. So therefore we pulled all this into a single measure called a evaluation indicator. This will help us to give you one index, and which help us to obtain the optimal threshold. So from this P, which is combined these two, grammar one mouse and KS test combined as a single value, you will get the optimum threshold. So from this graph you can obtain the optimal threshold value. So this will help us to getting an optimal threshold. Another problem we encounter is for different method you will get a different threshold, and also you will get a different sample size. So that is another challenging task. In order to avoid it, we go for another mechanism. And you see, we evaluated for Pico threshold and dual pace threshold method, and for each of this parameter is estimated, and this standard error is given in the parenthesis, and choose the best among all 3 methods. So for each method you will get a different model is a better model. So we will accumulate and form this consolidated report for all 7 regions in Tamil Nadu. So the first one is a maximum block maximum generalized extreme value distribution. This model is better. Similarly, Pico threshold for generalized Pareto and dual pace threshold for generalized Pareto distribution, you will get different model. So if you see, look at this region 1, you will have 3 different models. So among this model, which one is better? In order to choose among these suitable 3 models, which is the better. So in order to do it, we will use a QQ plot. So which one is better suited can be obtained from this plot. So I consider only for the first region, Chennai region, and from this plot you can obtain the third one is a better one. Similarly, you can perform this for the rest of the 6 region. You will get which model is best among the this suitable model. So that will help us to find a better model. And you can choose all 3 methods, which model is a better one, easily you can obtain. But after obtaining this, the very you can estimate. I have listed the our result for this given data. So for R1, this model is better. This is the transformation we are making. That is a quadratic for scale parameter and shape parameter. This is a measure. And similarly for the 7 region, we have this is the best model. What is its estimate? What is its information criterion? All are displayed in this slide number 37. So this is the best model among these three methods. The main objective of this extreme value theory is to estimate return period and return level. That means in how many years in future, how much a quantum of precipitation or this heavy rain likely to occur in each of this region can be obtained. That is easily possible in EVT. So in this return period of 2 years, 5 years and 10 years, for 4 region I am displayed here. So for the next how many years, how this value can be obtained. So for the 3 different return period and how much the quantum will be obtained can be easily obtained by using the EVT method. So therefore, from this study we can conclude how new way of setting and this automated threshold. So advantage of doing this is this procedure will computerize, so therefore you no need of human intervention. When you are writing a program for it, it automatically every time calculate and the suitable model is automatically selected, and you will get the result of return level and return period for this data, and the same concept can be extended to all other scenarios in real time. So this is the conclusion of my study, and these are the reference used in my study. Thank you.
Thank you, Professor. It's indeed a great presentation.
Thank
There is some few doubts from my side.
Yes, madam.
One is like, what is the efficiency of this data which we use it over here?
Here, there is information criteria is there, madam.
That
So,
criteria.
yeah.
And the second one is, can we use stepwise BIC model also?
Which one?
Stepwise BIC model.
BIC. What is this? No, these are the different measures we can use. Preferably, all will help us to the last one you are talking, right? HQIC, right?
Yes, yes.
Generally, these AIC, BIC will have a different purpose. We'll use it. HUIC is another measure which can be also used for model, but all 4 information criterion will give you the same direction. Therefore, I can't right now say clearly why we use it, but this measure is very frequently generally used mechanism EVT.
Okay, Professor. Then one more thing, Professor. About
Yes.
this non-stationary analysis, normally when you use the real-time data, it always reveals some reductions in return period. Does this happen in your analysis, Professor?
A little more clear, madam. Your audio is, voice is a little breaking.
Shall I repeat it, Professor?
Yeah, please, madam.
This non-stationary analysis, pre-analysis, normally it reveals some reductions in return period of data.
So here, return period is totally different concept in extreme value analysis. Return period, in the sense, the quantum of damage or extreme that is going to happen. That's what we do. You see, that is used as an indicate measure. See, what we generally do, we are classifying the data. One is a stationary, another one is a non-stationary. So if it is a stationary, it's well and good. We can use a conventional method. In case of it is non-stationary, it is we are using as a only indicative purpose, not as a prediction purpose. We are using the above discussed model for our predictive purpose.
Thank you, Professor.
That's what it differs from usual time series analysis and extreme value theory.
Exactly. Thank you, Professor.
Thank
Great
you.
presentation. Once again, let us all give a big round of applause to our Professor. Activate, sir.
Thank you, madam. Thank you very much. So
you.
I also wholeheartedly thank Professor Satish Kumar, Professor Riya sir, and also Vijay Lakshmi madam for helping us to given an opportunity to share my thoughts in this forum. Thank you very much.
Thank you, Professor.
Thank you,
very much. Next, we move on to the next speaker, Professor G. Sirisha, University College of Science, Osmania University, Telangana, India. Madam is going to talk on compound variable lifetime distribution. Ma'am?
Yes, ma'am.
Over to you, ma'am.
Good afternoon, ma'am. Good afternoon, ma'am.
Good afternoon, ma'am.
Yeah.
Please proceed.
Am I audible, madam?
Yeah, you are audible, ma'am.
Can I start my presentation?
Please proceed, ma'am.
Can you see my screen, madam?
Not yet.
Not it?
Yes, ma'am. Can you share the screen?
Share screen. Now, madam, can you see?
Yes, ma'am. Yes, ma'am. Presentation, ma'am. Ma'am, in presentation mode. Can you put it in presentation mode?
Yes, ma'am. I'm putting. Is it okay,
That's
ma'am?
nice. Yes, ma'am. Please proceed, ma'am.
I'm Dr. G. Sirisha, Associate Professor from Department of Statistics, University College of Science, Osmania University. I thank the organizers for giving me a chance to present myself. Today my presentation is on compound viable lifetime distributions. In this talk, I'll be discussing about two compound viable lifetime distributions, the basic assumptions involved in derivation of these models, and some useful characteristic features like mean, variance, distribution function, and so on and so forth. I'll be focusing on. Introduction. My new distributions are based on quality control. I'm using in derivation quality control aspects as well as reliability aspects to derive my distribution and to derive the properties. As we know, in any industrial practice, in any manufacturing process, we use two main statistical aspects: statistical quality control and reliability. Quality control always deals with the maintenance and improvement in the quality of a manufactured product, whereas reliability analysis deals with the chance of survival of a manufactured product up to a specified time. Quality of a manufactured product can be assessed by defining a suitable quality characteristic. This quality characteristic or the variation in this quality characteristic it can be characterized by using a probability law, and the lifetime, once the product is produced, we will put into use, and when we put that product into use, we speak about the lifetime of that product. This lifetime of the product, which is nothing but the duration, the functioning duration of the product before it fails, is also a random variable, which is of continuous time because it is based on time, supported on the positive half of the real line. And my distributions are based on the concept of cause and effect relationship between these two aspects of statistics. And here I'll be even using modified control limits. Modified control limits can be used in situations where the Six Sigma spread of the process is smaller than the spread in the specification limits. And in such situations, the process mean mu is allowed to vary over an interval mu lying between mu L to mu U, where mu L and mu U can be obtained by using these modified control limits. And these two are obtained in such a way that the process is still capable of producing items that meet the specification limits. And when a certain shift in the parameter mu is permissible on either side of the target value, the upper and lower control limits for the control chart, that is your mu U and mu L, can be obtained by using modified control limits. Then compound distributions. Basic definition. In applications of statistics, one generally has some a priori information about the variation in one or more of the parameters of the probability model under consideration. Such variation can be specified in terms of a probability law. When this information based on a probability law on the parameter is made effective and is superimposed on the basic model, then the derived probability density function as a marginal from the joint distribution can be termed as compound distribution of the basic model. Now my first distribution is compound Weibull uniform lifetime distribution. First, I need to make some assumptions. As I have told you, I'll be using modified control limits concept as well as reliability concepts. To use modified control limits, first I need to assume that my procedure, my manufacturing process is according to the framework of modified control limits. That is the first assumption. I need to consider quality characteristic, say X, which is normally distributed with mean mu and variance sigma square, where sigma square is known. I need to even initialize the specification limits, say U and L are the upper and lower specification limits specified by the designing department. Then the other condition which I have projected is the 6 sigma spread should be much smaller than the spread in the specification limits. That is U minus L should be greater than 6 sigma, which indicates that the process is capable of producing better products meeting the specifications. Now I am assuming that the manufacturer decides to relax certain conditions, characteristics of the process by fine-tuning either one or more of the 3 M's, that is raw material, manpower and machinery. You can relax certain conditions imposed on these 3 aspects. Then this next assumption which I am using is I am assuming the basic lifetime model of the product to be as Weibull distribution, whose density is given to be as f of t is equal to, I think you can see on the screen, the density function which we all know, Weibull density. Then the other 2 assumptions are when I use a shift in, when I make changes in the 3 M's, accordingly, there will be a variation in the shift in the mu value. This shift in the mu value or the parameter value is assumed to follow uniform distribution in the range mu L to mu U, where mu U equal to U minus 3 sigma and mu L is L plus 3 sigma. This is from modified control limits. And it can be observed that the greater the shift in mu, the greater deviation will be there from the process mean mu naught, and it also indicates that there will be a reduction in the lifetime of the product, or in turn there will be a reduction in the expected lifetime of the product. When the shift increases, there will be a decrease in the lifetime of the product or decrease in the expected lifetime of the product. I'm moving slightly away from the original model. Then obviously the lifetime is expected to decrease. That's how, based on this assumption, I'm giving a mathematical relation between the expected lifetime and my variation in mu. This is my 4th assumption. The increase in the absolute deviation of mu from mu naught results in an increase in the reciprocal of the expected lifetime, and the same is represented by the relation. Relation is given over here, where U is nothing but the absolute deviation of mu from mu naught. Now first I'll be deriving the density function for V. I know the density function for mu because the shift is uniform. I need to first obtain the density for U, then for V. So for U, the density, first I am obtaining from the assumption 3, just now what we have seen, assumption 3, I'm using modified control limits. By using those limits, I can get my delta. Delta is defined in terms of modified control limits. From the assumption 3 and the density function of mu, which is uniform in the range mu L to mu U, the same density is quoted here, uniform density, and we know that mu naught is average of these 2 modified control limits, which is supposed to be the target value. the probability of mu lying between mu L to mu naught will be equal to the probability of mu lying between mu naught and mu u, and is equal to half because of symmetricity. Now we can obtain this G of u in terms of these two probabilities, probability of mu lying between mu L to mu naught and mu naught to mu u. On simplification, it will be du by, and so the density function is as given in the lemma. G star of u is this by using this relation. Now the main density function of the new derived compound lifetime distribution as marginal of the joint probability between in terms of V and T. The distribution of the lifetime T under the framework explained above is given by f star of T is the new distribution density. This can be derived by using the previous lemma and assumption 4. By using these two, assumption 4, by using assumption 4, I can get the density of V. U we have obtained in lemma. Then now I am transforming U to V. And when I'm transforming, my density will change like this. Then the compound distribution, I'm obtaining the joint distribution as HVT, which is F1V into F1 of T given V. The joint density is this. Joint density in terms of the lifetime, Weibull distribution, and the parameter distribution uniform. When I club these two, compound these two, I'm getting this as the joint density. If I integrate this joint density in the range of V, with respect to V in the range of V, that is C to C plus M delta, I will be getting my density function in this form. The same density function, I think you can see here integrals. This integral C to C plus M delta, this can be evaluated by using incomplete gamma integrals, and the expression given in terms of incomplete gamma integrals is given over here. And where omega 1 is this expression, omega is this expression. Then this derived probability density function, new probability density function, is a proper probability density function. It means the expression, this density function should be positive for all values, and the total probability should be 1. This density will be always positive or non-negative because the terms used in this density, C, M delta, are all positive, and the range is also positive. Then total probability, total probability can be obtained by using integral over the complete range density. If I'm using that and with some transformation, and by changing the order of integration, transformation is given over here. I'm simplifying, we will be getting 1. Properties of this new distribution, the expected value of this new distribution, which I'm calling as CWLD1, the expected value, that is the mean value can be obtained by using integral over the complete range T into F of T dt, F star of T dt, which is E star of T. Expression is given over here. And likewise, according to our assumption, when I have a shift in the parameter, obviously the expected lifetime will decrease, and that also can be seen from this expected lifetime. Then variance of compound Weibull lifetime distribution, expression is given over here. This expression we have got by simplifying the standard variance formula. Variance of T is equal to expected T square minus expected T whole square. When I substitute the mean value here, and on expanding mean value and the density, and on expansion, we are able to simplify it to this form. Then the other property is the distribution function, capital F star of T of this new distribution can be given in this way, is derived to be of this form. in terms of incomplete gamma integrals. And distribution function, as we know, it is integral over the lower limit to any t f star of x dx. When I expand that, we are able to get this expression. And the next property is the reliability aspects of this new distribution. Reliability aspects, when I say reliability function, hazard rate, cumulative hazard rate also we have obtained. Reliability function R star of t can be defined as 1 minus of f star of t, 1 minus of the distribution function, which can be obtained in this form. Then hazard function of this new distribution, hazard function or hazard rate, small h star of t. Hazard rate is nothing but the density function divided by the reliability function. When I substitute density and reliability function, I'm getting the expression in this form. Then cumulative hazard rate is nothing but integral 0 to t h star of x dx. I'm substituting h star of x. We will be getting this expression. Integrating this would be very complex, so this is the final expression. Then when I substitute alpha equal to 2, this compound viable lifetime distribution reduces to compound Rayleigh lifetime distribution. Viable distribution, when we use value, viable distribution reduces to Rayleigh distribution, also reduces to exponential distribution. In the same way, this compound distribution also, when I substitute the parameter value alpha is 2, it can be reduced to compound Rayleigh lifetime distribution. 1, it means compounding Rayleigh as well as uniform. Here we have compounded viable with uniform. This is Rayleigh with uniform. The density is this. When I substitute alpha is 2, the reduced density is this, which is nothing but the density of compound Rayleigh lifetime distribution 1. This distribution in 2022, I have presented a talk on Rayleigh distribution, compound exponential as well as Rayleigh distributions. In the same way, when I substitute alpha is 1, CWLD will be reduced to compound exponential lifetime distribution. The next distribution is compound viable triangular lifetime distribution. Derivation assumptions are similar. First assumption is the same. Second assumption, here also I'm assuming lifetime distribution standard model as viable. Then the third point, the modified control limits point is also the same. Fourth point here, fourth point is as well the same, because I need to connect the lifetime, expected lifetime with some transform. I need to transform the expected lifetime in terms of my assumptions. Now the lemma here, I have assumed here in third assumption, I have used, there is a small change. In the first distribution, we have used the word follows uniform. Here we have used triangular. That is the only difference between the two distributions. When I am using triangular distribution, my density function of V. Triangular distribution, shift in mu is according to triangular distribution in the range mu L to mu U. And the density in terms of this triangular is given over here, where mu naught is mu U plus mu L by 2. And based on the symmetricity of the triangular distribution around mu naught, mu minus mu naught has a triangular distribution in the range minus delta to delta. And because of this symmetricity, the distribution of V follows folded triangular distribution with density as this. Then the density function of the new distribution is given over here. New distribution, compound distribution. When I'm merging the parameter distribution as triangular with the viable distribution of the standard lifetime model. Then using the lemma, we have in the previous lemma, we have obtained the density of V. Now I'm getting the density of W is like this. Then the joint density by compounding W and Z, we'll be getting this. When I integrate this, I'll be with respect to W in the range of W, I'll be getting the marginal density of Z. We will be getting the marginal density, and marginal density as it is in integral form, we can write the same in terms of incomplete gamma integrals, where omega 1, omega 2 are given over here. And this derived density function is a proper density function, as the density function term C m delta W, C plus m delta minus W, all these are positive. And total probability on expansion is leading to 1. And on using the change of order of integration and the transformation given over here. Properties of this new distribution: the expected value mean is given as expected star Z given over here. Then in the same way, as I have told you, here also the expected lifetime of this new distribution will be definitely is less than the expected lifetime of the standard Weibull distribution. Variance we have obtained to be like this, and distribution function for this new model is derived as this. Then reliability function expression is given over here. Hazard rate, cumulative hazard rate, procedure is the same what I have explained for the first model. Then when I am substituting alpha is 2 in the new density, we are able to get it to be as reduce it to as compound Rayleigh triangular lifetime distribution. And when alpha is 1, the same density reduces to compound exponential triangular lifetime distribution. And whenever conclusion, if a manufacturer wants to relax the conditions, whenever the process is under control, then instead of completely redoing the whole obtaining the lifetime distribution, we can make slight changes by using this compound distributions. These are the references used. These are the references used.
Thank you, ma'am. Hello, ma'am.
Yes.
Yes. Great presentation.
Yes, ma'am.
Any questions from audience? Participants? Professor? Okay. If not, ma'am, I have 2 things. Shall I ask?
Yes, ma'am.
Ma'am, one thing is like this is a topic where manufacturing, production, everything is involved.
Yes, ma'am.
So if that is the case, the failure analysis or the risk of the product, has it been analyzed?
Yes, I didn't understand, ma'am. Can you?
Failure analysis. Am I audible? Failure
Yes.
analysis.
Failure analysis.
Failure analysis.
Yes.
And has it been tested with real-time data or anything like that, ma'am?
No, ma'am. Failure analysis is the same as your reliability analysis,
Yeah, exactly.
complementary form.
But the product, risk of a product in manufacturing or production is also needed.
Yes, that's what reliability talks about survival. Complementary talks about your failure probability.
Exactly. So has it been tested with real-time data?
No, ma'am. I didn't check with any real-time data. I think I need to simulate the data because I didn't get any such data.
No issues. Then one more thing is, ma'am, any error loss function?
I need to still work on it, ma'am.
These are my humble suggestions. Okay, ma'am.
Okay, definitely I'll incorporate on this.
Best wishes to you, ma'am.
Thank you, ma'am.
Thank you. Let us give a big round of applause to Professor G. Sirisha, ma'am. And We move on to the next. Professor Ritam Groh from Indian Institute of Technology.
Yes, I'm here.
Good afternoon, ma'am.
Good
Madam is going to brief on, give a lecture on stochastic modeling of nearly periodic signals.
Yes.
We welcome you, ma'am.
Thank you, ma'am.
Yes, ma'am. Please proceed, ma'am.
Okay, I'll just share my slides. And
Please.
So, is my screen visible?
Yes, please proceed.
Yes?
Please.
I'm sorry, your voice is...
No, proceed, ma'am. Proceed, ma'am.
Okay, sure. So, I'll start?
Yes, ma'am.
Okay, thank you. So hi, I'm Rhythm, and I'm a faculty at Mehta Kami School of Data Science and Artificial Intelligence at IIT Guwahati. I hope I'm audible.
Yes, ma'am, you are audible.
Okay, thank you for letting me know.
Yeah, please proceed.
Okay, so I'll be talking about stochastic modeling of nearly periodic signals. Before I actually do that, I'll talk about more about periodic signals and what do we mean by signals. But I would like to first thank you, Professor Satish Kumar, for the kind invitation, and to all of you for being here. Okay, so before I talk about periodic signals, let me clarify that when I say signals, what I mean, or in general what we mean in signal processing, is everything and anything that can be observed or maybe recorded or collected, in the sense that high and low tides of the ocean that we record can be seen as signals, or ECG signals, for example, ECG data of a person being recorded, the heart measurements, contracting and relaxing, can also be seen as signal. You hearing my voice right now through my microphone and then through the speakers of your computer or laptop is also a signal. So these are the signals that we will be talking about in this talk. And particularly, I'll be stressing on periodic signals for quite a few slides. So when I say periodic signals, I do not, I don't want to define it mathematically, but the idea is that you are looking at data that has periodic pattern, that is cyclical behavior. For example, in this particular slide, you see 4 different examples from 4 different domains. The first signal is that of a speech data. So a person is uttering this sound. This sound is something like this. It's you, a vowel sound. And when they utter this sound and it is being recorded, the signal looks like this. And you can see that it's a periodic one. It has a cyclical behavior. Similarly, on the right-hand side, what you see is another picture. This picture or this signal is of a sunspot number. So sunspot numbers are being recorded over several years. And when you plot them together, you again see a periodic pattern here. So this is the kind of cyclical behavior that we will be talking about for periodic data. In the third picture, on the left bottom corner, what you see is ECG data, the measurement of heart relaxation and contraction that I was talking about. And again, most of us have seen these in movies or where patients are in ICU and the monitor shows this ECG signal, which is periodic in nature. And in the fourth picture, again, we have a data set, which is of number of airline passengers. It's again an old data set, but it clearly exemplifies a periodic structure. Right? So these are the things that we want to talk about. What are these signals and what do we want to do with them? Yeah, so I'll move on to the next slide. So why are we interested in analyzing these signals? There are several reasons to do that. One of the major reasons is to understand and predict a phenomenon. So if we go back to our sunspot data that you see on the left-hand side here, what we see is what we want to do is actually estimate the period of this signal. And if we estimate the period, we know when it is going to repeat itself. And this helps people who study climate changes and temperature of the planet and Earth. So they want to understand the physical processes in the sun, right? And it is useful for them to know the period of these sunspot numbers so that they can predict the Earth's climate. So that can be one reason to understand and predict any phenomenon under study that is periodic in nature. Another useful reason is data compression. So suppose we have a signal like this. On the left-hand side, you see a periodic signal, and this is a signal that is simulated. So if you see here on the x-axis, I don't know if it is visible or not, but these are 1,000 data points. It could be more also, right? The idea is that if I can use a mathematical model like this, which I'll talk more about later on, and if I know the amplitude, this A and B values and omega values, which are here on the right-hand side, then I can use this mathematical formulation to regenerate this signal whenever I want. So instead of storing these 1,000 data points, I can just store the parameter values A, B, and omega, and I can regenerate it whenever I want. What we mean is that we can compress data this way, and it can lead to a lot of space savings in your computer. Okay, so another reason can be to restore and enhance signals. For example, on the left-hand side here, what we see is a noisy signal. You can see the zigzag pattern over here, which represents noise. And the idea is if we analyze these signals or process these signals by modeling them, we can actually remove this noise. And the signal can look something like this, which is much more cleaner. So a practical application of this would be, suppose you have a CD and there are some music recordings there, maybe your favorite song, and maybe it's corrupted a little bit or there are scratches on the CD, then it can happen that your favorite song is noisy there and you are not enjoying it anymore. So in such a scenario, you would want to actually remove the noise, and that's where the modeling can help us. Another reason to do so could be recognition and comparison. So the parameters of the model, when you analyze a signal using models, say or convey information about such signals, right? And using this information parameters, you can actually classify signals into different categories. So again, my favorite example are always music signals. So one thing to do can be that you have several music recordings and you want to now train your computer to use this model, the model parameters, to classify the different music songs into different categories or different genres, right? So there can be several applications like this. Okay, so hopefully I have convinced you that why we need to analyze periodic signals. And now we want to see how to do that. So if you look here, the mathematical framework that we will be talking about in analyzing such signals will be the regular regression framework, which looks something like this. So here YT are the observed data. And this observed data can be decomposed into two components. One is ft theta, which is our deterministic component, and the other is epsilon t, which is our random error component. So the idea is that the signals that we are recording or observing are actually corrupted with noise in practice, as we saw in one of the examples, and therefore we need a random error component to account for that noise. And this ft theta will be something that captures the main information in the signal. If it is periodic, then it captures the periodicities of the signal, and so on and so forth. If you have any questions, please do let me know in between, and I would be happy to answer that. And if I'm too fast, then also please stop me and let me know that.
That's perfect, ma'am. No problem.
Okay. Thank you for letting me know. Yeah, so this is the mathematical framework, the regular regression framework in which we put our models, right? And the model that we will be talking about for the most part of our talk today is the sinusoidal model. So what I mean by that is that this ft theta, the deterministic component, will be a linear combination of these cosines and sines term, and you have this to be it's summation, sum of many cosines and sines. So this is what it looks like, and here amplitudes, here these AKs and BKs are called the amplitude parameters, and omega k's are called the frequency parameters. So these are the parameters that characterize this sinusoidal model, and it's one of the fundamental or the more very popular model to analyze signals that are periodic in nature. So we already know that sines and cosines are periodic in nature, right? So that is why this linear combination of them helps us capture many signals in different domains that are periodic or have cyclical behavior. Okay. So now we know that this is the model that we will be working with, and we want to now boil down to the problem that we want to solve. And the problem is that of parameter estimation first. That is, we want to estimate, as I said, the amplitudes, that is AKs and BKs of our model, and the frequencies, which are omega k parameters, and the number of components, which is P. As I said, it can be multiple number of sinusoids, sines and cosine terms. So you want to know how many of them are there in a particular signal. And then you need to calculate the amplitudes and the frequencies. And we do that using the observed data YT. So that's the signal that we have in our hand, which is a noisy one, and that's why the epsilon t. Now this is how we want to, this is the problem at hand. And we want to solve our problem by assuming certain structure on the noise. So the usual way, the regression way, is that you want to impose certain structure on the noise. Usual assumption is that of a Gaussian noise. However, the results that I will be showing here today are constructed under more general noise. The noise could be any stationary linear process, that is an MA, ARMA, or AR process, and still the results will hold true. So you assume a certain structure on the noise, and then you estimate the deterministic component. If you remember, our deterministic component is this ft theta, and theta is the parameter vector, which is nothing but your amplitudes a1, b1, omega 1, and ap, bp, omega p, right? So estimating the deterministic component is same as estimating these a1, b1, omega 1, and ap, bp, omega p. And then you have the estimated model at hand. Using the estimated model, you can estimate the error. And once you have the estimated error, you verify the assumptions that you have put in the first place, right? The first step of your procedure. Okay. Sorry, it's stuck a bit. Yeah. So now, how do we do this problem? How do we solve this problem? So one of the most conventional methods in the regression framework, and which was done in the 1953 first by Whittle, and then further explored by Walker, Hannon, Hassan, and Professor Kundu in 1997, is the least squares method, right? So one of the very traditional and the conventional methods that we all know about in the linear regression setup. The problem is not linear anymore, please note that, but the framework is the regression one, and therefore we can extend the least squares estimators, which are now the non-linear least squares estimators in this framework. So the idea is similar, that you estimate the parameters by minimizing this error sum of squares function, which is QAB omega, which is actually the sum of the squares of differences between the observed data YT and your deterministic component, which in this case is A cos omega t plus B sin omega t. And it is this because we are assuming there is only one component, sinusoidal component. This is a simple sinusoidal model. So P is 1 here. And now you want to minimize this error sum of squares to estimate A, B, and omega. It helps us to write down this problem in the matrix notation. So that is why you see Q phi omega here, which is nothing but Q AB omega. And this can be written as y minus z omega phi transpose into y minus z omega phi. So this, I'm hoping, is a very familiar quantity to all of us. Again, it's a least squares regression function. Just that your Z is not a design matrix anymore. It's a function of cosines and sines, and they are a function of omega. Okay, a good part about bringing in this matrix notation is that you can now separate your phi by separable linear regression and estimate phi by linear regression technique. And I'm hoping we all remember that phi hat will be nothing your linear regression estimator, which is your Z transpose Z inverse Z transpose Y. Right? So similar to your X design matrix, X transpose, X inverse, X transpose Y. It's just that your phi is a function of omega because your Z is a function of omega. So when you put this back in your function Q, you get this function R omega, which is now only a function of omega. And how this helps us is that now you need to estimate omega by solving only a one-dimensional nonlinear optimization problem, which is minimizing this R omega function with respect to omega. Right? Once you have that, you can plug in your omega here and get phi hat. So on the right-hand side, what you see is this this graph where on the y-axis we have R omega, and on the x-axis we have omega. So you can see there is a clear sharp valley, this trough, at the true value of omega. In this particular case, true value of omega is 0.1. And that's why you see a sharp trough there. So minimizing this function is basically locating this particular omega, right? Okay. So now, before I proceed further with these methods, I would like to mention one more method, which is another famous method to estimate omega, is the periodogram method. And periodogram method was first studied by Walker in 1971, and they said that you can estimate omega by maximizing this function that is called periodogram function, defined by this function I omega here. If you just open this right-hand side, you get a function that looks like this. Down here, I have a picture of I omega with, so again, we are graphing the function I omega for different values of omega on the x-axis. And again, you can see a sharp peak at the true omega value, which is again 0.1 for the same simulated signal. So if you go back here, this R omega function and this I omega function look kind of same in the sense that one is the mirror image of the other, because later we could show that actually this I omega, this function is actually some constant minus R omega plus small o of 1, which basically means that as n goes to infinity, for a large data points, you can show that I omega and R omega are related to each other in this way. So maximizing the periodogram function is same as minimizing your least squares objective function. Right? So these estimators actually behave quite nicely, and both of them in the same way when your n is large. So we have some nice properties for these estimators. The least squares estimators as well as the approximate least squares estimators. So the periodogram estimators, now we are calling them approximate least squares estimators because their functions are related to each other. These are both strongly consistent. The only thing is you have to assume that the second order moment of the error random variables, that is your variance, is finite. So once you assume that, you can prove that both of them are strongly consistent estimators. Not only that, you can show that the LSEs and the ALSEs of the amplitude parameters, that is your AKs and BKs, have a convergence rate of n to the power minus 1 by 2, which is your usual rate of convergence. And one can also show that the frequencies have a convergence rate, the estimators of the frequency have a convergence rate of n to the power minus 3 by 2, which is the unusual rate of convergence and is very, very fast. So if you can resolve your frequencies, they converge at this particular rate. And both of them have asymptotically normal distribution. This is also something that we can show. So these are all the good things about the statistical properties for the least squares estimators as well as the ALSEs for this particular model, and they extend for the multiple component model as well. But things are not all good here in the sense that finding these estimators gets very, very difficult. So the drawbacks are the computational drawbacks in the sense that the problem is highly nonlinear when you want to solve for omega, because the least square surface, the surface that we were looking at in our previous slide, the R omega as well as the I omega surface, they have several local minima. Since they have several local minima, most of the methods like Newton-Raphson algorithm and gradient descent, any of the standard algorithms, they will not converge. And even if they do converge, they might converge to a local minimum rather than the global minimum. And this problem becomes particularly difficult when P is large, that is when you have multiple components in your model, because it's now a multidimensional nonlinear optimization problem. So to recollect, our graph in that picture looks something like this. This is our R omega graph, the least square graph. Although the problem is not quite highlighted here because you see a sharp trough at the true value. But if you zoom into the picture, which is on the bottom right corner, you see that there are several local minimum here. So if I start my Newton-Raphson or some standard algorithm here, it might happen that it will get stuck or maybe reach somewhere here, but it will never reach my global minimum position. So that is one major problem with these least squares estimators. Although theoretically on the paper they look very, very nice, finding them becomes very, very difficult. So what to do? So one alternative is to look at this faster method, which is the sequential algorithm to find the least squares estimators. They are actually called sequential least squares estimators. And the idea is that you minimize this error sum of squares function, which is the same as before. That is your function of A, B, and omega. You call the estimators that you get from minimizing this function A1 hat, B1 hat, and omega 1 hat. Once you have these estimators, what you can do is find your estimated component, the first component, and subtract its effect from the observed data YT and get new data called Y1T. So Y1T is nothing but your observed YT minus the first estimated component. And now using this Y1T, you again assume that you have one component and minimize this error sum of squares function. Just that this function is different from this function because you have replaced YT by Y1T. When you do that, you get the new estimators. You call them A2 hat, B2 hat, and omega 2 hat. And then you keep repeating this process P times until you have all the P component estimators. This method works because the columns of the matrix Z omega, right, the cosines and sines, are orthogonal for large N. And because of this orthogonality, we are able to reduce our multidimensional optimization problem into a cascade of one-dimensional nonlinear optimization problems. So that's a lot of computational savings. Okay, so far we looked at periodic signals and a very popular periodic model, the statistical model, to look at these periodic signals and analyze them. But now we want to look at signals that are not exactly periodic in nature, but can be called nearly periodic, in the sense that if you look at some segments of these signals, they will look periodic, but when you put it all together, they are not exactly periodic. So the first example is that of a bat echolocation call. These calls are actually made by many species of bats, also many species of whales, to detect their prey. So when they give out these signals to know where their prey is, these sounds come back to them as an echo, and when they come back, they are modulated with time. So that is why they are not exactly periodic in nature and look something like this. So this is one example where you have not exactly periodic signals. And this is another example where we have an EEG data. So these are brain signals rather than heart signals. And now again, if you look at segments of these, they do look periodic up till a certain point. But again, when you put it all together from 0 to 250, you can see that the signal is not exactly periodic. So now how to analyze such signals? Because the sinusoidal model, the popular model that we have talked about over several years, that doesn't work anymore because it won't be able to capture the all the intricacies of this model, the modulations that happen. So an alternative way is to look at a model where your ft theta is something like this. So what is happening here is that inside these cosines and sines, you don't have just the frequency parameter. Earlier we just had this alpha kt. Now we have alpha kt plus beta kt square. So what is happening here is that inside this cos and sine, you have a term like this, alpha k plus beta kt whole times t. What that means is that this is your new frequency now, which is changing with time, and it changes at the rate beta k. So you want to now estimate both alpha k and beta k to fit this model, and this model is called a chirp model. So it's a famous model in the signal processing literature. And because of this randomness that is present in the signal, it is many statisticians are also involved in analyzing such signals from a statistics point of view. Mostly the noisy part in the signal makes the problem open to the statisticians. Anyway, so now we are looking at a chirp model rather than a sinusoidal model, because this model helps us capture the modulations in the frequency that change with time. And again, we can look at similar methods, those conventional methods like least squares method. I'll not go into the depth of that method again, because the overall idea is same, but the problem changes quite a bit in the sense that if I now look at, actually before I go into the method details, I wanted to show how chirp is different from sinusoid. So on the left hand side, what you see is a sinusoidal signal, which is periodic in nature, right? You have a nice sweep, a periodic sweep. However, on the right hand side, what you see is this red signal, which is a chirp one. So if I just add a small beta parameter, this causes my sinusoidal, the original blue sinusoid, to have a rapid change in the frequency, and that's why this ups and downs, the sweeps that you see in the red signal come into picture. Okay, so that's how chirp is different from sinusoid. And the question is how to fit a chirp to a data that is not periodic in nature. And what you can do is again look at the periodogram function, which is now a function of two parameters, alpha and beta. And this is what the periodogram surface looks like, which is the picture on the left-hand side, as a function of alpha and beta when you have only one chirp in your model. So remember, you can have p chirps, but right now you have only one chirp in your model, and it looks something like this as a function of alpha beta. And again, you can see that the problem is more difficult now because you are in 2 dimensions. It's again a nonlinear problem, and you have several local maxima sitting on the surface. So when you start with a bad initial guess, it can get stuck anywhere on this surface and not reach the global maximum. So for a single chirp, we need to solve a 2-dimensional nonlinear optimization problem, and the surface is something like this, so with several local maxima. And for a multiple component chirp, you need to solve p such optimization problems, which becomes all the more difficult. And actually for large P and large N, it almost is infeasible. It's a computational nightmare, and unless you have very high computational power, actually in that case also, I don't think it will be solvable for large P and large N. So what we did was to find an alternative to the chirp and modify our ft theta to look something like this. It's a linear combination of the sinusoidal model. So this is our usual sinusoidal model. And what we add to it is what we call an elementary chirp model. So what happens here is that in cosines and sines, you no longer have alpha k and beta k sitting together, but you have different set of alpha k's and different set of beta j's. But the good part is that it can be proposed as an alternative to the chirp, and that's why we call it a chirp-like model, because many of the applications we observed that whatever could be modeled using chirp could be modeled using chirp-like and in a computationally efficient way, in a computationally feasible way. So I'll quickly show you some pictures. So here what you see is a blue signal, which is a chirp signal, a simulated one. And we fitted a chirp-like model to it, which is the red one. And you can see that how nicely they overlap each other, which gave us hope that you can use chirp-like as an alternative. Not only that, initially, when we looked at the bat echolocation data, we could not model it using the chirp model because of the computational issues. However, using the chirp-like model, you can see that we could fit it quite nicely, and the red signal is the one that we estimated, this bat echolocation data, and it fits quite nicely to the blue one, but that was possible only because of the chirp-like model. And when I say it was possible in the sense that the chirp model had computations that involved n-cube order computations at each step of the algorithm. However, for this particular chirp-like model, we had to solve which are this problem of n plus n square size, which is a huge reduction, as you can imagine. Yeah, I would be happy to talk more about chirp-like model, but I'm looking at the time now, and I think I already overshot. But if you have any questions, I'll be happy to answer them.
Thank you, Professor.
Thank you.
Questions from audience? If not, I would like to discuss on some scenario. Can I, madam?
Yes, please.
Ma'am, about this complexity of the algorithm.
Mm-hmm.
Now, did you face any complexity of running the algorithm? Have you used any real? Yeah, please. Have you used, yeah.
You are saying that if we faced any complexities in the model?
Yes.
Yes, that's what I quickly skipped through in the end, that the problem of finding least squares estimators, particularly when you do the chirp model for this nearly periodic data, the problem is that it's a nonlinear problem, right? If it's a nonlinear problem, you cannot do your usual thing anymore. You have to do some iterative method, right? And for the iterative method, you have to have some initial guess. Now, unless your initial guess is very, very nice, what happens is that it will get stuck in the local minima or local maxima, whatever we are looking at. Yes. So now the only way out is that you have to do a grid search, a very fine grid search. Particularly for the chirp model, that grid search is of size n cube. And that n cube size is for each of the p components that you have in the model. So even if you do the sequential method, you'll have to solve n cube problem at each p steps. So if your p is large and n is large, it is a computational nightmare. And that's why we have this chirp-like model. So for chirp-like model, what happens is that you have to solve n p-dimensional problems. So it's like one-dimensional problem. So grid search is only of size n. But you also have elementary chirps. So if you have a few chirps, then you have to solve n square problems also. But you can imagine that n plus n square is still much better than n cube, right?
Okay.
So that's one major.
Okay, nice. I have one more thing, right? I think if I'm correct, you used Gaussian process regression. Am I correct?
Gaussian processes?
Regression for estimation.
No, we are not using Gaussian processes here. So that becomes a non-parametric way of dealing with signals. One can do that, definitely. I think there are many people who are doing that also. But we are looking at the parametric setup where we are assuming this structure and then estimating the parameters.
Okay, good. Okay. Then final thing is, do you have any error component? Like
error component? Yes.
When you have this damping proportion of vibrations, like that.
Yes, exactly. So that is what actually makes it a problem for statisticians to deal with. Usually it is, if you just look at the mathematical model, then it's just a problem for engineers maybe. But if you look at it with a random error component, because yes, when you are recording signals, for example, if it is a phone recording also and your car window is open, then some noise will enter. And that's what makes it interesting for statisticians to deal with this problem. And this is what our random error component is.
Okay.
So we have this epsilon t in our models. I think I lost you
Yes,
here.
it's fine. It's fine. No issues. No issues.
Yes. Yeah, so we do have a noise component. This epsilon t is actually to account for that randomness in the
To
signals.
remove the random. Yes, ma'am. Thank you, ma'am. Thank you so much for your presentation. Nice presentation.
Thank you.
Thank you. We are moving on to the next presentation by Professor Sambasiva Rao from Mizoram University. First talk is on burden due to alcohol-related liver diseases in India and its stages and regions. A stochastic modeling approach. Sir, we welcome you, sir.
Oh, sorry, I just muted myself. Am I audible now?
Yes, sir. Please, sir. Please. Yeah, you're audible.
Yeah, namaste to all.
Namaste, sir.
Namaste, sir. Satish, sir. Thank you for giving me this wonderful opportunity, sir, to present my work with other colleagues from India and from around the world. See, this work, what I'm going to present is my screen is visible?
Yes, sir. Your screen is visible. Please proceed.
Let me put in presentation mode, and in between I have to switch to the other files too.
No issue.
This work is a part of my UGC funded project titled Estimation of Health and Economic Burden Due to Alcohol-Related Liver Diseases in India. And the title of my talk today is Burden Due to Alcohol-Related Liver Diseases in India and its States and Regions, a Stochastic Modeling Approach. Unlike the other presentations, this work doesn't require heavy statistical concepts or statistical calculations. It's more like a empirical kind of work, and this kind of work can be done by epidemiologists or economists or statistics people. And while I was working previously in Institute of Liver and Biliary Sciences, the epidemiologists there, it is a liver institute, they want to estimate how much is the burden due to alcohol-related liver diseases in India and its states. But because of some heavy computations involved, according to them, these are heavy computations, but according to statisticians, this is, a basic computations only. So they asked me to to lead this work and to jointly work with them for this project, which I started along with them. Now, this one, after developing the proposal, we sent it to UGC, and I got this as a startup grant for doing this work. Here is the brief introduction. See, we know alcohol is very commonly used. It is used for recreational purposes, and its use is common around the world. And we also know that it is alcohol use can produce psychoactive kind of characteristics, and it produces dependence on alcohol if someone is taking it on regular basis, frequent basis. Alcohol is available in different forms and in different brands throughout the world. But whatever may be the form or whatever may be the brand it may be available, alcohol use has some detrimental effect on health, and there is wide acceptance about this fact throughout the world. In fact, alcohol use can influence cerebral system, so-called brain system, hepatic system, so-called liver system, renal system, circulatory system, cardiac system, and many other systems. In fact, worldwide, about 3 million deaths, 30 lakh deaths every year, are caused by harmful use of alcohol. And these deaths alcohol-related deaths are accounting for 5.3% of overall deaths in the world, and even 5.1% of global burden of diseases, which is, in terms of Delhi's, 5.1% of Delhi's lost can be attributable to alcohol. Indeed, more than 200 disease and injury conditions are attributable to alcohol. And of all the major damages that alcohol can cause, most of the damage is in the form of liver diseases. In fact, studies are saying about 50% of harm that alcohol causes is in the form of liver diseases. The other two kind of causes are, one is road traffic accidents, otherwise some kind of cancers, esophageal cancers related. Now, as 50% of the burden is due to alcohol-related liver diseases, in this, and nothing is known in the context of India, how much is the health and economic burden due to alcohol-related liver diseases. In this study, we took up this issue and systematically investigated this. This is the first study in the context of India, and not only in the context of India, in the context of world also, that specifically focuses on alcohol-related liver diseases. There are 4 alcohol-related liver diseases that were considered in the study, and these conditions represent 90% of alcohol-related problems due to liver diseases. 4 stages are considered. Normal stage, in which there is no liver problem. If a person is drinking alcohol quite for some long time, then 90% of the drinkers will develop steatosis. The first stage, this is called fatty liver disease, alcoholic fatty liver disease. And if the person keep drinking after that for long times, then about 20 to 40% of them will be moving to steatohepatitis stage or fibrosis stage. And if the person is continue to drink, then they will move to cirrhosis stage. This is end stage liver disease stage. After this, the person either will develop hepatic cancer, so liver cancer, and die, or else they may directly die due to cirrhosis. The objective of this particular study is to estimate the health and economic burden due to alcohol-related liver diseases for India and its states and union territories for the period 1st March 2021 to 28 February 2022. That is for a 1-year period, basically. Annual deaths and annual burden due to alcohol for India and all its states and union territories. That's what our first objective is. The second objective is, after 2022, for the next 10 years, how much will be the burden due to alcohol-related liver diseases, and how the burden over the years is anticipated to change because over time population is increasing. So burden is also naturally, even at the current levels of drinking, the burden will increase. So how much the burden is anticipated to increase. So this is what is our objective. Here is the methodology. This is the conceptual framework to find health and economic burden. Particularly, this slide shows how to find health burden. So initially, we started with, this is how we find the main idea. Initially, at the beginning of the 2022, how many people are there that, say for example for India, how many are there? Then how many of them are anticipated more than 15 years? Why we find this? Because people whose age is above 15 are only at risk of drinking alcohol. That is what the assumption we have taken. Though there may be few people who start drinking before age 15, but such number is negligible. And of them, based on percentage of the people drinking alcohol that is found from National Family Health Survey, we estimated how many number of people are drinking alcohol in India. I mean, I'm just taking India as an example. I'm saying the same thing we did it for all the states and all the union territories. And of them, based on the literature of all the drinkers, how many will be in stage 1 liver disease, stage 2 liver disease, stage 3, stage 4. So whatever the previously I talked, that alcoholic steatohepatitis, and cirrhosis, they are different stages, stage 1, stage 2, stage 3. So based on the literature, what proportion of people are anticipated in different liver disease states? We obtained it from published articles. Then based on that, we anticipated, I mean, how many number of people are expected not to have any liver disease among all those people who are drinking alcohol. How many are anticipated not to have any liver disease? How many are anticipated to have fatty liver disease or alcoholic steatosis or alcoholic steatohepatitis? Or how many are having alcoholic steatohepatitis, and then how many are having cirrhosis? Then after finding expected number of people in different liver disease states, then from the literature, we gathered information how the transition of liver diseases from one state to other over the next 1 year. We have gathered that information. For instance, here I'll be showing here. I hope screen is still visible.
Yes, sir. Yes, sir. Please.
Yes. Now, all these numbers were gathered from the literature. What is this number 0.733 means? This do mean if there are 100 people who do not have any liver disease, who are drinkers, who do not have any disease, if they continue to drink alcohol over the next 1 year, 73.3 of them will still do not have any liver disease or won't develop any liver disease over the next 1 year. But 16.7 of them will develop, of these 100 people who do not have any liver disease at the beginning, 16.7 will develop alcoholic hepatic steatosis, and 10 of them will develop alcoholic steatohepatitis. Like that, the other numbers can be understood. Now, then we applied those Markov, they are called, I mean, state transition probabilities, 1 year state transition probabilities. Now we applied those, using those, when applied to these number of people who are in different liver disease states at the beginning, we can get over the next 1 year, how many person years we can anticipate, how many people are expected to live, I mean person years in normal disease state, alcoholic steatosis stage, alcoholic steatohepatitis stage, and cirrhosis stage. Now this is like, if these terms are a bit difficult, say some other problem, I mean, how many are, say, diabetes setup, how many are in non-diabetes stage, in diabetes stage, I mean, person years experienced in that. Now, if all those who are in normal condition, their utility, their life utility is 100%. On the other hand, those in cirrhosis stage, their utility is, life utility is 0.76. It means in the normal circumstances, if they are 100% efficient, but those who are having cirrhosis, they are only 76% efficient as compared to the normal people who do not have any liver disease. Now, indirectly, these utilities will give efficiency lost per person per year. Now, basing on these, we can find total years of life lost due to reduced utility from liver diseases. Similarly, using the same Markov model, we can find the number of deaths due to alcohol-related liver diseases, and then applying, see, those who died due to alcohol-related liver diseases, on an average, they die at the age of 47 years. So now in India, life expectancy at birth is 69 years, or say 70 years. Now, when they are dying at the age of 47, those who are dying due to liver diseases, so per person who is dying due to liver diseases, at 23 years is last. So after finding number of deaths due to alcohol-related liver diseases, then when we multiply that with this, we'll be getting total years of life lost due to premature mortality. In this study, we have estimated health burden in terms of number of deaths and days lost. DALYs, disability adjusted life years, is a term that is commonly used in epidemiology, and that measure focuses more on quality years lost rather than the quantity of years lost due to a particular disease. Now, after finding the number of deaths and anticipated number of years, days lost, and then anticipated number of years in different liver disease states, then we have estimated the health burden. How we estimate this economic burden? How we did that? After finding person years spent in various alcohol-related liver disease states over the 1 year period during 2021, say 1st March 2021 to 28th February 2022, this is a 1 year period. You can simply literally think the entire calculation were done for 2021. You can literally think there is a problem. Why didn't do for 1st January? Because population estimates are available on 1st March 2021 for every year. So that's why we have to go by these particular dates. I mean, for 1 year. Now, after finding person years in different liver disease states, they are equivalent to number of people. Though I am using the word person years for technical reason, but they are equivalent to number of people having alcoholic steatosis, alcoholic steatohepatitis, and cirrhosis during that year. Of these people who are having alcoholic steatohepatitis, either they may visit private hospitals or they may visit government hospitals. In the government hospitals also, there are 3 levels of care in India: primary healthcare centers, community healthcare centers, and tertiary care. So those who are going to private hospital, they have to bear all the expenses for treatment for 1 year. We have considered treatment for 1 year only. So yes, they have to bear that expenditure is called out-of-pocket expenditure. But if they go to government hospital, there are 2 components. There will be cost to the government, I mean to the healthcare system, and there is also some cost to the people. Not all facilities are there even in government hospitals. So sometimes they may ask for scanning, they may ask for medicines to purchase outside, go for scanning outside. So there will be some out-of-pocket expenditure also to the people. And the other technical details I'm skipping because I want to focus more on the findings. As we can anticipate, the burden is more in states where the percent of the people drinking alcohol is more. I'm just showing before going to show results, the prevalence of alcohol across different states and union territories in India. On the whole, 9.91% of the people are drinking alcohol during the period 2021 to 2022 based on NFHS estimates. Here is the estimates, health and economic burden estimates, comprehensive estimates for India. Apart from estimating using Monte Carlo simulations, we do have estimated 90% confidence interval for the burden. See these during 2021, you can literally say 1st March 2021 to 28th February 2022 as during during 2021. During 2021, there are 218,169 deaths due to alcohol-related liver diseases in India. And 95% confidence interval for it suggests these deaths could be as low as 1,47,990 and as high as 2,95,487. And information is also provided on other kinds of losses, productivity losses. And in this study, we have estimated economic burden in fact, 3 different conditions. But here in this presentation, I'm showing burden in 2 different scenarios. What are those scenarios? If all alcohol-related liver disease patients, they are to be treated as for their current preference to go to public or private healthcare facilities. In India, about 30% of the people go to public healthcare facilities if they face any problem, for getting treatment. 70% of the people, they go for private hospitals. That is at all India level. But that vary greatly from state to state. In northeastern parts of India, 70% of the people, they go to public healthcare facilities only, and only around 30% go to private healthcare facilities. Whereas in case of southern parts, most of the people go for more than 70%, go to private hospitals only. Now here, this figure shows estimated number of deaths due to alcohol-related liver diseases across the states of India during the study period of 2021. There are 2 figures here I showed. This is total number of deaths, left side, right side, number of deaths per million population. Now first let me discuss about total number of deaths. Uttar Pradesh is anticipated to have highest number of deaths due to alcohol-related liver diseases during the period 2021. There, about 25,650 deaths are expected due to alcohol-related liver diseases, whereas in case of northeastern states, very less deaths are expected. Then the question may come, it is natural that, because here we are talking about total number of deaths, and it is known that in the northeastern states, population is very less. Though alcohol drinking is more in these regions, because of less population, obviously we can expect less number of deaths. Compared to these northeastern states and even southern states, alcohol drinking is bit less. Percentage drinking alcohol in Uttar Pradesh is comparatively much less. But because of huge population here, the total number of deaths anticipated due to alcohol-related liver diseases is very high. Now, for a proper comparison, standardizing population, in the sense that when we compare deaths per million population, then where there is a high prevalence of alcohol, their number of deaths we can anticipate more. And this is what is happening if we compare number of deaths per 1 million population due to alcohol-related liver diseases. India as a whole, for every 1 million population, there are 160 annual number of deaths. Because what we find is, for a 1 year period, how many deaths will be there, how much is the economic burden, how much will be the productivity losses, those things we found. And India as a whole, there are 160 deaths per million population, but these deaths per million population vary substantially across states, with Arunachal Pradesh is anticipated to have highest number of deaths due to alcohol-related liver diseases per million population. Per million population, 635 deaths are anticipated here. And in some union territories like Lakshadweep, where population is too less, the deaths anticipated there are 0, because there is less than 1 lakh population is there. There per million population, only 6 deaths are anticipated. And in Uttar Pradesh, just we have seen previously that total number of deaths are highest in Uttar Pradesh due to alcohol-related liver diseases. But when it comes to deaths per million population, is only 111. In fact, this is much lesser compared to all the southern states, all the northeastern states, and many north states as well. Now, this figure shows Delhi's last across the states and union territories due to alcohol-related liver diseases. Total Delhi's last, obviously, it will show a different picture than Delhi's last per million population. But the real focus should be on both these things. I mean, total Delhi's last is important, and of course, and also to know pockets where the loss is more, we need to focus on Delhi's last per million population also. Because if you want to bring changes, the places where per million population burden is high, their interventions has to be a bit stringent compared to other places. Delhi's last per million are very high in northeastern states, southern states, and eastern states. Even deaths also, if you see, per million population, deaths are more in northeastern states, southern states, and eastern states per million population. This is Delhi's last and its components. There are two components: total years lost due to premature mortality from ARLDs, total years lost due to reduced utility from ARLDs. This figure shows that. Yeah, this is the same thing per million population. Per million population, Delhi's last are highest in Arunachal Pradesh and is followed by Sikkim, Telangana, Andaman Nicobar Islands, Goa, Tripura, Manipur, and so on. And Lakshadweep is the union territory where Delhi's last is least and is followed by traditionally alcohol banned state of Gujarat. And the burden is following Gujarat, the burden is least in Jammu and Kashmir and Rajasthan. The economic burden we have estimated, as previously said, in 3 different scenarios. One, respecting people's choice to get treatment from public and private healthcare facilities. So if the people are to be treated as per their choice to get treatment from public and private healthcare facilities, how much will be the total burden at state level and at All India level? And if all the people are to be treated in the public healthcare facilities only, then how much would be the burden? And the third case, only if a fraction of alcohol-related liver disease patients only go for treatment, then how much is the burden? Third, the first 2 cases are hypothetical cases, but they are important because if alcohol is not there in the society, how much burden could be avoided will be there in the first 2 cases. Whereas in the third case, if only assuming only a fraction of people will go for treatment, so it means allowing for silent suffering. So in this case, the first 2 cases only in this presentation I showed. Here, there are in economic losses also there are a couple of aspects: productivity losses, then losses in the form of out-of-pocket expenditure to the people, losses to the healthcare facility in the form of providing treatment to all alcohol-related liver disease patients, and overall economic burden, which is sum of all these components. When it comes to economic so productivity losses and economic burden, Telangana is the state that is having highest burden. You may ask, we have seen in Uttar Pradesh the total number of Delhi's last is high, total number of deaths are high, then why the economic burden is more in Telangana? The answer is simple. See, the economic burden, it depends upon the per capita income of people in the place also. In case of Uttar Pradesh, per capita income is around 60,000 rupee a year. In case of Telangana, it is more than 2 lakh. So loss of a person a year in Telangana is having more results in more economic loss than in Uttar Pradesh. If you see, Telangana, Tamil Nadu are the two states where the productivity losses, not only productivity losses, subsequent slides shown, the economic burden is also very high in these states, Telangana and Tamil Nadu. And as seen previously, deaths are less in Lakshadweep, Delhi's are less. Obviously, then productivity losses and economic burden is also less in Lakshadweep. In the two hypothetical scenarios, along with their components, say for example, in case of Uttar Pradesh, now if all people are to be treated following their current preference, there 413 billions of INR, Indian rupees, will be lost per year. And majority of this is in the form of out-of-pocket expenditure. And a part is, the next high part is due to productivity losses. And only a small fraction is, a burden is falling on the government in the form of providing treatment to those coming to the public healthcare facilities. And this is the case, this is the total economic burden in case if all people are to be treated as per their choice to get treatment from public and private healthcare facilities. Now, and this here I am comparing, due to alcohol, various state governments are getting tax revenue due to alcohol, so-called excise duty. At all India level, around 2.05 lakh crore of income various state governments are getting due to alcohol related revenue, means as excise duty. But the burden due to alcohol related liver diseases at all India level is 3.807 lakh crore. 3.807 lakh crore, which is more than 150% burden than the tax revenue on alcohol. Now this is alcohol related liver diseases is only a fraction of the total burden due to alcohol. Now, as I said in the initial itself, alcohol is responsible for more than 200 disease and injury conditions. Just because alcohol related liver diseases itself, of course, I mean, is a different thing. This is the major kind of burden. 50% of the burden due to alcohol is due to this. Now, if all the 200 disease and injury conditions are added, the burden will be much, much more than what the income that government is getting on alcohol. I'm just skipping the, I don't know how much time I'm left.
Sir, can you please continue if it's not enough? Hello, sir. Hello, Professor.
Yes, madam. Yes.
Can you please continue?
Yes. Now, previously what I showed is burden, annual burden during 2021, or exactly speaking, 1st March 2021 to 28th February 2022. But now here, how much is the projected burden? How the burden, burden is changing over the years 2023 to 2031. This is how the burden is anticipated to change. Even if the level of drinking in 2021, if it remains same over the next 10 years also, but the burden is going to increase because the population size is going to increase. As a result, number of drinkers are going to increase, and hence the burden would increase. Between 2022 to 2030, the deaths are anticipated to increase from 2.2 to 2.4 lakh per year. Similarly, Delhi's are anticipated to increase. Productivity losses are going to increase. Economic burden is going to increase. But when we see, as compared to number of deaths and Delhi's lost, productivity losses and economic burden losses are going to increase very substantially. See, for example, here from more than 1,000 billion INR to more than this is 2,500 billion INR. Similarly, economic burden. I mean, this is productivity losses. This is total economic burden. This is because our income is going to increase almost a double over the next 1 decade. So obviously, as a result, economic burden is also going to double due to these alcohol-related liver diseases. And if we see across the regions, now as far as the projections are concerned, we did it across regions instead of across states and union territories. In southern India, annual deaths are going to increase from 60,029 to 64,442 between 2022 to 2031. Similarly, in other regions, this is how the number of deaths are going to increase. In all the regions, the deaths are going to increase. And Delhi's are going to, Delhi's last disability adjusted life years are going to, Delhi's last are going to increase across all the regions. Similarly, productivity losses are going to increase, but the productive losses are anticipated to increase substantially in southern India as compared to the other regions. Similarly, economic burden is anticipated to increase more in southern India than compared to the other regions over the next 1 decade after 2022. And if you see how much is the total burden, what we have seen is how annual burden is going to change across regions. This is how the total burden over the next 10 years, starting from 2023. In South India, 6.19 lakh people are going to die due to alcohol-related liver diseases. In East India, it is 5.81 lakh. And in case of Northeast India, it is 1.52 lakh people are going to die over the next 10 years due to alcohol-related liver diseases. And similarly, and this is deaths per million population. How deaths per million population is will be over the next 10 years. At all India level, 163 deaths per million population during this period. The same thing during 2022, it is 160 only. So deaths per million population are also is anticipated to increase further. Similarly, the Delhi's last, and then economic burden estimates are given here. Total burden over the next 10 years. And here is the summary of important findings. A total of 218,169 deaths were estimated due to alcohol-related liver diseases in India during the study period of 1st March 2021 to 28 February 2022. I mean, this is the annual number of deaths. You can think literally that at present, because situation is not going to change dramatically over 1 year to other year. So this is what they estimate for 2021. So merely this is the estimate even for the current year, roughly, maybe some plus little. Around 2.2 lakh deaths are happening in India due to alcohol-related liver diseases over every year in the recent period. That's what the story is. And more than 10,000 deaths are expected due to alcohol-related liver diseases in 10 out of 28 states in the country. At all India level, a loss of 8.2 million Delhis is estimated due to ARLDs, and 60% of this loss is due to premature mortality from alcohol-related liver diseases. Arunachal Pradesh, Sikkim, Telangana, Goa, Andaman and Nicobar Islands, and Tripura were the 6 states or union territories that experience highest health and economic burden per 1 million population. And Lakshadweep is the union territory where the burden is the least. If all the ARLD patients are to be treated, considering their usual preference to get treatment from public and private healthcare facilities, it would cost 3,807 billion INR. In terms of US dollars, it is 46.40 billion US dollars. And this is more than 85% higher than the combined tax income on alcohol to all the states and union territories in the country. Alcohol consumption is highest in North India and is followed by southern.
Sir?
Yes, please. So, okay, let me continue. Consistent with high drinking in northeastern states and southern states, the burden is also high in northeastern states and southern states. When it comes to economic burden, southern states are worst affected. When it comes to health burden, that is in terms of number of deaths, northeastern states are worst affected in India. Assuming that the current level of drinking continues in future over the next 10 years, it is anticipated that 2.34 million deaths are expected in India, and a loss of 93.3 million disability adjusted life years is also anticipated at all India level. And at national level, the annual deaths due to ARLD are forecasted to increase from 2.2 lakh to 2.49 lakh over the period 2022 to 2031, meaning that annual deaths are going to increase over the next 10 years. Here is the conclusion. Enormous health and economic burden exists due to alcohol-related liver diseases in India and its states, and there is a wide variation in the burden across the states and union territories. And this change is consistent with the pattern of drinking alcohol, meaning that where there is high prevalence of alcohol, there is high burden, and where there is less prevalence, obviously there is less burden, health and economic burden due to alcohol-related liver diseases. The total economic burden due to alcohol-related liver diseases outweighs the income on alcohol to various state governments. This is here are the references. Thank you.
Sir?
Yes, madam.
Am I audible, sir?
Yes, madam. Yes.
Sir, nice presentation. Yes, sir. Nice presentation, sir. Only 2 things.
Yes. Madam, your voice is breaking, madam. I am unable to hear you.
I think she is not audible. Very good presentation, Dr. Rao.
Thank you, sir.
I have one simple question. What is the source of your data?
Yes, sir. Sir, we used more than 40 sources for collecting this data. As far as population figures are concerned, population estimates are concerned, Census of India, they projected population from 2011 onwards up to 2036. That report we use for population estimates, and for alcohol prevalence estimates we banked on NFHS data sets, and for all other parameters more than 70 health parameters are involved, and more than 400 demographic parameters are involved in the calculations. These 70 parameters we have taken from different published articles, I mean medical related parameters, for which I have taken the help of epidemiology, my epidemiology collaborators.
Okay, that's great. And which round of the NFHS data?
Obviously the latest one, sir. The NFH is 5, the last one. Yes.
Okay, okay, that's good. That's good. Thank you.
So great, sir. Am I audible, sir?
Yes, madam.
So only two things I would like to ask, sir. One is like about the relative risk estimates for mortality.
Relative risk estimate for mortality. What you are asking, madam? Yes.
Yes. Has it been estimated or any analysis has been done on that?
No, madam. Relative risk, all those things we haven't estimated anything. Rather, directly the total number of deaths due to alcohol-related liver diseases we have estimated.
Okay. The second one is about the any prognostic factors. The effects on the prognostic factors, has it been analyzed?
Because this is not a kind of regression kind of analysis. Rather, this is a kind of estimation and forecasting. So those factors we have not taken into account, madam. Those any
Thank you,
regression.
sir.
Okay,
Thank you, sir. Thank you very much.
Thank you.
I have one question.
Yes, sir, please. Yes, sir.
Okay. Thank you very much. A very nice presentation, Professor Samsarao.
Thank you, sir.
And I have one question.
Yes, sir.
Which models you used for this?
Sir, it is this discrete stochastic process approach. Yeah, just let me show you. These Markov models only I used. I'll just, because there is not enough time for me to present many things. Even most of the results also I didn't present. Main things only I presented. And these to find person years spent in different liver disease states, I used this Markov modeling approach. These transitions, all those. Yeah.
Okay. Not a time series models.
Hello. Yes, sir.
Yes, sir. That also I have used.
Okay. Nice. Yes. Nice to hear. Nice. Thank you.
Thank you, sir. Thank you so much.
Thank you, sir. Thank you so much.
Thank you, madam.
Let us all give a big round of applause to Professor Samsarao also. The next presentation, sir. Thank you, sir.
Thank you, madam.
We move on to the next presentation by Professor M. Ramakrishnan, sir, from Ramakrishna Mission, Vivekananda College, Chennai. And Professor is going to talk on performance of all the Indian batsmen in the year 2023 World Cup squad, a survival analysis approach. So, over to you, Professor.
Okay, thank you, madam. I think I am audible.
Yes, sir. Yes, sir. Please. Yes, sir.
Yes, ma'am.
Please, sir.
I'm sharing my screen.
Yeah, please, sir.
First of all, I thank Professor Sri Satish Kumar. Continuously is organizing excellent conferences and seminars and competitions for the encouragement of the researchers and also giving opportunity for the researchers like me continuously. Because of that only, we are searching something and doing some research work continuously. So, and also I thank my senior teachers and well-wishers, Professor P. Venkatesan from ICMR and Dr. G. Gopal from University City, and my guide R. Ravanan. Why I am telling means, even I am working in the Arts and Science College as a mathematics professor. I am doing research in the field of survey in the year of 2007, but we didn't get World Cup within the gap of 13 years. And also, India came faced finals in the test match also. But this is the dream of the Indians. So what we thought in the last ODI World Cup match, we are all know it gone, and the Indian faced the final and we lost the match against Australia. Before that, in the September 4th, we collected the data of the Indian squad. They are announced. At the time, we collected up to 4th September 2023. Under the squad, we have selected the batsman list. So with the help of these things, the organizer may feel which batsman we can place opposed to the team, and we will play the particular batsman in the top order or bottom order or in the middle order. In which position we will put it. These are the things we kept it in mind. Myself and Professor Viswanathan, we sit together and we have taken the data from the ESPN Cricket Info website, and we tried put it in some survival model, and we gotten some observation. Those observations may help the organizer. We thought it, but the same approach we faced in the match also, the final match in ODI. That is which is happened in the 5th October 2023, between 5th October 2023 and 19th November 2023. So this is this motivation we did in this one. So here we have taken the data from the particular website I already told, but we used some survival method. So many methods are there in survival analysis. So non-parametric Kaplan-Meier approach and semi-parametric, and also some non-parametric tests for comparing the survival distribution of the pattern. So then, and keep it in the mind, the parametric approach is also there. What type of the distributions, the survival pattern made for the each player, that is also we can get it from the data. So these are the statistical methods we applied for this each batsman's data. And we compared it for the whole India team also. So many things we thought it in mind. What are the things we come to in mind? We applied it in with the statistical survival model, what I told now. So with that we got some information from that one. So these are all I kept it in the discussion and the conclusion, because we have so many authors did apply the survival model for the cricket data also. So we all know the survival analysis is the study about time to event data. Time to event data, here we have taken the survival time as runs scored by the batsman, and the event is the getting out or not out. So when getting out, it is a survival time. Then not out, we are considering as a censoring concept. So mostly these are the survival analysis used in the medical field, and also you are also mentioned the sometimes failure analysis and the reliability analysis. So these are all the one type of survival analysis. Whenever it is used in the medical field, it is called as a survival analysis. But this data we have taken and applied these techniques. So I have already told the Kaplan-Meier method of estimation, the Cox proportional hazard model, the parametric model we applied for the each batsman data. Then with the help of the R programming language, now the recent version is 4.4.1, and using some few packages, survival package and survey minor package, we use and get it our output, and also nice figures also. So we are all know this is the survival model. Study starts here. We are just getting the data of the each match the player played from starting to and getting out or getting not out. So that is our follow-up time. If it is getting out, therefore event happens. Not getting out means that is censoring or retired out. This is also we have taken as a censoring. So this is the Kaplan-Meier estimator. This is a non-parametric method. This is a well-known method used by the researcher, those who are doing the survival analysis, because it does not involve any distribution. Easily we can find it. There another method is also that is called the Nelson-Allen method. We used this method in our study also. When to get it the survival probability. To get the survival probability, how long the batsman will stand after 10 hours, 10 runs, after 30 runs, or after 50 runs, 70 runs, or 100 runs. These are the things we can obtain with the help of the Kaplan-Meier non-parametric estimate. So when comparing the two batsmen, or when comparing the opener and middle order and lower order batsman structure, we use the whole survival pattern. It is significant or insignificant, that can be obtained with the help of the log rank test or Pito test. So here we are using log rank test for comparing the survival patterns are equivalent or not. So another important method is called as a Cox proportional hazard model. It is called as a semi-parametric model. It does not involve any distribution, unstructured structured distribution, but it involves the structured parametric parameters. Therefore, it called as a semi-parametric method. So therefore, it is a hazard function split into two parts. One is a baseline hazard, and the another one is the exponential of the function containing the variables. So for using the Cox this one we need to one assumption that called as a proportional hazard. Proportional hazard assumption needs it is throughout the study it is constant. So related to the hazard. Therefore, another thing, these are all tested by the exponential residual, because we are in this study we use these things. We verified the proportional hazard satisfied or not. Everything we done it. After the thing only we found out the hazard ratio between the players and between the innings the player played. So the another one is called a parametric model. That is our data should follow some parametric structures. It is exponential or variable, log normal, or log logistic distribution. So therefore, we apply the parametric model also in our data and obtain the structure, the pattern of the each player in what type of the pattern. This is exponential in the increasing or decreasing or increasing and decreasing structure. So everything we can obtain with the help of the parametric model, and also these are also verified. The data is satisfied for these type of all model or all. These are also verified with the help of the graphical methods. So this is the data structure and methodology. I told you, because before World Cup ODI match starts, we kept this data before 1 month. They announced the squad for the World Cup of 2023. So therefore, these are the batsmen we have taken: Kohli, Rohit, Rahul, Gill, Suresh Iyer, Hardik Pandya, Ishan, Jadeja, and Surya Kumar for the study. So here we have taken runs of the batsmen were considered as a survival time. So what are the things we analyzed here? For log rank test innings, they are facing. They have some type of runs, and chasing they got some runs innings. These are all compare. We take it as a covariates, innings and positions. So we divide the positions top order, middle order, and lower order. So when the player stands in the position of first, second, third, we consider as a top order. 4th, 5th, 6th, 7th considered as a middle order, and the remaining 8, 9, 10, 11 positions are considered as a lower order. Some cases the Kohli itself played in the top order and also the middle order. So usually the Jadeja played in the middle order and the lower order. So therefore, with the help of the log rank test, the comparison is made. Then these are the things I told you. No, yeah, two group comparisons also made. What are the survival pattern of the top order players and the middle order players? Here we consider the 5 players: Kohli, Rohit, Rahul, Gill, Suresh Iyer as top order players. Hardik Pandya, Ishan, Jadeja, and Surya Kumar are middle order players. So the here I have given here. Okay. So then next thing is in the previous match, the day before yesterday also, we observed that Akshar Patel played in the place of Dubey. Because of the scenario in the final, the South Africa within few hours, 3 wickets are gone. So therefore, the strategy of the organizer, they send Akshar Patel in the place of Dubey. That will create the motivation to Akshar Patel, and he scored nearly 47 runs. That 47 runs is the one part of the victory, because all the players are contributed in the day before yesterday match. This is the statistical analysis. We can observe that what type of people we can send them in the position. So that is also analyzed in the through the survival patterns. So therefore, in against which team we can send the particular player, that can be also obtained with the help of our survival probability concept, survival techniques. So therefore, here, so how long the player will stand when he already scored the runs 10, 30, 50, 70, and 100, we will expect Kohli will stand up to 100 or up to 50 when he the position, the probability. With the help of the things, the other players will be some confidence. So these are the things I already told. So here we use the position and hazard ratio. Two variables are taken and apply the non-parametric method also, and semi-parametric and also parametric method also we did it. And with the help of the AAC and the BAC value, which player distribution we can find it. So and also the another thing is when comparing with all nine players, when compared to with which one are having the survival is higher, that is also we can find it with the help of our Kaplan-Meier approach. So this is the descriptive statistics of the batsman. Kohli played 266 matches. This is ODI. So therefore, average run secured by all the players, the maximum average run is got by the Gill. Then the least one is Jadeja, 21.10. So these are the descriptive statistics I have given. So all the batsmen except Ishan and Shreyas Iyer didn't get the 0. So therefore, this is the survival probability of each batsman. So therefore, from the table, we can easily understand Kaplan-Meier approach. So therefore, we can expect the Kohli will play after 10 runs with the probability, the survival probability is 22.56. But Hardik Pandya didn't get the 100 up to now. Therefore, these are all Hardik Pandya, Ishan, Jadeja, and Surya Kumar are bottom order players, because they didn't get a chance to play. Among this one, Ishan got centuries, and we will expect Ishan will get century after 100 runs. He will stand. Possibility is 6% chances will be there. So this is the nice survival curve comparing all the batsmen. Easily we can understand the Kohli and Rohit are got maximum runs, because you see that the number of runs from Kohli and Rohit are very higher. So this is the nice graphs and tables explains. This is the pattern between among openers. This is the pattern among that is a middle order people. So here there is no significant difference exists among the openers. We can send them in any order, first, second, or third. Similarly, here also this is Iyer, Pandya, Jadeja, and Surya Kumar. There is a not significant, but when comparing, overall pattern is not significant. When comparing the pairwise Kohli and Gill by using Lagrange test, this is the chi-square value, this is the p value. They are all not significant. Therefore, there is no significant difference among these 5 people. But here, when middle order people, when comparing the survival pattern of, that is the scoring pattern of Iyer and Jadeja, there is a significant difference is there. And also Shreyas Iyer and Surya Kumar Yadav, there is a high significance is observed, because Shreyas Iyer obtained the maximum runs. So this can be identified with the help of our log-rank test value. Whatever I told, that is I have written here. The next one is when comparing the opener is one group and the middle order is one group, this is the survival probability. But you see that the top order batsman getting the more runs than middle order people. So there is a significant difference exists between the open order batsman and the middle order batsman. So this is also another thing. Therefore, among the 266 matches, Kohli played facing innings 120 and another thing is second innings, that is 146. Chasing innings is 146. Because here you see that Kohli is getting maximum average runs in the chasing. When we expect Kohli, whenever we are going to get high runs in the chasing field. But we observe that Rohit and Rahul, these are all written in the green. Rahul, Gill, they are got the average runs in the first innings. But Suresh Iyer, Hardik Pandya, they are all got the higher runs in the average runs in the second innings. These are the things we obtained. But the Kaplan-Meier approach, the significant difference for up to 10% level only exists for Kohli, because there is a survival pattern of first inning scoring and the second inning scoring is there, but it is not for all other players. So these are the things we have written here. So another thing is when we consider about the players against 16th, here we have taken the players among the 9 players, those who have played 50, at least 50 matches and at least 10 matches against the each team, then only we consider. So the Kohli, here, this is the Kohli, is you see that the Kohli is the day before yesterday, he scored maximum runs against South Africa. So what is the things, therefore, we will expect that the Kohli will stand after 10 runs, it is 82% against South Africa. So he will play, he will get 100 runs, more than 100 runs, we will expect. He will stand after 100 runs. The probability is 22% is there. So these are the scenario we can send the players against the particular team. So similarly, we have so many players against so many teams. But you see that so for against Pakistan, yes, only 50% chance to stand. Minimum percentage of the chance to stand after 10 runs. So this is for Jadeja and this is also for Pandya. So this is the survival curve for this one. Whatever I'm told, this one things. Each table, each player, we can explain these things. So similarly, so our expectation is conditional probability we applied here. This is survival conditional probability. So what is the meaning is the 30-10 means if the Kohli playing 10 runs, we expect Kohli will stand up to 30 runs. The chance is 75%. We will expect Kohli will when Kohli is in 10 runs, we will expect he will be we will stand up to 100 runs is 30% of the chances are there. So similarly for Rohit, similarly for Rahul, similarly for Gill and Suresh Iyer, this is the data. From the data, we can understand their experience and how they will stand in the crease against the particular team and whenever they are taken the runs. So this is for Hardik Pandya. So therefore, when comparing with the using the Cox pH model, and two variables are there, innings and the position. We separated the each one played. If they are played in the first, second, and third, we comprise them as a top order. And fourth, fifth, sixth, seventh. At the time, the same Kohli is played in fourth, fifth, sixth, seventh. That is the middle order. So there is any significant difference exists or not, that can be observed. So the only observation we have seen in the non-parametric approach, Kohli has some significant survival pattern of the innings, chasing or facing. The same thing observed in the Cox pH model also. So therefore, here Rohit has a significant difference when played in the position of the top order and middle order. There is a significant difference is that. These are the two things are observed. This is the verification for proportional hazard assumption. We got the p-value is greater than 0.05. So the A, B, C denotes that denote how many matches they are played. Among 266 matches, Kohli played in the position of 1, 2, 3. That is the top order, 218 matches. In the places of middle order, that is the 4th, 5th, 6th, and 7th, the 48 matches. So Rohit only played in the only one match in the bottom order. That's the bottom order means 8th, 9th, 10th, and 11th. So these are all things motivate and finding the player how they are playing in the which position. So these are all the things we observed. Then we use the survival parametric regression approach, and also we verified it through the graphical approach and find it there is any significant difference exists between innings and also the position. When I am considering the 0, it is impossible. Therefore, we have taken it as a 0 when Kohli is out at the time of 0. Then we consider it as a 0.001, 0.0001, and 0.00101. Then it does not affect our model parameters. That's why we have taken in the place of 0, we consider it as a 0.001. And we tried it, and we got the result. So here, this is the Kohli time ratio. Time ratio means innings exponential, only innings we have taken. So therefore, I told the accelerated failure time, the median survival time of the one innings is equal to the median survival time of the alpha into the time. So therefore, that alpha is an accelerating factor. So therefore, here this is the alpha is 1.29. That is called as a time ratio. Among this, which value AAC and BAC, which one is the least? We can select the Kohli played in the pattern of this type of distribution pattern. So this is therefore hazard ratio between scoring the runs. We kept Kohli as a base player, and others are other compared to the other players. So there is no significant difference exists for these type of players and Kohli survival pattern of scoring runs. Rohit, Rahul, Gill, and Suresh Iyer and Ishan something. But there is a significant difference exists between Kohli and Hardik Pandya, Jadeja, and Surya Kumar Yadav, because they are getting run out early than Kohli. So these are the things we observed it. This is 1.599 means the hazard ratio is 1.599. That is 1.5 times more hazard than compared to Kohli. Surya Kumar also 2.142 times. So this is our conclusion. So survival estimate, hazard ratio, time ratio are used to predict the performance of the batsman. So before the World Cup, we did it. So this study helps to find the performance of metrics of the batsman. That will be useful for placing him in a particular position, because I told you it is a top order, bottom order, or lower order. So Kaplan-Meier method, we observe that significant differences. Position of the batsman, the same thing we observed it. So opposite to the opposite team also we consider. These measures evaluate each batsman's performance, and with the help of this prediction, the captain and the whole team may take the decision to send the player in the batting order against corresponding opposition. If they know the opposition and the order of the batsman, in which order he will play more well, then we can send them. So this study also evaluates batsmen during the live match and at every run he is scoring. The parameter model helps us to identify the best distribution fit and further enable us which batsman has high performance in terms of getting run. These are the some observations we got it. That observation will be useful for the organizer and also the commentator also. Nowadays, the commentator also, when they are doing their commentary, they are expecting this type of player should place in the place of so-and-so or something. These are all the references we made it. So thank you.
Thank you, Professor. Any questions from audience? If not, Professor Ramakrishnan sir?
Yeah, please.
Yeah, we would like to place our sincere thanks for your nice presentation. And maybe a comparative analysis of hierarchical Bayesian model and Gaussian process model can be included as a suggestion.
Yeah. Because we are expecting in the same survival model, the competing risk model,
Yes.
the player getting run out, then recurrent event model also.
Yes.
After 50 and after 50.
Yes,
That is our suggestion.
Yes, sir. This is a suggestion from my side. Thank you, Professor.
Thank
So, at the outset, we would like to place our sincere thanks to all the speakers, Professor K. M. Shakti, Professor G. Sirishaman, Professor Ritan Grobo, Professor Samithiva Rao, and Professor M. Ramakrishna. Thank you very much. Let us give a big round of applause for all the speakers. And at the outset, I would like to place my sincere thanks to Professor Satish Kumar, sir. Thanks for the opportunity given to me, sir. Thank you so much. Thank you, sir.
Thank you, Professor Vijayalakshmi, for chairing the session, and thanks to all the speakers, especially the Professor Ramakrishnan and all other speakers for your wonderful talks.
Thank you.
Now, let us move to the next session. We became a little bit late by the last session, even though there are several speakers. That's why. Okay. Now, we are expecting a very good session on design of experiments organized by Professor D.K. Ghosh of the stalwart and the area of design of experiments. Now, let us listen to that before for chairing the session. Professor Paramesh Pandit is here in the group. Khadija is here in the group, isn't it?
Yes, sir.
Please introduce the chair and help the chair to run the session in a better way.
Sure, sir. Good afternoon, everyone. We are moving on the 20th technical session of WTSA 2024, which is an invited session organized by Dr. D.K. Ghosh, and the session shall be chaired by Dr. Parameshwar V. Pandit. Dr. Parameshwar V. Pandit is a professor of Department of Statistics in Bangalore University. He is having 25 years of teaching experience and 20 years of research experience. He is having 29 national and 31 international publications. He is a life member of Indian Statistical Association, Pune, and Indian Society for Probability and Statistics. His research interests include non-parametric inference, inference on reliability, non-parametric quality control, and SPRP. We feel privileged to have you with us, sir, for chairing the session today. Without delaying you further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Welcome, Rose. Welcome.
Good evening, everybody. Yeah, am I audible?
Yeah, Professor, audible.
I am audible. Okay. So, thanks for the nice introduction. I would like to thank the organizers, particularly Professor Satish Kumar, for giving me this opportunity. And the session is on design of experiments, organized by Professor D.K. Ghosh. And we have 3 speakers in this session. The first speaker is Poonam Singh. The second speaker is Shyam Saurav. And the third speaker is Professor D.K. Ghosh. So we will start the session with Professor Poonam Singh. However, let us stick on to the timings. Particularly, let us have 25 minutes of presentation and 5 minutes for discussion. And if we stick on to that, I think we can be in time. And I request Professor Poonam Singh, University of Delhi, to give a talk. The title of the talk is Mappable Nearly Orthogonal Arrays Using Difference Matrices. Poonam Singh, please.
Very good evening to everyone. First of all, I would like to thank the organizers for giving me this opportunity. Am I audible to everyone? Namaskar.
Yeah, audible.
Yes, you are audible.
So,
you are audible.
Okay. Can you see my slides?
You can see your slides also.
Okay, thank you. So let me just make it full screen and slideshow. So today I am going to talk about mappable nearly orthogonal arrays using difference matrices. So mappable nearly orthogonal arrays are basically nearly orthogonal arrays which are mappable to fully orthogonal arrays, and in this work we have used difference matrices to construct these arrays. Now, so I'll begin with the introduction of the orthogonal arrays, then I'll move on to the nearly orthogonal arrays, and then to the mappable nearly orthogonal arrays, and then I'll discuss the method which we have proposed, and I'll take up certain illustrations for that. Now, in 1946-47, they have introduced orthogonal arrays. Bose and Bush in 1952, they have provided a suitable upper bound on the number of constraints for a given array, for an array with a given index, level, and strength. Bush 1950 have explained the interpretation of meaning of orthogonality in orthogonal arrays. Here, the orthogonal is different from orthogonality of the columns, and it is also different from orthogonal matrices. Difference matrices, Hadamard matrices, Latin squares, BIBDs, projective geometries, they all play an important role in the construction of symmetric and asymmetric orthogonal arrays of strength 2 and 3. Orthogonal arrays have been widely used in medicine, agriculture, computer science, cryptography, and manufacturing industries. But the main application of orthogonal arrays is still as fractional factorials in screening experiment, where these are used for identifying the important factors to improve the quality and productivity. So what is an orthogonal array? Orthogonal array is an array or table whose entries originate from a fixed finite set of symbols, say 1 to p. These symbols are arranged in the array in such a way that if we select any t columns from the table, all ordered t tuples of the symbols occur equally often as a row. And such an array is called an orthogonal array of strength t. So the formal definition of orthogonal array is, it's written here. We have two types of orthogonal arrays. First is symmetric orthogonal array and asymmetric orthogonal array. When the number of levels of each factor is same, then we have a symmetric orthogonal array. So the formal definition is an n cross k array with entries from a set G of size S is said to be an orthogonal array with S levels, strength T, and index lambda, where T lies between the range 0 to K, if every n cross T sub-array of A contains each T tuple based on G occurring exactly lambda times as a row. So the NKST, and lambda are called the parameters of the orthogonal array, and such an array is denoted by OA NKST. And orthogonal arrays are discussed in detail in the book by Hidayat et al. 1999. So this is an example of an orthogonal array. Here we can see that the number of rows is 8, number of columns is 4. So capital N is 8, small n is 4. Number of levels in each factor, for each factor is 2. And the strength of this array is 3, because if we consider all 4 tuples with 2 symbols, we require 16 runs to repeat each of the tuple exactly once. So this cannot be an array of strength 4. So when we look at any 3 columns from this array, we can see that all possible 3 tuples with 2 symbols, which are 8 in number, they occur equally often as a row exactly once. So this is an array of strength 3. This array is also a strength of 2 and 1 because an array of strength T it is also of strength T dash where T dash is less than or equal to T. So it is easy to construct an orthogonal array of strength strength 1. We can see here it is an orthogonal array with 2 runs, 12 factors, each with 2 levels, and the strength is 1. But in general, it is difficult to construct orthogonal arrays when the strength of the required array is large. So there are some properties of symmetric orthogonal arrays. If one orthogonal array can be produced or obtained from another by a series of permutation of columns, rows, and levels of each factor, the two orthogonal arrays are said to be isomorphic. And we have not written the lambda in the parameters of the orthogonal array because this can be obtained from this equation, lambda equal to the total number of runs in the design upon s to the power t. Any orthogonal array of strength t is also an orthogonal array of strength t dash, where t dash is less than or equal to t. Also, if we have, say, L orthogonal arrays, say, denoted by AI with parameters Ni, K, S, Ti, then by juxtaposition of these L arrays, we can obtain an orthogonal array with parameters N, K, S, T, where N is summation Ni, and strength T, where T is greater than or equal to minimum of T1, T2, TL. Rao 1947 was the first one who obtained the upper bounds on the largest number of factors in an orthogonal array. This is the theorem. The first inequality is 4 when the strength of the orthogonal array is even, and the second inequality is where the strength of the orthogonal array is odd. And this is also used for determining the minimum number of runs required for the existence of an symmetric orthogonal array. And if we get the minimum number of runs in the array, then such an array is called a tight orthogonal array. This means tight orthogonal arrays are those arrays which meet these limits. This is an example of a symmetric orthogonal array. Here, in the definition, we can see that a symmetric orthogonal array is with n runs, summation ki factors, where k1 factors are at s1 level, k2 at s2 levels, kn factors are at sn levels. So it's a matrix of order n cross k, where k is summation ki, and the total number, which is the total number of factors, with the property that every n cross t subarray contains every possible t tuples equal number of times as a row. So when we look at this array, we can see that the first 4 columns, they have 2 symbols, and the last column has 4 symbols. So this is an orthogonal array. This is an example of a symmetric array, and the strength of this array is 2. In the past years, several research studies have been done on the construction and application of orthogonal arrays of various strengths. Some methods of construction of orthogonal arrays are given in the paper by Bush in 1952. And the construction of orthogonal arrays is a very important problem in combinatorial designs, and it holds a significant significance for the design of experiments in statistical analysis. The construction method of orthogonal arrays are discussed in Hidayat et al. So one can refer this book by Hidayat, Sloan, and Stufker. So when the number of factors to be investigated is much larger than the number of runs in an experiment, then we have 2 options. Either we can omit some of the factors, or another option is we can use a supersaturated design. So supersaturated designs are fractional factorial plans in which number of runs is not sufficient to estimate all the main effects. The main attraction of using SSDs is their run size economy. These designs provide low-cost identification of few possible dominating factors in screening experiment. And Zhu and Wu, 2005, have proposed general methods for multi-level supersaturated design. So due to run size constraints, nearly orthogonal arrays can also be considered as a good alternative to OAs. Wang and Wu proposed the concept of nearly orthogonal arrays and constructed many nearly orthogonal arrays with appropriate run sizes and high efficiency. So these nearly orthogonal arrays means that in this some of the columns are not every n cross 2 submatrix of the array, not in every submatrix of order n cross 2, every 2 tuple will occur equally often as a row. So Zhu 2002 has given an algorithm for constructing orthogonal and nearly orthogonal arrays with mixed levels and small runs. So now let's come to the mappable nearly orthogonal arrays. So these mappable nearly orthogonal arrays are basically nearly orthogonal arrays which are mapped to a fully orthogonal array. So Mukherjee et al. In 2014, they introduced and constructed a class of nearly orthogonal arrays which are called mappable nearly orthogonal arrays. They have used resolvable orthogonal arrays for constructing these arrays. So this type of arrays before mapping satisfies the property that each column of a group is orthogonal to a large proportion of other columns of the same group or other group. So this means in the pre-mapping array, this condition is satisfied. And then these arrays are convertible to fully symmetric and asymmetric orthogonal arrays by using some permutation of symbols in the columns or by collapsing the symbols of the pre-mapping array into smaller set of symbols of fully orthogonal array. And the pre-mapping array of mappable nearly orthogonal array can also be viewed as supersaturated designs. Now let's come to the definition of this mappable nearly orthogonal array. A mappable nearly orthogonal array with the parameters n, product of Si, Ci, and this is a n cross C tilde matrix, is a matrix of order n cross C tilde, where C tilde equal to summation Ci. So the total number of factors is summation Ci. And these columns can be partitioned into m disjoint groups of columns C1, C2, Cm with the following properties. First one is, for I equal to 1 to m, every column of the ith group is populated by Si symbol. So in the ith column, every factor takes takes Si symbols. Any two columns from different groups are orthogonal, and for I equal to 1 to m, j equal to 1 to Ci, the Si symbol in the jth column of the ith group can be mapped to a set of Rij less than equal to Si symbols, such that the mapping convert the array into a full orthogonal array, which is written here. So in a mappable nearly orthogonal array, we have a pre-mapping array, and before mapping, each of the Ci columns in the ith group is orthogonal to at least proportion pi I, where C tilde is summation Ci of the other columns. And so this leads to the following measure of pre-mapping degree of orthogonality among columns, which is given by pi bar, and the minimum value of this pi bar is written here in equation number 2. In particular, if C1, C2, Cm are all equal and equal to C, then the total number of columns or number of factors is MC, where M is the number of groups and C is the number of columns. So by equation number 1 and 2, we get the measure of pre-mapping degree of orthogonality, which is written in equation number 3. So when Si equal to S, so that means levels of each factor is constant, and the number of columns, each group is also constant, and Rij is also constant, fixed. Then for every I and j, a mappable nearly orthogonal array is denoted by MNOA n S to the power C to the power m, R to the power C to the power m. So the total number of factors here is Cm, and in the pre-mapping array, each factor has S levels, and in the post-mapping array, each factor has R levels. So here are the examples of mappable nearly orthogonal array with 16 runs and 4 groups. In the pre-mapping array, we have 4 groups, each group consisting of 2 columns and each factor with 4 levels. And this is on the right hand side. Sorry, on the right hand side, it is a post mapping array where we have 4 groups, each group consisting of 2 columns, and each factor has 2 levels. So this array, which is written on the right hand side, the post mapping array, is a full orthogonal array. The importance and applications of this type of arrays have been of considerable interest because of their inherent better space filling properties. Mukherjee et al. In their paper, they have also mentioned that a mappable nearly orthogonal array with 81 runs, 40 factors, each with 9 symbols. So when we consider an orthogonal array, with 81 runs, 40 factors, and if we want to look for 2 dimensions, then we get 40 C2 dimensions, which are 780 in numbers. So a mappable nearly orthogonal array with 81 runs, 40 factors, each with 9 symbols, it can achieve stratification on 9 cross 9 grid in 720 2 dimensions out of 782 dimensions, and on a 3 cross 3 grid in remaining 62 dimensions. Thus, having a better space filling property than an orthogonal array with 81 runs, 40 factors, each at 3 levels, and also accommodating more factors than orthogonal array with 81 runs, 10 factors with 9 symbols. Because here we have only 10 factors, whereas here 40 factors can be studied. So what is the work which is done in this area? Mukherjee et al. In 2014, they have derived the mappable nearly orthogonal arrays of strength 2 using resolvable orthogonal arrays. Our group has also worked in the direction, and we have constructed nearly orthogonal arrays which are mappable into symmetric orthogonal array of strength 2 using Hedemond matrices, and we have also constructed nearly orthogonal arrays which are mappable into tight symmetrical orthogonal arrays of strength 2 using projective geometry. Lee et al. In 2021, they have proposed 2 methods for constructing column orthogonal nearly strong orthogonal arrays. Chen and Tang 2022 derived orthogonal array-based designs under a broad class of space filling criteria. Liu et al. 2023 constructed a series of MNOAs which possess near or column orthogonality, projection uniformity, and enhance the MNOA's projection uniformity only in one direction. Lee et al. 2024, they have developed a new class of space filling designs for computer experiments. So in this paper, we have used difference matrices to construct a series of mappable nearly orthogonal arrays. And so we have proposed a method, and the post mapping array of these MNOAs are fully symmetric orthogonal array of strength 2. So I'm going to illustrate the method through the examples also. And we have observed that some new MNOAs are constructed, and it is also observed that the obtained MNOAs have high value of degree of orthogonality. And the MNOAs are very useful in computer experiments as designs with large number of factors having benefit of attractive space filling properties. So because we have used difference matrices, so let's see what is a difference matrix. An R cross C matrix D with entries from G, where G is a finite abelian group of order S with a binary operation plus, is called a difference matrix based on G plus if it has the property that for all I and J, where I and J lie between 1 to C, I not equal to J, the vector difference between the ith and the jth column contains every column of G equally often. So necessarily, sorry. So here is an example which is a difference matrix with 4, 4, 2. So difference matrix is denoted by DRCS. Okay? So R is a multiple of S, say R equal to lambda S. So lambda is the number of times each element of G occurs in the difference of two columns. So for example, in this matrix, if we pick up any two columns, say column number 2 and 3, so we can see that the difference is 0, -1, 1 and 0. And the -1 under mod 2 is 1. So the two symbols, 0 and 1, they occur exactly twice. So this is a difference matrix with two levels and index 2. Bose and Bush in 1952, they have developed a simple method for obtaining orthogonal area of strength 2 using difference scheme. So if D is a difference matrix with parameters, say R, C, S, where R is the number of rows, C is the number of columns, S is the number of levels, is a difference scheme over G plus, where G contains the elements 0 to S minus 1, and Di is obtained from D by adding I element to the G, adding element of G to each element of D. Then an orthogonal array can be obtained with parameters RS, C, S2. So we exploit this in our construction. For example, the orthogonal array 16, 4, 4, 2 can be obtained from the difference scheme D4, 4, 4 given here. Okay. So we add elements 0, 1, 2, 3 in turn to obtain the matrices D0, D1, D2, D3. And then we juxtaposition these matrices to obtain the orthogonal array 16, 4, 4, 2. So this is the resultant array. It has strength 2. So now let's come to our method of construction. The method is described here in certain steps. First step is we consider a difference matrix of order, difference matrix with p to the power alpha rows, p to the power alpha columns. That means square matrix with p as a number of symbols in G, where p is a prime number and alpha is an integer. So for I equal to 1 to p minus 1, we obtain the difference matrices Di by adding I to the each element of D. Then we write the matrix C by juxtapositioning of Di in order. So we get C as D0, D1, D2, Dp minus 1. So the C is a matrix of order p to the power alpha plus 1 cross p to the power alpha, where each column has p symbol and each symbol is repeated p to the power alpha times. So in the next step, we replace p to the power alpha occurrences of each of the p symbols in each column of C by p to the power alpha symbols from this set. So for the kth column, we define TKH equal to HP, HP plus 1 and so on, where H takes value 0, 1, 2 up to p minus 1. And replace the p to the power alpha occurrences of the symbol H by p to the power alpha members of TKH in order as obtained in 5. That is, the first occurrence of the symbol H is replaced by HP, and second occurrence is replaced by HP plus 1 and so on.
Excuse me, madam.
Yes.
You have 2 minutes more.
Only 2 minutes?
Yes.
Okay, then I'll rush up. Okay. So this is how we obtain the matrix R. Then we number these matrices, the rows of these matrices by R0, R1, R to the power P alpha plus 1 minus 1. And then we consider an orthogonal array with parameters n and p to the power alpha plus 1, 2. And then we use the, and then we replace the symbols using equation number 5 to obtain a pre-mapping array which consists of n groups, each group having p to the power alpha columns populated by p to the power alpha plus 1 symbols. So then in the pre-mapping array, we use reworked mapping of 5 as described here to obtain the post-mapping array, which is a fully symmetric orthogonal array of strength 2, and it is P with n groups, each consisting of p to the power alpha column and each factor with p levels. So we have this result, which is written here. So based on this method, we have certain constructions for the specific choices of alpha MP. The first construction is this. So this is an example where we have used the difference matrix 2 to 2, and for the specific value of m equal to 2, alpha equal to 1, and we have used this 16 orthogonal array 16, 5, 4, 2 as the array B, and then we have obtained the pre-mapping array, and this is the post-mapping array. And in the second construction, also we have certain specific values of alpha, m, and p, and so this m and OA can always be constructed by taking n equal to this 2 to the power 2m plus 1, n equal to 2 to the power m plus 1 in theorem 2, and then this is the pre-mapping array which we have obtained. It has 9 groups, each group containing 2 columns and each factor having 4 symbols. And using the revert mapping, we obtain this post-mapping array. And similarly, we have a third construction for the specific value of alpha, m, and p, where p is greater than or equal to 3. In the first and second construction, we have used p equal to 2. So this m and OA can be constructed by taking n equal to p to the power 2m and small n equal to this in theorem 2. And this is the example. And here we have used orthogonal array 81, 10, 9, 2 as a orthogonal array B. Sorry. Yeah, this is the array. And because of this space problem, I have not written here the pre-mapping array and the post-mapping array. This is the MNOA which we could able to construct. It is with 30 factors in 81 runs, and the post-mapping array is a full orthogonal array with 30 factors in 3 symbols. So these are the results which we have obtained. Some more orthogonal, mappable nearly orthogonal arrays are constructed using construction 1. So in the rightmost column, we have written the value of degree of orthogonality of pre-mapping array. These are the results which are based on construction 2, and these are results which are based on construction 3. And the value of degree of orthogonality in the last column of all tables is obtained by using equation number 3. And the designs listed in 9 are important, and some other designs are also can be constructed. These are useful because they have greater number of groups compared to the existing designs which are given in Mukherjee et al. Paper. And the increment of number of groups and increased value of degree of orthogonality can be seen here in the table. On the left hand side, we have the existing designs which were there in the Mukherjee's paper, and the designs which are written on the right hand side, these are the designs which we obtained using our proposed method. So in this work, we have given a method for constructing MNOAs using difference matrix. The post-mapping arrays are fully symmetric orthogonal arrays, and the difference matrices of order p to the power alpha, p to the power alpha, where p is prime number or a power of a prime number is used. And we can see that we could able to generate many new mappable nearly orthogonal arrays with increased value of degree of orthogonality. Thank you. These are the references which we have used. Thank you for the patience.
Thank you very much, madam, for a nice talk. And let us have quick questions. Anybody?
Dr. Singh.
Yes, sir.
I think if you consider nearly orthogonal with 2 levels, 0, 1, and then converting it as a 1 and -1, some superstructure design can also be constructed.
Yes, sir. Yeah.
But number of factors will be small.
Yes.
Because you are taking the group of only 2 columns.
Yes, sir. Thank you.
Okay, thank you very much, madam. Let us thank the speaker again. The next speaker is Shyam Saurav from Tata College, Kulhan University, Jharkhand. title of this talk is Some Recent Constructions and Applications of Group Divisional Designs. I request Shyam Saurabh to take over.
Okay, sir. Am I audible, sir?
Yeah, you are audible. You are audible.
I am thankful to the organizer for inviting me to present a talk in the seminar. I am. I am sharing my screen. So is my screen visible?
Yeah.
Thank you, sir. The topic of my talk is some recent constructions and applications of group division designs. First, I start with an example. Suppose consider an arrangement of V equal to 9 elements into 3 cross 3 array as follows, which first row contains 1, 2, 3, second row is 4, 5, 6, and third row is 7, 8, 9. Suppose you want to extract B equal to 9 subsets, each of size K, from the above set of 9 elements such that each element occurs are equal to 3 times, and any pair of elements from the same row of the array occurs together in no subset, whereas remaining pair of elements occurs together in one subset. The above arrangement or construction is equivalent to a semi-regular group division design SR23 with parameters V equal to B equal to 9, R equal to K equal to 3, lambda 1 equal to 0, lambda 2 equal to 1, M equal to N equal to 3. Here, SRX numbers are from the table of Clatworthy 1973. A solution is given below. Here we can see that any pair of elements, suppose we consider a pair of elements 1, 2, then 1, 2 belongs to the no subset of the solution. Whereas if we consider any pair of elements from any two different rows, suppose we consider 1, 5, then 1, 5 occur in the R3 and it belongs to only one subset. Similarly, it can be checked for remaining pair of elements. So now I come to the definition of GD design. Suppose we have V equal to n elements arranged in a certain M cross n array. Then a GDD is an arrangement of these elements in B blocks, each of size K, such that every element occurs at most once in a block and every element occurs in R blocks. R is also called replication number. Further, every pair of elements which are in the same row of the array occur together in lambda 1 blocks, whereas every remaining pair of elements occur together in lambda 2 blocks. We also call lambda 1 as inner occurrence and lambda 2 is also called outer occurrence. The non-negative integers V equal to Mn, P, R, K, lambda 1 and lambda 2 are known as parameters, and these parameters are not all independent but are related by the following relations. The relation is written here. Further, based on the eigenvalues of n into n transpose, a GD design has been classified into 3 categories. First is singular, if r minus lambda 1 equal to 0. Second is semi-regular, if r minus lambda 1 is greater than 0, and rk minus v lambda 2 equal to 0. Further, it is regular if r minus lambda 1 is greater than 0, and rk minus v lambda 2 is greater than 0. And SRGD design having k equal to n and lambda 2 is equal to 0 is also known as a transversal design. And there is a close relationship between a semi-regular GD design and orthogonal arrays. Next, the incidence matrix of a GD, let n be the incidence matrix of a GD, then the structure of n dash is given as, where IM cross IN, in IM cross IN, the cross denote the Kronecker product or direct product of matrices IM and IN, where IM is an identity matrix of order n, Jn is an n cross n matrix with all entries 1. Alternatively, suppose we have any 0, 1 matrix n of order V equal to Mn such that its all block small submatrices are of size n such that each column sum of a small submatrices is K, and the inner product of any two rows of blocks of n is this written as, then n is the incidence matrix of a GDD with parameters this. and the inner product of any two rows is independent of any pair of rows. Further, if we can decompose a 0, 1 matrix N into an M cross N smaller submatrices such that the column sum of each submatrix is K and the inner product of any two row blocks of N is such as, then in this case N is also the incidence matrix of a GD design. This is the example which I already explained. Further, a fine resolvability in a GDD. A GDD is resolvable if the B blocks, each of size K, can be partitioned into R resolution classes, where each resolution class contains B by R blocks, and in each resolution class, every element or point is replicated exactly once. Replicated means it occurs exactly once. Clearly, a necessary condition for a design to be resolvable is that R divides B, or we can also say that K divides B. Further, if any pair of blocks belonging to different resolution classes of a resolvable GDD intersect in same or fixed number of points, then such a design is called affine. Here is an example of an affine resolvable semi-regular GD design. There are three parallel classes or resolution classes as R equal to 3. First class is R1, second class is R2, and third class is R3. Here it can be observed that any pair of blocks from different parallel classes intersect in one number of points. For example, 147 belonging to R1 and 249 belonging to R2 intersect in only one point, which is 4. And it can be clearly checked for remaining pair of blocks. But these are some recent constructions of RGD design. These constructions may be recently found in our paper, which is published in Bulletin of the ICA. Suppose there exists a RGD design, means regular GD design with the mentioned parameters. Suppose N1 equal to this, where 0n is a null matrix and alpha is a permutation circulant matrix, which is explained later, and In is the identity matrix of order n. Clearly, from N1 we can write N2 and N3 also. It is clearly a permutation of these three rows. Then if we juxtapose these three block matrices, then we obtain a regular GD design with the above mentioned parameters. Here is an example. For n equal to 3, we can get the matrices N1, N2, N3 as follows, where 0, 3 is a null matrix of order 3, I3 is identity matrix of order 3, and alpha is a circulant matrix 0, 1, 0. Circulant means we can write the remaining rows using the first row by shifting the elements rightwards. Here you can see that the first row is 0, 1, 0, then second row is 0, 0, 1, which can be obtained from the first row by shifting the elements rightward, and last row is 1, 0, 0, which is wrapped anti-clockwise. We called such a matrix permutation circulant matrix because such matrix can be obtained from a permutation, which are the elements of a permutation group. Further, second construction is from permutation circulant matrix. Here we have considered a set of n matrices, which we have denoted as EI matrices, whose ith row is 1 and remaining rows are 0. Then such matrices satisfies the following properties, which is given in 1, 2 and 1 and 2. And using this property, we can prove the following theorem, which is there exists an SRGD, means semi-regular GD design, with the parameters V equal to 3n, B equal to n square, R equal to n, K equal to 3, lambda 1 equal to 0, lambda 2 equal to 1, M equal to 3, and n, whose incidence matrix is given below. Example is given for if we consider n equal to 4, then using the value of n in the previous theorem, we obtain a semi-regular GD design SR26, which is the design listed in the table of Collet-Verdi, whose incidence matrix is given n equal to this, where E1 is here. Earlier we defined EI as a matrix with ith row 1 and remaining row 0. So then here E1 equal to first row 1 and remaining row 0. E2 equal to second row contains only ones and remaining row 0. Similarly E3 and E4, and alpha equal to circulant 0, 1, 0, 0. This is also a permutation circulant matrix. Further, the next construction is from conference matrices. A conference matrix C is an n cross n matrix with 0 on the diagonal, means diagonal entries will be 0, and off diagonal entries will be 1 or minus 1, such that C into C transpose is equal to n minus 1 into In. In other words, we can say that the inner product of any two different rows of C is equal to 0, and inner product of same row is n minus 1. Then here is the result. The existence of a conference matrix of order this implies the existence of a RGD design with the parameters, whose proof is given. We have considered here two matrices. First of all, we have considered a conference matrix of order T. Then we have obtained two matrices N1 and N2 using C, which is given. And then we have considered a block matrix, which is equal to n equal to first row N1 N2, and then second row is N2 N1. Then inner product of two row of blocks of n is given as the first one is inner product of the same row of n, and second is inner product of different rows of n. Then it is easy to verify that n is the incidence matrix of RGDD with the above mentioned parameters. And here GD design with parameters 2 is the complementary design of GD design with parameters 1. Complementary means in the incidence matrix we can interchange 0 and 1. Further, here is an example given. This is a conference matrix of order n. From here we have obtained n1 and n2. Then n equal to n1 n2 nt11 represents a RGD design. Symmetric hai. This is a symmetric RGD since V equal to P, which incidence matrix is n equal to n1 n2. Further, here are some applications of recent applications of GDD designs. GDD designs are useful in group testing experiments, sampling, intercropping, and factorial experiments. Here reference is cited. Next, GDD designs are applicable in the constructions of low density parity check codes, which are 3 or 4 cycles, and also applicable in heap redistribution schemes. For details, the readers can see Lee and Stinson 2005. Further, affine resolvable and partially affine resolvable GDDs are useful as optimal heap redistribution schemes. The details on this paper may be found in the paper of Saurabh and Sinha 2023D. Further, recently, dual of GDD designs have been used to construct near regular LDPC codes, which can be found in the paper of Saurabh et al. 2024. Further, alpha resolvable GDD designs, where alpha is greater than or equal to 1, are used to obtain LDPC codes with varying code lengths and varying code rates, which can be found in Ju et al. 2019 and Saurabh and Sinha 2023. Further, double resolvable GDD designs have wide applications in coding theory as well in perfect secret sharing schemes, or we can say that in threshold schemes. Here, some examples of doubly resolvable semi-regular GDD design are given. Doubly resolvable means the design is row-wise resolvable and column-wise resolvable both way. Here one can see that every row of this array contains each element 1 times. Similarly, every column of this array contains every element 1 to 12 exactly 1 time. So it is row-wise and column-wise resolvable. Similarly, in example 7, one can observe that the elements 1 to 15 can occur exactly once in each row and each column. Hence, it is also doubly resolvable. We can here say that it is two-way resolvable. Further, here is a table is given of GD designs under the range of RK less than equal to 10, which are not listed in the tables of Colletworthy and the updated table of Sinha 1991. Here are total, to the best of my knowledge, these are the new designs available in the literature. Here the design number 4, 5 and 9 are resolvable, and design number 11 is affine resolvable. The source of these designs will be found in the paper of Saurabh and Sinha, published in Communication in Statistics, Theory and Methods. The design numbers 4, 5, 9 and 11 are obtained by Ghosh and Diveja, 1995. I think the year is 1995. And in this table, E stands for efficiency factor of a GD design, where the efficiency factor of a GD design can be calculated using the formula. This formula is given in the table of Flatworthy. These are the references cited in the paper. Thank you for the attention. Thank you, sir.
Thank you. Thank you for, we have time for questions. If there are no questions, let us thank the speaker for the good presentation.
Thank you, sir.
Am I audible?
Ji, sir. Ji, sir.
Yeah, okay. Okay.
Thanks, sir.
Now, the next speaker is Professor D.K. Ghosh from Marwadi University, Gujarat. He will be talking on hypercubic design and its applications. Over to Professor Ghosh.
So, dear friends, I am very much thankful to Professor Satish Kumar, who gave me an opportunity to organize a symposium on design of experiments. And at the same time, we also thankful to two speakers, Dr. Poonam Singh and Dr. Syam Saurabh, who immediately accepted my invitation to deliver an invited talk in this symposium. So now I am just sharing my it is not working, Dr. Satish?
Yes, sir.
It is not working.
Sam Nigel, yes, sir. What happened? Please send that slide to me, sir. Yeah, it's working, sir.
That is seeing?
Yes, sir. I can. Yeah.
So my topic is E-optimal hypercubic design and its application. Hypercubic design was introduced by Shah in 1958, and then this design was developed by Kusumoto in 1965. After a long time, that Cheng constructed some more hypercube designs using symmetrical factorial experiments and developed an important property of this design in which all the normalized treatment contrasts belonging to the same main effect or interest are estimated with the same variance. This is a very important point. And because of this, the hypercubic design is also called a balanced factorial experiment. Then Jacques studied the E-optimality criteria of the hypercubic design. Next, Thanipara, that my PhD students, we developed some methods for constructing E-optimal hypercubic design developed by the Jacques in 1980. Again, Thanipara et al., that is which we also carried out simple methods to construct some more hypercubic designs using factorial designs, which were developed by the Kusumoto. Again, 2007, we discussed the application of hypercubic designs. Now let us have what is first E-optimal regular graph design. Let ND is defined as NDIJ with the V cross B inset matrix of a design, say D, where Nij is equal to 1 if treatment I occurs in the block J, And if doesn't occur in that block J, then the value will be 0. The design is called binary design because the elements of the N matrix are 0 and 1. Assume that the design D is connected, and then the concurrence matrix ND and D prime with the concurrence matrix of the design D, provided all the diagonal elements of concurrence matrix ND and D prime are equal, and again all the off diagonal elements are differ by at most 1. So since we are considering the binary designs, then naturally the elements of the concurrence matrix will be 0 and 1. Then again, the design is called a regular graph design, and for that we see the work done by the Jacques 80 and Cheng 80. We'll discuss later on. Now let us define what is hypercubic design. An incomplete block design is said to be hypercubic design in which T is equal to V raised to M treatments are represented by M plates x1, x2 dot dot xm, where the x1, x2, xm lie between 1 to B. Now, how to explain the association matrix of the hypercubic design? That is, if any two treatments are ith associates, if they differ in exactly I component, this is a difference from the other designs. So we are making difference in the I components, not in the ith treatments. For all the I is equal to 1 to N. Not I is equal to 1 to V. This is also a very important point. Now, for obtaining the E-optimal hypercubic design, let us consider a lemma first. What is lemma? If a hypercubic design with parameters T is equal to V raised to M, we have considered here only V is equal to 2 and 3 only, because if take V is equal to more, then the treatment should be very large. So this constraint we have kept in this experiment. K is equal to 2 or 3 exist and also satisfy the condition that ZDI is greater than or equal to maximum of A and B. If this satisfied ZD, then D is called E-optimal in design DR, where DR is the class of connected equiduplicated designs. And Z1 is the minimum non-zero eigenvalues of the information matrix C of the design D, which A and B is equal to V raised to M minus 2 into R times K minus 1 minus 2 plus M minus 2 divided by K times V raised to M minus 1 into B M minus 2. Whereas B is defined as B raised to M times R raised to K minus 1 minus M minus 1 upon K raised to V M minus 1. So now I'm not giving proof, but this theorem lemma can be proved in the line of Cheng 1980. So I'm avoiding the proof here. So this is the important point. This criteria should be implemented for finding the E-optimal regular graph design. Now let us have a theorem which is considered as the generalization of lemma 2.1. If a hyperdesign D having parameters T equal to V raised to M, V is equal to 2 or 3, K is equal to 2 or 3, R is equal to R for any I is equal to 1 to M, where lambda absolute value of lambda 2 minus lambda I minus lambda j is less than or equal to 1. But this is the criteria for the regular graph design. So this must be satisfied. If this violates, then the design on with the regular graph design. For all I is not equal to j equal to 1 to m, then D is a regular graph design. And also if D satisfied the condition 2.1 means ZDI is greater than or equal to maximum of AB, then D is an E-optimal hypercube design in class of design DR. A small proof I have just given. Let us have concurrence matrix as ND times ND prime. So this is equivalent to some Nij into Ni prime j, and this value will be R if I is equal to I prime, and equal to lambda times p, lambda p, if I is not equal to I dash. When I and I dash are pth associative treatment, where p is equal to 1 to m. This shows that if the concurrence matrix ND prime of the design D, then all the diagonal elements are equal to R. And of the off diagonal elements differ by at most 1. Hence, by definition, the hypercubic design is a regular graph design. And if this satisfied this design, the condition 2.1, then naturally the design will be E-optimal regular graph design. So this completes the proof, small proof. Now let us have a method of construction. Here we describe how to obtain hypercubic design with V is equal to 2. Now we discuss below method of construction of hypercubic design with parameters T is equal to 2 raised to m, K is equal to 2 raised to also m, R is a MCH, B is equal to TR by K, lambda 1 equals 1. Here I have taken this all construction, first lambda is a 1 and the remaining lambda is a 0. Whereas when we constructed in Fanipara work 2005-7, we took lambda I different 2, 3 also. But this example, this article contains all the lambda 1 as a 1. For I is equal to h and lambda j is equal to 0, for the remaining j is equal to 2, 3 to m. Suppose all the 2m treatment combination we are writing in the form of the factorial ways, that is m treatments are written with all possible combination with taking level 2. So if you take the m is equal to 3, then our 2 raised to m will have the 8 treatment combination, and this 8 treatment combination are 111, 112. Just for one point, here I have taken the level as a 1 and 2, not as usual 0, 1 in case of the factorial design. 121, 122, 211, 212, 221, and 222. We call it a standard sequence of this treatment. This we have to keep in mind to construct the hypercubic design. If I violate this, then there is maybe a problem in constructing hypercubic design. Now, these 2 raised to m treatment combination are assigned as a treatment number T1, T2, etc. to T2 raised to m, corresponding to the same standard sequence. Now, we can construct this by taking the block of different replication using some groups. These are the groups. By taking these groups, 1, 2, 3, 4, so for different values of I can construct a hypercubic designs. Let us take an example. Consider a hypercubic design D having parameters 16, that is 2 raised to 4, and B is equal to 32, K is equal to 2, R is equal to 4, lambda 1 is equal to 1, lambda 2 is equal to 0, lambda 3 is 0. Let us here one thing keep in mind, that the lambda will be as much as the M value. Here we have M value, so there will be 4 associates, lambda 1, lambda 2, lambda 3, and lambda 4. Whereas only first lambda, lambda 1 will be always 1, and remaining lambda will be 0. Here our reflection size R is equal to 4. So naturally, B is equal to 32. So B by R, that is 32 by 4 is equal to 8. So we have the 8 groups. So 8 replication size. And in each replication size, we have the 32 treatments. So for these examples, we consider the 4 blocks. So number of blocks will depend upon the replication size. So our 4 groups are Ti, Ti plus 1, Ti, Ti plus 2, Ti, Ti plus 4, and Ti, Ti plus 8. So you can find there is a sequence here also. And for different values of I, we can construct the designs. So let us take the first treatment, 16 treatment combinations. And this is denoted T1, T2, T3, T4, T5, etc., up to this 2 to 2 as a T16 treatment number. Now let us take the first group, Ti, Ti plus 1. It means one block contains 2 treatments. And I should have the different values of I. So our I here I have taken 1, 3, 5, 7, 9, 11, 13, 15. So there are 8 values of I, and there are one group block, the 2 treatments. So naturally there will be 16 treatments in this group. So there 8, if you take different value of I is equal to 1, so T1 and it is T3, so the first block will be this and this T3. If I take 3, the T3 and T4, the second block will contain this and this. This way, we can construct a first group of 16 treatments which are here. So 1, 2, 3, 4, 5, 6, 7, 8. So all the 16 treatments are here in 8 groups. This is for reflection number 1. Similarly, for the second group, we have the group Ti, Ti plus 2, but I is equal to 1, 2, 5, 6, 7, 9, 10, 13, and 14. So now one can ask me how you are selecting the I, because you have taken the different values of I. So this will depend upon the criteria by selecting the treatment in one block, that the position of the ith component, this is first, second, third, fourth component, first, second, third component, position of the ith component will be same for each block, 2 blocks. For example, here in this block, that it is a 1, 1, 1, 1, 1, 1, 2, 1, the only third place or third component is different. Otherwise, first component, second component, fourth component is same. So this shows lambda 1 is equal to 1. And other lambda, similarly you can say any group you can say. So here see 1, 1, 1, 2, 1, 1, 2. Only this is component is different. Anyone you can take. See, it is take here. So 2, 2. Here only third component is changed. Here is them. So in all the 8 group blocks, our component treatment should be selected in such a way for different value of I that the position of the component of 1 to 4 for 3 will be same, only any 4 will be different. This is the idea of selecting the I value for the construction of the design. Now let us take the third group. Third group was a Ti, Ti plus 4. Here again I is different. 1, 2, 3, 4, 9, 10, 11, 12. And for this group, our designs are this. You can check here also, any design, let us take this. So first position same, only second position different, but third, fourth position are same. So the lambda 1 is equal to 1. So this will be true for all the blocks. Now the last group we have taken as a Ti, Ti plus 8, and I is equal to 1, 2, 3, 4, 5, 7, 8. This is I have taken. And this we got the fourth group. So all the 4 group I got. So this is a complete hypercubic design with B is equal to 16 and block number of block 32. Here also you can see, take this, any group block we take. Here also see that the first position, the first component differ 1 and 2, but remaining position components are same. So this will be true for all the 4 groups of 32 treatments, that position of the component must be same for 1 and remaining should be, so 3, remaining should be different. So this way we got a hypercubic designs of 32 blocks in R with R replications. So this is, so it means if take any treatment 1 to 1, 1, it will be replicated 4 times in entire the design D. Now we'll go to for finding the regular graph design. So I have taken the binary designs because elements in 1 and 2. Now for finding the concurrence matrix, what we did, we converted 1 as a 1 and 2 as a 0. By using the concurrence matrix, we found this is the concurrence matrix of the hypercubic design with 16 rows and 16 columns. Now we can verify that each diagonal elements are same, that is 4. And again we check all the off diagonal elements are either 1 and 0, and difference between any 2 off diagonal elements of this design are at most 1. So 0 minus 0 is 0, 1 minus 0 is 1. So any you can take. So this shows that the diagonal elements of the hypercubic design is same as 4, and off diagonal elements of the design is differ at most 1. So design is a regular graph design. Now we shall come for the E-optimal regular graph design of the hypercubic design. So you have seen that all the off diagonal elements of concurrent matrix are same, and all the off diagonal elements of design are at most 1. So design D is a regular graph design. Further, the minimum eigenvalue of C matrix associated with the design D we calculated, and we found this value. And now using the criteria of max ZD1 is greater than maximum of A and B, we are finding the value of A and B. So A is equal to this much. So B raised to M 16 minus 2, R was 4, K minus 2 minus 1 minus 2, plus M was 4, 4 minus 2, K was 2, M was 2, 4, 16 minus 1. So if you solve this, I got as 1 upon 14. Similarly, B is equal to V raised to M R times K minus 1 minus 1 minus M minus 1 upon K raised to V minus 1 1. So if I put value of Vm 16 R 4 K is 2 minus 1, M is equal to 4 minus 1 upon K is equal to 2 Vm 16 minus 1. After solving, I got 3 by 2. Now we have the maximum of A by B. Naturally, you can see A is equal to 1 by 4, B is equal to 3 by 2. The maximum of A by B is equal to 3 by 2. So since A is equal to 1 by 14 and B is equal to 3 by 2, hence maximum of A by is equal to 3 by 2. Now using theorem 2.1, obviously ZD1, I found it. It is greater than maximum value of A and B. Therefore, D is an E-optimal regular graph design, hypercubic design. Further, we also verified that following hypercubic designs, which are E-optimal regular graph design, are also satisfying the criteria. But here we have kept one thing always in mind, that all the hypercubic designs, I have shown only up to M5, not more. It's all lambda 1 are 1. While in other work, previous work, we have taken a different value of lambda 1 also. So these are the hypercubic design. Up to 4 I can develop, but we can write so many other hypercubic design also, but they all are E-optimal regular graph design. Now let us have some application of hypercubic designs. Hypercubic design can be applied to construct the following designs. First, we are constructing the semi-regular graph design. A group, let us have the definition of group design. I will not explain because already Dr. Syam Saurabh has explained these parts. A GD is a partially balanced incomplete block design, which is an M arrangement of V is equal to Mn treatment in V blocks, such that each block contains K is less than V distinct treatments. Each treatment is repeated R times, and the treatment can be divided into M groups, each of N greater than 2 treatments, provided that any 2 treatments belonging to the same group are first associate, otherwise second associate. This was also true in the case of the hypercubic designs. For the usual instant matrix N of the GD designs, the continuous matrix Nn prime has non-zero eigenvalue R minus lambda 1, which we always call theta 1, say, and another is Rk minus V lambda 2, we call always theta 2, other than Rk, with multiplicities M times N minus 1 and M minus 1 respectively. If theta 1 is greater than 0 and theta 2 is equal to 0, the GD design is called the semi-regular group design. Here we will illustrate with some examples of hypercubic design through an example. Say an example, this actually I didn't explain in the construction because of time. I have taken V is equal to 3. So our treatment is 9, V is equal to 3 square, and M is 2, and V is equal to 6, K is equal to 3, and R is equal to 2, lambda 1, 0, lambda 2, 1. So I have it, R is equal to 2, so we have the 2 replication groups. Here I have made hypercubic design. You can see here, everywhere, in one place, the treatment is changed first component, 2, 2, 2, but second place treatment is different. Here also 3, 3, 3, but here is different. Similarly, in representation 2 also 1, 1, 1, but second component, it is different. First component same, second component different. First component same, second component different. So naturally it is a hypercubic design. Now we will decode this thing as a 1, 1, 1, 1, 2, 2, 1, 3, 3, 2, 1, 4, 2, 2, 5, 2, 3, 6, 3, 1, 7, 3, 2, 8, and 3, 3, 9. So we got the 9 treatment now. So After this, we add 3 more blocks. 1, 2, 3, 4, 5, 6, and 7, 8, 9 of the same block size with the blocks of the hypercubic design, this and this. So now we have the 6 plus 3, 9 blocks. So B is equal to 9 is equal to B also already 9, RK3, lambda 1, 0. You can verify lambda will be 0 because of the property of the hypercubic design. That it is differing at the first component, second component, and first component remains same. So lambda 1 is equal to 1 lambda is 1, other lambda is 0. Why I took lambda to 1? Because that first component is not differing. Not differing only in the second component. Now we will discuss the application of hypercubic design for the confounded factorial design and its identification of main facts and interaction effects. Suppose we have V is equal to 3:m symmetrical factorial design whose treatment combinations are denoted by exponent to xb, where xi is equal to 1 to v, then hypercubic design provides some confounding system for the factorial designs. Ghosh and Bagoi, we developed a very simple techniques to identify the confounded main fact and interaction effect in the case of symmetrical factorial design. And this technique is now extended here for the identification of the main fact and interaction effect confounded in the hypercubic designs. I will go to the examples. We have the first example, we have taken a hypercubic design D having parameters B T is equal to 16, that is B is equal to 2 and M is equal to 4. A block is 32 K2 R4 lambda 1, lambda 2 0, lambda 3 0, and lambda 4 0. The plan I have already explained you already. So we have now denoted in 4 replication: replication 1, replication 2, replication 3, and replication 4. Any replication you can see, only the ith component, they are different. Other remaining components, they are same. This is a hypercubic design. Now, I will take one by one replications. And after taking one by one replications, we will convert this 1 as a 1 and 2 as a 0 and write down these replications into the blocks within the replications. Because confounding, we know it is confounded into the blocks. That is to reduce the block sizes. To construct the confounded design and identify main fact and interaction effect, the blocks of design are rearranged as follows. The first element of all the blocks in one replication are taken together and consider them as the first block of the confounded factorial design. Similarly, the second element of all the blocks in the same replication are taken together and considered them as the second block of the confounded factorial design. Now, for the convenience, we replace the symbol 1 and 2 by 0 and 1 respectively, which gives the resulting design of the replication 1 here. So what I took, in replication 1, all the first element, there are 8 first elements, we took in one block by converting 1, 0 and 2 as 1. Similarly, the second element of first 8 element of the second replication considered in one block. And this is written in this block 2. Now I have 2 blocks in one replication. So this is a confounded design. So this is a layout of 2⁴ factorial design confounded into 2 blocks. Each of block has size 8. Now we discuss the identification of the confounded main fact or interaction fact, which is confounded here using the Ghosh and Bagoi techniques. Let us consider block 1. So we call block 1 as a principal block group because in principal block group, there is a one treatment combination which is a control treatment, that is level of all the treatment are at 0. All the factors, sorry, are 0. So we will call such block as a principal block. And the other block where this is not true, we'll call the non-principal block group. So block 1 is a principal block group, block 2 is a non-principal block group. Next, we search the treatment combination that contain a single higher level 1 from the non-principal block group and combine this treatment combination multiplicatively with reduced mod 2, because our level of the factor is 2, to identify the confounded main effect and interaction effect. Let us take the non-principal group. The highest one letter is only this 001. All other treatment combinations are more than 1. So I have to select this. So this is a factor B, C, and this is level of factor D. So here it means in this D is confounded. So this is an experiment where it is completely confounded. A factor D is confounded.
So please conclude in 2 minutes.
Okay.
You have taken 35 minutes.
Okay. I'll conclude. So this way we have the 4 replication, 1, 2, 3, 4. We can see D, C, B, A in all groups are confounded. So since C, B, A and D are confounded in the replication 1, 2, 3, 4, so this concludes that all the main facts are confounded a same number of time. So the resulting same number of time of main facts. So the resulting design is a balanced confounding experiment. Since there is no time, so like that we can go for the partial confounding also. We have, this is another experiment with the same hypercubic design, but I have considered into the 4 blocks instead of 1 block. So 4. So first 4 elements in the first block, second 4 elements of the reproduction 1 in the second block. Similarly, we'll take. So now it is a 2-4 factorial experiment confounding into the block size of 4. And here we use the same as Ghosh and Bagay method of confounding to identify. We found that design D is a partially confounded factorial design with 4 blocks per replication confounded into a blocks of size 4, and different main facts and interaction are confounded in different replications. If the order of the blocks are changed in each replication of the hypercubic design, the confounded main fact and interaction will have the change. However, the total number of confounded main facts and interaction will remain the same. So now I am just skipping all these examples. That was the confounding experiment for 2 raised to n. Now this is a confounding experiment of 3 raised to n, taking the hypercubic design with b is equal to 3. This will give the confounding, partial confounding, and balanced confounding with factor with level 3. This all I am skipping. So this is the conclusion I'll just explain. In this investigation, we can conclude that the confounding is either complete or partial or balanced, depending upon the way the blocks of the confounding designs are formed. Another property of the hypercubic design used as a confounding design for a symmetrical factorial design is that the complete balance is achieved over each of the main fact in any other order of the interaction effect. That is, all the normalized treatments, contrast belonging to the same main effects or interaction effect are estimated with the same variance due to the fact that a hypercubic design is also a balanced factorial experiment. Cheng 89 has obtained partial and balanced confounding design from hypercubic design, while in this article we have obtained the complete, partial and balanced factorial design. So this is how it differs with the Cheng's work. This is the references. I have taken 100% problem from this paper. Then these are our paper with the Thanipara et al., where we have developed the hypercubic design with lambda 1 not less than 1 but other than lambda. But in this article we have defined 1 lambda as U1. Thank you.
Okay, let us thank Professor Ghosh for a nice elaborate speech. So now let us have some quick questions or discussions. So if not, I would like to thank again the Professor Ghosh for organizing this session as well as giving a talk in this webinar, and also the other speakers, Professor Poonam Singh and Dr. Shyam Saurabh, for their nice presentations. At this time, I would like to thank the organizers for giving me this opportunity, particularly Professor Satish Kumar. Thank you, sir. Thank you very much. So with this, this session comes to an end.
Thank you, Professor Pandit, for chairing the session in a very nice way. And we are very much thankful to you, Professor Ghosh. Please, you can, can you hear Professor Ghosh for organizing a very informative session, utilizing potential speakers like Poonam Singh, Professor Poonam Singh and Shyam Saurabh. We are very much grateful to you, Professor Ghosh, for your support to our activities through these types of academic, soundful academic deliberations. Very active. Even you are in the US now, you have taken much pain to or much efforts to organize session with and join with us. We are very much grateful to you, Professor. Thank you so much. Thank you. And also, we once again thanking you, Professor Pandit, for your support as a chair. Now we have 10 minutes remains for more than for the next session. There is a small break we can take, or otherwise we can discuss anything. No problem, Professor.
I'm thankful to Professor Satish Kumar because he considered my request to organize the symposium such a way that in the USA it should in the morning. So now we have the morning 6 o'clock, and otherwise it would be difficult for me to present my paper. Thanks for considering my request.
Yeah, in fact, I doubt whether this time, whether it is while organizing a session, this much time is taken, and that is why I have placed another person as chair. Otherwise, you have to chair also. Anyway, thank you, professors. Thank you, Professor Pandit and Professor Ghosh. Thanks a lot. And thank you, Shyam Saurabh, and thank you, Poonam Singh. For your support to our. Very, I think next session, Professor
Jaya ma'am joined, sir. Elia ma'am is also joined.
Okay, all are there. Okay.
Jaya ma'am, good evening, Jaya ma'am.
Hi.
Hello, good evening, good morning.
How is things there in
Very good, very good. it's summer, and so we have our summer
Last
session.
time you are some other trips.
Yes,
December,
I was in December. I was traveling. Yes, I
Yeah.
was unable to join the December conference. I hope you had a very good conference as usual.
How was your challenging trip that time?
It was nice. It was nice. We went to the Sahara in Algeria, in southern Algeria. It was, we were a group of 27 friends.
Oh,
we traveled together. So it was a very good experience. And it was very nice to be in a very different form of nature.
Yeah. You mentioned there is no network issue and other things there. Okay.
Yes.
And so how many days you were there?
We were there for about 8 days. Yeah, 8 days.
Okay. So full more than a week time. Okay.
Yes, it's very nice. You feel very humble in front of nature, that essentially you are at the mercy of nature.
Okay.
It's a very humbling experience.
Yeah. While in the busy academic, in between you have to find time to
yes,
enjoy nature.
yes.
Yeah. Right.
We must. Otherwise, we need some. Our mind needs to refresh.
Yeah. How is the professors there? Rutgers, everyone are okay there. In fact.
Okay, this is the summer session, and summer is when a lot of our research happens.
Okay.
So there are some classes people teach, but fewer than the other semesters, and this is when we are required to catch up with our research. It's very important, and that's how we are.
Okay.
That's the time we must demonstrate productivity. Yeah.
Okay. Great.
So everybody is very busy with their research programs. Yeah.
Do you have any idea about our George?
Oh, Dr. Varghese George. Yeah, he's fine.
Varghese.
Yeah, I think he has retired from his as a department chair.
Yeah.
And I guess he is experiencing a good retirement life, I hope. I have not communicated with him after he retired, but I am confident he is doing fine. Yeah.
Okay. Whether he is there in the US or in India?
I have no idea. Yeah.
Okay.
I hope this conference is going well so far.
Yeah, going well.
Program is great.
Yeah, going well. Yeah. Tomorrow, the morning session starts with Professor Barry.
Oh, great. Wonderful.
Now we have the biostatistics people. Starting
yes.
Immediately after design of experiments, we shifted to biostatistics.
That's wonderful. Yeah. So that's great. So it will be a nice. I saw that you have very nicely themed sessions. That's a wonderful program you have put together. As usual, you have done a great job.
Everything, in fact, because of you people, process. Yeah, madam. And Shubha also informed me about her trip to there.
Yes. So let me just open my.
Yeah. You can check now by your slides. Yeah. Check.
Eliama teacher, good evening. Teacher.
Good evening, Eliama teacher. Teacher, you are muted. Please unmute your mic.
Good evening.
Good evening, madam. Good evening.
Good evening. So, am I late?
No.
No, teacher.
The right time.
Oh, okay.
Fine.
Because I came just half an hour ago from the office.
Okay. Now also you are in the office?
No.
Not.
Came back at
You
home.
mentioned about some busy schedule today and day after tomorrow. Daytime. There's some interview, some selection, something.
All right.
Yeah.
Today, tomorrow, and the day after tomorrow. All the 3 days are.
3 days are busy with
Busy. Yeah. Day after tomorrow, this PhD research scholar selection.
Okay.
PhD.
Yeah.
Hi, Dr. Jayas. Hi, nice to meet you.
Nice to meet you. Yeah, once again.
Once again.
Yes.
I think long time ago we met in Karyavatam.
Yes, in the ICSTC conference.
Correct.
Yes,
I remember.
very nice to see you again. How are you?
Doing good. Very busy
Wonderful.
program.
Wonderful.
Yeah.
Yes, I also had the joy of meeting some of the people from your team, Dr. Krishna, Dr. Preeti, and many more people. I hope, please give them my regards.
Sure. Yesterday, Preeti was, her presentation was yesterday, and today
Okay.
Jagat had already done his presentation.
Wonderful. Yeah, they're all doing great work. It was a pleasure to meet them and learn about their works when I met them.
Once he mentioned about your discussion regarding this collaborative research programs, something like that. I remember long time ago.
Long time ago. Yes. Yes.
So what time we should start? We are right time, no?
We are right time. We have to start at 18:55. Yeah.
Okay.
Yeah.
What is time there in New Jersey?
Now it is.
It is morning 9:21.
Okay. You are in the office or?
Yes, I'm in my office. Yes, we all come to our office these days. Yes.
New Jersey is just like a mini India, isn't it?
Yes, it is. Yes, mini Gujarat, more specifically. It's nice. It's a nice state. Yeah.
നയൻ ഭട്ടാചാര്യക്ക് ഒരു താങ്ക്സ് വിളിച്ച് പറഞ്ഞേക്കണം. കാരണം നമ്മൾ ഇതിൻ്റെ ഇടയ്ക്ക് ഇത് ചെയ്യാൻ പറ്റും. അതൊക്കെ ഇതൊക്കെ അറേഞ്ച് ചെയ്യാനായിട്ട് മറ്റവരൊക്കെ കയറി ഇത് ചെയ്യാൻ പറ്റും. ഇതിനകത്ത് തന്നെ ഇപ്പോൾ ആൾ കുറഞ്ഞു എന്ത് പോയി കിടക്കാൻ പിള്ളേർ അത് വലിയ ഇതായിട്ടുള്ള രീതിയിലാണോ ഇവരെല്ലാം. അതുപോലെ നമ്മളെ കോൺട്രിബ്യൂട്ടറി സ്പീക്കേഴ്സിന് എല്ലാവരും ഇത് കൊടുക്കുന്നത് സൂക്ഷിച്ചു തരണം. അപ്പോൾ നമ്മൾ ചെറിയ ഇതിട്ട് കൊടുത്താൽ മതി. 20%, 10% നമുക്ക് കൊടുത്താൽ മതി. Nayana?
Yes, sir.
Nayana, okay. Now we are 6:54. Now let us start the session through introducing the chair. Please, Nayana, introduce the chair.
Okay, sir.
And help the chair to run the session in a very
Hello, everyone. We are moving on to the technical session 21 of WSTA 2024, which is a plenary session that shall be chaired by Eliama Matthew. Dr. Eliama Matthew is the professor to the Department of Epidemiology and Biostatistics, Regional Cancer Center, Trivandrum. She is the recipient of 2022 Cancer Foundation Finland Prize of 5,000 euros. She has been served as a country representative for Asia Pacific Organization of Cancer Prevention. She is a recipient of several national and international fellowships. We are really lucky to have you, ma'am, for chairing the session today. So with great joy and honor, I cordially invite you, ma'am, to chair the session. Over to you, ma'am.
Thank you. At the outset, I thank the Professor Satish Kumar for giving me an opportunity to chair this session. In fact, I am really proud of chairing this session, the lecture taken by Jaya M. Satagoban. She is a professor in the Department of Biostatistics, Epidemiology, and Associate Dean for Faculty Affairs at Rutgers School of Public Health, Piscataway, New Jersey. She is a full member Cancer Prevention and Control Program at Rutgers Cancer Institute, New Jersey. Her research is in statistical and computational methods for studying the distribution and determinants of cancer risk and outcome. At Rutgers, she established and served as the inaugural director of the Center for South Asian Quantitative Health and Education. She is a fellow of the American Statistical Association. With this brief introduction, I invite Dr. Jaya Satagoban for the talk on sparse canonical correlation to identify breast cancer-related genes related by copy number aberrations. Dr. Jaya, please.
Thank you, Dr. Matthew. It's truly an honor to be in a session chaired by you. I'm very grateful. And I also want to give a big congratulations to Dr. Satish Kumar and his team for putting together yet another wonderful conference and a great program. I know how difficult it is to organize a conference. It takes a lot of energy and time and coordination, and Dr. Satish Kumar has done it once again, and this is a great opportunity for everybody, all of us, to come together and share our works and learn from each other and positively move forward. So I am happy to share my screen. Shall I? Are you able to see my screen?
Yeah, it is okay.
Yes.
It's fine. It's fine. Yeah.
Thank you very much. Yeah. So as Dr. Matthew introduced, I'm going to talk about a recent work that I did with some colleagues on identifying breast cancer genes using sparse canonical correlation analysis. And there is a QR code here. These days, many people have cell phones. So I put a QR code here because this will take you to the paper that we wrote, and this talk is based on that paper. So anyone that is interested is welcome to use this QR code. I will have the QR code again as well. So once again, the QR code is here. This is a joint work with two colleagues, Dr. Deeptavo Datta from the National Cancer Institute in Bethesda, Washington, D.C. area, and Dr. Anando Sen, who is a biostatistician in the University of Michigan. So this has been a wonderful collaboration, and we are looking forward to many more productive interactions. So this talk is about a statistical approach, but it focuses on application in breast cancer, but it can be applied to any cancer or any chronic condition. And I will focus on breast cancer. So breast cancer, the tumor itself exhibits a wide variety of characteristics at the genomic level. So what are some of these characteristics? Of course, we know breast cancers have different subtypes and stage and so on. And also there can be certain inherited mutations present in certain breast cancers, not necessarily all. But some of the genomic characteristics that are present in breast cancers or breast tumors include somatic mutations or somatic changes. These are mutations or changes in the DNA, but they are not inherited. That is, we do not inherit from our parents. These are changes that happen suddenly. And that's why these are called non-heritable changes. And why do they occur? They occur due to certain incorrect or errors that happen when our DNA replicates, or due to some other stress. For example, the stress can be exposure to certain environmental conditions, or it can be exposure to our own body's different characteristics, certain excess of certain estrogen, or certain processes that happen in our body due to being obese, or due to different being not very active, or perhaps I carry some mutation that I inherited from my parents, and that could cause some stress, and that could lead to somatic mutations and so on. So the somatic mutations themselves are not inherited, but they are changes. And very importantly, copy number aberrations. These are structural changes to the chromosome. So we all know we have 23 pairs of chromosome, every 22 pairs, and a pair of sex chromosomes. Women have 2X and men have 1X and 1Y. But chromosomes come in pairs. But what happens in some cancers is certain chunks of chromosome may be missing. Maybe one of them is missing, or sometimes the chromosomes can also have replications, 2 or 3 copies of them. So these are known as chromosomal copy number gains or losses. And these gains or losses can happen, and they may lead to the onset of cancer, or if it happens in a person with cancer, or if it is present in a person with cancer, it can impact the progression of the disease or the severity of the disease. And these copy number aberrations, the gains and losses, they may harbor very important genes that may be responsible for cancer initiation and progression, known as oncogenes or tumor suppressant genes and so on. And they may also have the potential to regulate cellular pathways. So what is cancer? Like uncontrolled cell division is what is cancer. And this can, when the cell division can travel to other parts of the body and replicate there, that's cancer. And the nice process is when we can control the cell division and prevent that cell from dividing, bad cells from dividing. But when that cannot happen, that leads to cancer. And these oncogenes and tumor suppressor genes have the potential to regulate all these aspects. But when that cannot happen, that leads to cancer or to cancer progression for someone, disease progression for someone that has cancer. And these changes, somatic changes, or especially copy number losses and gains, they also have the ability to regulate the expression of the gene. What does it mean? So we have DNA that leads to RNA, protein, and then our functioning of the body. So things that happen at the DNA level can impact what happens at the RNA level, that are measured in the form of RNA level gene expressions, among other things. So any changes that happen at the DNA can have an implication for the RNA and subsequently for the outcome of the individual. And why is it important to study these genomics in breast cancer, or for that matter, any disease, other cancers, cardiovascular disease, diabetes, and so on? Studying the genomics have known to help with treatment. So let's see a few examples here. So, for example, estrogen receptor positive cancer, for luminal A or luminal B subtype of breast cancers, they have certain types of expression, and these expressions lead to certain therapies. So if a person with ER positive breast cancer has a certain types of expression of some of their estradiol receptor expression, then that woman or that person can be treated with anti-estradiol therapy. I cannot say women because men can also get breast cancer, although it's very rare. So breast cancer, a breast tumor that is HER2 positive will have HER2 overexpression, and these tumors can be treated with anti-HER2 therapy. And similarly, let's look at triple negative breast cancers. These are very, very difficult to treat. But some of them, if for example, if we have some cancer that are basal-like cancers that have EGFR expression or ADN repair pathways, and there are ways to treat these cancers. So there is a very nice paper by Hamdan et al. And this paper lays out some of the progress that we have made in the treatment of breast cancer by studying different types of genomic characteristics of breast cancer. So that's why it's very important to keep looking and keep studying the genomic characteristics of tumors so that we can continue to make progress in identifying good treatments for the disease. Because not any two breast cancers can be very, very different. So a treatment given to one woman need not be applicable for another woman because their genomic characteristics are different, or for two men as well. So in the context of this background, we propose a following approach, an analysis pipeline with the following hypothesis. Our hypothesis is that copy number aberrations, CNA for short, they regulate gene expressions, and ultimately these gene expressions impact disease outcome. So when copy number aberrations impact gene expressions, they impact gene expressions that relate to certain biological processes that are important for the disease. So our analysis pipeline is as follows. We have typically a large number of information about copy number aberrations in each breast cancer. And similarly, we have a large number of gene expressions measured in each breast cancer. So our goal is to identify the gene expressions that are regulated by copy number aberrations, that is, that are affected by, impacted by, associated with, correlated with in statistical terms. And how are we going to identify this? We are going to use sparse canonical correlation analysis. Why canonical correlation analysis? Because it's not a single copy number and a single gene expression. Several thousands of copy numbers are measured in several thousands of gene expressions are measured. So we have to come up with a way to correlate this very large amount of data, and a canonical correlation analysis is a useful approach for doing that. And why sparse? Because there's a very large number of CNAs and gene expressions. So we have to impose some sparsity to select the few that are deemed important. So we will impose some sparsity to correlate these two large amounts of data. And once we have identify the gene expressions, our next stage in the hypothesis is it is these gene expressions that are impacting the outcome. So copy number information at each location on the chromosome, we have copy number. Is the copy number the same? That is 2 copies of the chromosome available. That means there is no aberration. Then the value will be recorded as 0. If there is, instead of a pair, there is one of them is lost, one arm is lost, or they are lost, then we will have it recorded as -1. That is a copy number loss. And if there is a copy number gain, that is if there is 2, 3, 3, 4, and so on, when the chromosome must occur in pairs, but if we have 3, 4, and so on, so we will have additional numbers representing copy number gains. And what is gene expression data? It is at every gene, we have some RNA level information, and that information is recorded as a continuous variable typically. And there is a lot of literature available out there for anyone interested on how to interpret these numbers, how these numbers are obtained, what is the pipeline to arrive at those numbers, and so on. I will not go into those details. But for the purpose of this talk, it is sufficient to note that these are continuous variables. And outcomes in the breast cancer setting, there are numerous outcomes we want to study. One is a binary outcome, where is the person having ER positive or ER negative cancer, PR positive or PR negative cancer, and so on. Some continuous outcome may be there, or maybe we will have time to event, survival, for example, and so on. So to go from the identified gene expression module and their relationship to outcome, we can use a generalized linear model or a Cox proportional hazard model, and so on. And then we can use, once we identify these are the gene expressions, let's say 3 gene expressions that are associated with whatever outcome I'm interested in. How do you know that these are really good genes, these are relevant genes? There are several bioinformatics tools available, and we can identify what is the role of these genes. Why is this gene associated with my outcome? So all of these are feasible, and I will walk through an example about this. Are there any questions at this time? Okay, so let me move on.
You can complete and then we can have discussion.
Okay, thank you, Dr. Matthew. Yeah. So to demonstrate this pipeline and the methodology, we use data from what is known as the Metabrick breast cancer study. These data are available to anyone that is interested. These are freely available data. And I welcome you to go to this website shown in the bottom of the slide on the left-hand side, www.cbioportal.org, and there is a dataset tab. There are numerous datasets available for anyone interested in pursuing statistical methodology research and their applications. And this is available, there are 2 publications given here that describe this data set, and they have conducted various investigations of these data. And what are these data? There are 1,904 breast cancer cases, all female. And these are, copy number ablations are measured in 22,544 sites in each breast cancer case. So we can think of this data as 1,900 rows and 22,544 columns. And this is the DNA level data. And for the RNA level information for each breast cancer case, 24,360 data points are measured. And these are all measured using the primary breast cancer tissues. These are all non-Hispanic white women. That is, these are all Caucasian women. And these tissues are obtained from tumor banks in the United Kingdom and Canada. And in addition to this, outcome is measured in different women, different clinical data are measured, and so on. So what do our data look like? This figure on the top left illustrates what we have. So think of each woman's data as like a row. I show you here as a square, but we can think of it as a row or as a column. And each woman's data is obtained from some array, which is a plate. That's why I show a plate here. For each woman, 22,544 data points. And we have 1,904 cases. Similarly, gene expression, a lot of gene expression, once again for 1,904 cases. And the outcomes measured are ER status is binary, positive or negative. 76.6% are positive for ER, estrogen receptor status. Once again, progesterone receptor status, it is also a binary value, positive or negative. About 53% are positive. HER2 status, about 12% are positive. And grade, we also made it binary. And lymph node, is there lymph node present or absent? That's a marker of how far the disease has gone. And age at diagnosis of breast cancer is also made binary. Age 50 is deemed approximately age at menopause. So what happens before menopause and after menopause? Crudely, because age at menopause can be different for different women, but approximately average age is 50 is what our assumption is. And we also have data on overall survival, and the median survival time here is 154.2 months, which is, you can convert it into years. So ultimately, we have a data set shown in the table below. Each row is a person, 1,904 people, and each column is a data point, so is a variable. So 22,544 copy numbers, 24,000 and so on gene expressions. And there may be some covariates measured in these women, body mass index, and so on. And then outcomes, the Y variables. There are many, many Y variables. So now, in this analysis pipeline, our first goal is to identify which copy number aberrations are related to gene expressions, because this is a biological process where changes in the copy numbers impact the functioning of the RNA, and that ultimately impacts disease. So the first analysis pipeline is to use a sparse canonical correlation analysis to extract the key relationship here. And how do we do this sparse canonical correlation analysis? So let's say G is a matrix of the copy numbers normalized so that everybody's copy number is mean 0, standard error 1 or standard deviation 1. And E is once again a normalized matrix of gene expressions. These normalizations are all done in the analysis pipeline for extracting these data, and we get the normalized information. We don't have to do any normalization. So it is an N by G matrix and an N by E matrix of expressions. So what is canonical correlation? The canonical correlation, as we know, is we are maximizing the linear relationship of E with a linear value of G, maximization with respect to the vectors U and V. This is our standard canonical correlation. But here we impose sparsity because not all the gene copy numbers are going to be impacting all the gene expressions. Certain select number of copy numbers will be affecting, as associated with or correlated with a select number of gene expressions. So we have to impose 0 values for some of these U's and 0 values for some of the V's. And that's how we impose the sparsity here. And further details about this maximization is provided by Witten and colleagues. But we adapted that to our approach in a particular way, where what we can do is we can maximize this with respect to U and V and extract that U and V. So it will say which U's are non-zero and which V's are non-zero. We know those copy numbers are related to those gene expressions. So that's our first set of canonical correlations. Now we must get the second set of canonical correlations. We can get many number of canonical correlation. Maximum number of canonical correlation is minimum of G and E. Right? So we have to deflate the G transpose E, this correlation matrix, to account for the fact that we have already extracted one canonical correlation. And we use a Hotelling's deflation approach, and then we extract the second canonical correlation. And once again, we have to deflate the G transpose E, the correlation, according to the Hotelling's deflation, to account for the fact that we have extracted the first and the second canonical correlation, and we have to continue this until certain stopping rule is achieved. Okay? And I will not go through the stopping rule. I invite you to look at the paper where we provide all the details. So using this procedure, we have extracted a total of 14 canonical correlations, right? So there are 22,000 odd copy number aberrations, 22,000 odd gene expressions. Together with this imposing sparsity, we extracted 14 canonical correlations. And this figure shows these, illustrates these canonical correlations, and it must be interpreted as follows. So each line, horizontal line, is a chromosome. So we have chromosome 1, which is the longest chromosome, chromosome number 2, 22 and so on up to chromosome number 22. And we have the X chromosome because these 1,904 individuals are all females. So they will have only 2 X chromosomes. And each chromosome occurs in pairs. That's why there are 2 in horizontal lines, and certain key aspects of the chromosomes are illustrated here. And the red point in each chromosome is a centromere, kind of the center-ish part of the chromosome. So as you can see, there are some colored lines on top of each chromosome. So these represent our canonical correlation. On chromosome 5, we have a long orange line. This is the first canonical correlation component that we extracted. So the U values were non-zero for a consecutive set of values on chromosome 5, and the U values were 0 for the rest of chromosome 5 and for all the other chromosomes. So this is a contiguous portion in chromosome 5 that we have extracted first. And the second canonical correlation similarly is another component. Let's think about, let's say, chromosome 3 or chromosome 8 and so on. The next, after we imposed Hotelling's deflation, we extracted the second canonical correlation. The U's were non-zero for these continuous set of values in chromosome 3, and the U's were 0 for all the remaining chromosome 3 and all the other chromosomes, and so on and so forth. We have obtained 14 such contiguous values until we stop the procedure. And each of these contiguous values are correlated with certain gene expressions. And what are those? And that is described here. So we have 14 canonical correlations. The first canonical correlation was extracted from chromosome number 5. There were 139 contiguous values. And in chromosomal language, it is in this region, we call it. And these 139 copy number aberrations at the DNA level were correlated with 70 genes at the gene expression level, 70 E values. Of these 70 E values, 18 were genes that are from the same chromosome, but distal, like further away from this region. And 24 of them are from totally different chromosomes. So these 139 copy number DNA values can impact RNA changes occurring in different chromosomes. And the remaining, I think this is 42, remaining 28 are, these remaining 28 are impacting genes occurring in the same region, in this chromosomal region. And in this manner, we can interpret each and every canonical correlation that we have identified. For example, canonical correlation value 8 is identified in chromosome number 8. There are 125 canonical values there, chromosomal aberrations there. In this chromosomal language region, they impact 59 gene expressions of 59 genes, of which 24 are distal to the same chromosome. They are not affecting the expression of genes occurring in entirely other chromosomes. They are only mattering for genes, expression of genes occurring in the same chromosome, and so on. So once we have identified these genes, now we want to relate these genes. The hypothesis is that these genes are the ones that impact the outcome. So now we are going to use generalized linear models to extract this. So, of course, we all know how our generalized linear models, some function of the mean is a function of the expression of the selected genes. And so we will use, if it's a binary value for let's say, estrogen receptor positive versus negative, we can fit a logistic regression model relating the estrogen receptor status, positive, negative, to, let's say, the 70 genes occurring in chromosome 1 or 59 genes occurring in, 70 genes corresponding to the first canonical component, 59 genes corresponding to the second canonical component. They can all be from different chromosomes, and so on. Right? And we know to get the p-value, the effect estimates from a logistic regression, the corresponding p-value, and there is going to be multiple comparisons. We are testing a large number of RNA level expressions. Even though we started with 22,000 and we reduced it considerably, still it's not only 1 or 2 RNA level expressions. There's like a few hundreds that we are testing. So we have to account for multiple comparison, and we do that by calculating the false discovery rate. So we have done this exercise, and we do find that we have very useful results. For example, the first canonical correlation occurs in chromosome number 5. So this is values occurring in chromosome number 5. There are several hundreds of values. So one of them, let's take one of them. It takes value -1, 0, 1, or 2, this particular chromosomal aberration. And the gene expression, if this impacts RNA level expression, and that RNA level expression affects estrogen receptor status. So for women who have females with negative estrogen receptor status, this is the gene expression. As this is the expression of women who are estrogen receptor negative and have a normal copy number aberration. That is 2 chromosomes, a pair of chromosomes there. For women who have a loss, the expression reduces. And for women who have a gain, expression goes up slightly, or maybe it's similar. On the other hand, for women who are estrogen receptor positive, some of them have a normal copy number, some of them have a loss, so their expression is reduced. Some of them have a gain of 1 copy number, which is what happened in estrogen receptor negative patients. But in the estrogen receptor positive cases, some women also have 2 copy number gains, and their expression level is considerably bigger than those who are estrogen receptor negative. And similarly, another copy number aberration, how we interpret this. And we also found very important genes, SQ2 and DNAL1. So the expressions of those genes are shown here. Then we identified which genes these gene expressions are correspond to. And I also mentioned earlier that there are bioinformatics tools. So let's say chromosome number, the copy numbers in chromosome number 5 are affecting 70 genes, and these genes are sitting in various different chromosomes. But what are those genes doing? Why are those genes important? Bioinformatics tools can allow us to understand that. And there are some very important bioinformatics tools for those who are using the R programming language. There is something called GoShiny, GoShiny. GO is gene ontology and shiny. GoShiny is a very important tool, and you can get pictures like that. So these are the genes, the 70 genes correspond to very important pathways, and these are all pathways written on the left-hand side of the figure. How do we know these are important pathways? We have to now communicate with an oncologist and get their input. And the oncologist that we communicated with also educated us on that these are these correspond to DNA repair ability of the gene, and they are also enriched for certain oncogenes known as MYC and so on. So at this point, the statistician engages with the oncologist to learn about the importance of these genes. And then since we have analyzed different outcomes, we analyzed the relationship between the gene expressions and the ER status, gene expressions and PR status, gene expressions and HER2, and so on. So we conducted a meta-analysis to examine, are there genes that are associated with all the outcomes or with certain outcomes and so on. And we performed so that will be for each gene, we have multiple different outcomes, and we have p-values correspond to all those outcomes. So there is another multiple comparison issue, and we have to conduct certain tests to meta-analyze this data, which is known as the Cauchy combination test, for getting overall p-value across the different outcomes. So we conducted a Cauchy combination test. I invite you to read this paper by Pillai and Meng that appeared in the Annals of Statistics. Very elegantly describes if you have a p-value for a particular gene or a particular x variable, but for many y variables, how to consolidate their p-values to understand, is this x variable associated across all those y variables? And we found that certain, so 182 genes, so 39 genes do not have strong association for any single outcome. And 182 genes are found to be significant or relevant for across multiple outcomes with a false discovery rate of less than 0.05. And some of these genes are based on the bioinformatics tool that we used and conversations with our with oncologist experts. Some of these genes are targets for BRCA1. So BRCA1 mutation is important for breast cancer, and BRCA1 mutation leads to certain abnormalities, and so on and so forth. We learned a whole different importance of these genes and how they might impact outcome. So in conclusion, I want to share with you that the analysis approach that we have provided, or the analysis pipeline, suggests certain interpretable associations. What is the role of certain components of RNA and how they are DNA, that is copy number aberration, how they impact certain useful gene expressions, and how they impact outcome. And these are all ways in which statisticians look for independent regulatory structures or biological processes or interpretable biological processes that relate DNA level information measured as copy number aberrations and gene expressions. And instead of a typical analysis, will say, okay, let's take each copy number aberration associated with outcome, each gene and expression and associate with outcome. That is 22,000 copy number aberrations and 22,000 genes that are associated with outcome. But instead, our analysis pipeline allows us to associate more interpretable gene modules, components, instead of focusing on each of those 22,000 associations. And it can be a very useful umbrella approach. There are 2 steps in the process. First, we look at a canonical correlation analysis, and then we extract useful gene expressions and look at the outcome. So these two, the changes that can be made to the methodology in each of those 2 approaches are separate. So we can use this umbrella approach as 2 separate approaches as well, 2 separate steps, and make modifications individually to those steps. But this is only one way of looking at it. There are numerous open problems. Why is only DNA impacted with RNA? These days we have epigenetics, microbiomes, where do they fit into the picture? And many more open problems are also feasible, right? So I will wrap up with that, and I will open for any questions you may have. Thank you very much.
Okay, thank you very much for the excellent talk. Any question from the audience and the participants? Any question? Yes, please. You are not audible. Not audible.
Professor, you have to unmute your mic.
Professor Rajagopal from Indian Statistical Institute.
Hello.
Wonderful, Dr. Jaya, on the clarity of your presentation. Only one clarification I ask about that minus log 10 p-adjusted value. Is it something? Is it something like Taguchi's optimization model?
No. So this is negative log. Let's think of.
That's a nice ratio we do.
No, it is negative log. The adjustment is not Taguchi adjustment. It is more of it's a much more simpler adjustment, like a family-wise error rate type of an adjustment.
Okay. Because it was minus 10 log, the signal noise.
Yeah, so because the p-values can be very tiny to
okay.
They can be 0.000001. So
Okay.
negative log transforms it to a more visually easier way.
That is the idea. Okay. Same thing with the Taguchi's minus 10 log signal noise ratio.
Yes. And here it's only used for visual, ease of visual things.
My second question, I had some interaction with Banaras Hindu University, Human Genetics Department. They are talking two things. On the given genes, how it is related, or the space of genes, how it is related. This is restricted to space, or it is restricted to given type of genes?
This is very restricted to given. Yeah, I'm glad you brought that up. So this is not a spatial assessment of genes. This is much more of a given. It's a more cross-sectional of each gene we look at without taking into account the spatial organization of the genes.
Great. This is now the new advent is happening in India in the medical research on genes investigations. And we are looking to associate with you how we can go ahead with some of the studies in nephrology.
Sounds good. Happy to hear from you. Thank you.
Thank you, Dr.
Thank you, sir.
Thank you, Dr.
I have a few questions. Like you have 1,900 something breast cancer cases and 22,500 something DNA values and another 23,000 for RNA values of each patient.
Yes.
Isn't it? So
yes.
This and you are assuming linear relationship.
Yes, absolutely. It's a linear correlation between the gene expressions and the copy number aberrations. So it need not be a linear correlation. So there can be much more sophisticated correlation, like the spatial correlation, for example.
Yeah.
And we are not considering that.
Correct. So in fact, now we can this machine learning algorithms. So in many algorithms which do not assume such a linear combination. So is it possible to do this because algorithms are there for classification to identify this gene expression, and can we use machine learning algorithms in this type of analysis?
I'm sure one can be creative in applying those methodologies.
In machine learning techniques, this kind of basic assumptions, we are not checking whether these variables are linear or not, because it can be, because biologically it can be other relationship also, need not be linear relationship, isn't it?
Yes, absolutely. So the linear relationship essentially allows us to get the low-hanging fruits. Right? And then once you get the low-hanging fruits, then people start looking for networks, for example. Though when starting to look for networks or tree-like relationship between genes, that's where machine learning can be very, very useful.
Well, another thing, you have shown a table like ER status 72, PR status another 54%, something like that, and grade 3 versus. So what does it mean that ER positive or ER status?
Yeah. No, ER positive. So 76% of the women of the data, 1,000 of the 1,904 women, 76% of them have ER status positive. So maybe I should clarify that. Yeah.
That table in two places it is mentioned. So the grade also, in fact, greater than or usually grade is 1, 2, 3. Well, yes. Moderate and poorly differentiated. So greater than or equal to 3. What is that? 3?
Yeah, there is grade is 1, 2, 3, 4. So grade 3 and 4 are one group, and grade 1 and 2 are another group. And the higher level is what I am providing the percentage for. So 47.5% are grade 3 or 4.
In fact, 4 classification, this is all international classification. So grade 4 is.
We do have grade 4 we do. It's a classification into 4 grades for these data.
Oh, okay. Anyway, that's not a major issue. Grade 4.
And lymph nodes is whether it's present or absent. And HER2 status also, it is for positive HER2 status, and also for PR progesterone receptor, it's also for positive progesterone status. And age at diagnosis is also for age 50 or above is the percentage.
That's okay. So this analysis, on the basis of this analysis, we can identify the ER, PR status, etc.
Exactly. The data set gives all that information. Yeah.
No. Using this canonical correlation analysis, we can identify the outcome, like whether the patient is having ER status positive or no. Is it like that? The analysis?
No. So it's not predicting whether the person has, it's not predicting the ER status. It's more like an association analysis. It's like a prognostic model, right? So we have the ER status of these women given to us. Those are the Y values. And the X values are the gene expressions selected from the canonical correlation. Instead of using 23,000X, let's say we have 200X values. So now we have identified 200X values, and the Y values are given for 1,900 women. So we now do the logistic regression modeling to identify the relationship.
Okay. You can assess the risk also.
Exactly. Yeah, but in order to make it a prediction model, then we have to go through cross-validation, training test validation type of exercise.
Correct.
But here we have not, let's think of it as only a training model.
Okay. Good. Very good analysis. Thank you very much.
Yeah, there is a lot more to be done as still this is only a small piece of what is the potential of such data.
We have a large data, so that maximum utilization of that data, doing this kind of analysis. And you can think of machine learning algorithm also for that gives you better classification.
Yes, absolutely. Yeah, but only thing about machine learning is one has to go about it very carefully, because it can become a black box, and one has to be cognizant of the assumptions one is making at every single step. But that said, it has a lot of potential, definitely.
Okay, thank you very much. Let us wind up this session. Thank you.
Thank you all. Yeah.
Thank you. Thank you, Professor Dea, for your wonderful talk. Let us give a big clap to Professor Dea.
Thank you. And I am grateful for Dr. Matthew for chairing the session, and Dr. Satish for the opportunity to present this work, share this work.
Also, we wish to express our gratitude to you, Madam, LMA Madam, for chairing the session. Thank you so much. Thanks a lot. Yeah. Now let us move to the next. Yeah, bye.
So next is my presentation.
Yeah, next let us move to the next session, in which Professor our Dr. Dharmaja is here to chair the session, and also Swapna, please introduce the chair and help the chair too.
Hello everyone. We are moving on to the 22nd technical session of WSTA 2024, which is a special invited session that shall be chaired by Professor Dharmaja. Now, Dr. S.H.S. Dharmaja, head to the Department of Statistics. We are really lucky to have you, ma'am, chairing this session today. With great pleasure and honor, I invite Dr. Dharmaja to chair the session. Over to you, ma'am.
Thank you, Sapna. Good evening, everyone. It is with great pleasure that I am given a chance to chair the session, and it is my responsibility to introduce the two eminent personalities in epidemiology and biostatistics for the special invited lectures by Professor Eliama Matthew from Regional Cancer Center, Trivandrum, and Professor Anil C. Matthew from PSG Institute of Medical Sciences and Research, Coimbatore, India. Feel free to interact with the eminent speakers after their lecture. Expecting your energetic participation. This technical session number 22 for 1 hour. Already 10 minutes is over. So we have only 1 hour for this session, which is distributed as 20 minutes for lecture and 5 minutes for discussion for each session. Thank you. I hope so. Anil sir is also in this session.
Both are there. Anil sir also joined.
The first speaker is Professor Eliama Matthew from RCC Trivandrum on application of meta-analysis for assessing relation between diabetes mellitus and liver, pancreas and colorectal cancers. Short introduction. Professor Eliama Matthew, presently working as Professor and Head in Division of Cancer Epidemiology and Biostatistics, Regional Cancer Center, Trivandrum, did her MSc in Statistics, and she holds a recognized postgraduate medical qualification of Fellow Academic of Medical Sciences since 2011. Worked as a postgraduate trainee in epidemiology and obtained PhD in epidemiology from Finland, and worked as a postdoctoral scientist in the National Cancer Institute, USA. She holds a doctoral degree in statistics also. She has 32 years of experience in the field of cancer epidemiology and biostatistics. She served as a country representative for Asia Pacific Organization of Cancer Prevention conferences held in Japan in 2009, Thailand in 2011, and Bangkok in 2013. She received international and national fellowships to attend various conferences in Japan, Thailand, Malaysia, South Korea, the Netherlands, France, and USA. Served as a regional editor of Asia Pacific Journal of Cancer Prevention during 2010 to 2016. Under her guidance, 5 students were awarded doctoral degree, of which 2 are from epidemiology as guide and 3 in statistics as co-guide. She has 118 indexed publications with 4,482 citations, an H index of 39 and I-10 index of 75. As a professor and head, she has the credit for expanding the project Hospital-Based Cancer Registry, HBCR of RCC Trivandrum, to the status of Department of Cancer and Epidemiology, Cancer Epidemiology and Biostatistics, and computerized all data since its inception of HBCR from 1982 to 2018. She also made a paperless registry, population-based cancer registry, Trivandrum, and it made into an internationally accepted registry, covering to nearly 10 million in South Kerala from a population of 1.1 million. During her tenure as professor and head, HBCR published 15 annual reports and a 30-year consolidated report. Let us hear her and welcome you, madam, for enriching the audience with your lecture.
Thank you, Sarmal teacher. So, my screen, is it visible?
Yeah, visible, ma'am.
Okay. Thank you for your introduction. Very elaborate introduction. So let us move to the talk. As she mentioned, my talk is application of meta-analysis for assessing association between diabetes, type 2 diabetes mellitus and gastrointestinal cancers. In fact, meta-analysis, it is a set of, so my screen, it is moving. My screen?
Yes.
Yes, madam, it's moving.
Okay, meta-analysis, it is a set of statistical techniques for combining information from different studies to derive an overall estimate of a treatment effect or any effect size. In fact, this the background of the historical note is on the importance of research synthesis. First, it is made by Carl Pearson in medical research to use formal techniques to combine data from different studies in 1904. He synthesized data from several studies on efficacy of typhoid vaccination. So meta-analysis, if you see this pyramid, the topmost is it comes meta-analysis. The randomized clinical trials, double-blind studies also comes afterwards. In fact, the main thing is if we do the meta-analysis properly, the rank is first. So these are the various steps. We have to define the research question first, perform the literature search, select the studies, extract the data, analyze the data, and report the results. In fact, one of the major problem which comes is heterogeneity, which will be discussed in the subsequent session. So to do a meta-analysis, first of all, we have to make a prisma diagram. So identify all studies from the literature, and then that is identification, screening, then we separate eligibility criteria, and finally include the studies for our topic of interest. Then coming to the topic type 2 diabetes and gastrointestinal cancers. So we know that type 2 diabetes mellitus, it is a chronic disease characterized by hyperglycemia due to metabolic derangements. In 2014, it was estimated that 422 million people in the world had diabetes, with a prevalence of 8.5% among the adult population. Further, it is reported that 5.7% of all incident cancers in 2012 were attributable to the combined effect of diabetes and high body mass index, and reported that the East and Southeast regions of Asia were the largest number of cancer cases attributable to diabetes only. In India, National Family Health Survey 5 reveals that 13.5% of female population and 15.6% of male population have high blood sugar values. In 2020, an estimated 129% increase in cancer burden compared to 1991 in India. Most studies linking to cancer to diabetes report strongly positive association between diabetes and colorectal, hepatocellular, that is liver, gallbladder, and pancreatic cancers. Global estimate shows that 25% of cancers are gastrointestinal, which are pancreatic, liver, colon, and rectum cancers. These cancers are increasing worldwide. So in the present analysis, we searched 3 databases: PubMed, Google Scholar, Medline, and Scopus database. Using the keyword pancreatic cancer, hepatocellular cancer, the same as liver cancer, because sometimes people use both either hepatocellular or liver cancer. So that is why we used these 2 keywords together: colorectal cancer, diabetes, gastrointestinal cancers, and observational studies. Our exposure, the exposure considered in the analysis, diabetes, and we collected the published articles, whether they have collected data through self-administered questionnaire and later validated using data from medical registries. Further, we collected duration of diabetes, age, and all other confounding factors. The outcome is incidence of different gastrointestinal cancers, liver, pancreas, and colorectal in subjects with diabetes compared to those with no diabetes, and studies on incidence of these cancers with the duration of diabetes and studies on gender-based differences were included. And this is the principal diagram which we have 181 articles we identified through these databases, and then among these 181 we collected full articles 53, and we excluded 128 articles because of these title we could obtain only abstracts, etc. And then among these 53 full text we excluded 17 articles. Full text articles received assessed for eligibility 36, and all these 36 articles used for the analysis. Inclusion and exclusion criteria already I have mentioned. Then among these 36 studies, 12 studies we obtained for related to pancreatic cancer, 5 case control and 7 cohort studies, 13 studies on colorectal cancer, 4 case control, 9 cohort, 11 studies on liver cancer, 5 case control and 6 cohort studies. The results were the pooled analysis based on these 36 observational studies. In total 14 case control, with we have obtained 15,482 cases and another 72,000 controls. This is for the case control study, and 22 cohort studies, and among these 69,000 something cancers, and this number of subjects, general population, and subjects at risk were stratified into 2 groups. One group diabetes duration less than 5 years versus more than or equal to 5 years. And for case control studies, we estimated pooled or we collected OR, and for cohort studies RR, we separately for less than 5 years and more than or equal to 5 years. Then we adjusted OR were obtained from different studies and reported data on men and women separately, and pooled risk was calculated with DM compared to those without DM. This pooled risk along with the 95% CI were computed using Mandel-Hinsel method, and we assessed the heterogeneity among studies. We know that the different studies are conducted in different platforms. There will be definitely heterogeneity among studies. So we assessed the heterogeneity using Cochrane's Q test and I-square statistic, considered statistically significant, and graphical representation using forest plots. So this is the list. Once we abstract data from each study, the cohort studies. These are the data. This public year of publication, when they conducted the study, what is the sample size, and summary risk not available, confounding factors not available, likewise. So we collect data. This table is used as the material for the meta-analysis. These are the studies which we obtained, cohort studies showing risk of diabetes mellitus and colorectal cancers. These are the only 2 studies we obtained, case control studies obtained, which showed the risk of diabetes and colorectal cancer. Then cohort studies showed risk of diabetes and liver cancer. So for each study, whatever confounding factors they have given, all those are collect. We make a table like this before conducting the pooled analysis. Cohort studies, these are the cohort studies, and these are the case control studies showing the diabetes mellitus and liver cancer. These are the cohort studies showing the diabetes mellitus and pancreatic cancer. And the case control studies showing risk of DM and pancreatic cancer. Previous one cohort case control. Then we the DM and estimation of pooled effect size. Basically, 2 types of statistical models, such as fixed effect and random effect models, for estimating the pooled effect size. In the fixed effect model, we assume that the effect size shares a common effect size in all the selected research studies, and hence the term we use fixed effect. However, when studies with different study designs or differences among the studies are considered, the fixed effect assumption may be violated. So then in such situation, we use random effect model and assumes that the effect size varies from one study to another, and it is mainly due to the differences among the studies. So statistical methods for pooled risk estimation: for fixed effect model, Mandel-Haensel and Peto's method, and for random effect model, Desimonian and layered. This is one method for random effect model, and statistical heterogeneity using Q statistic and I-square statistic, and this I-square values correspond to low, moderate, and high levels of heterogeneity, and if RR less than 1, which reflects a lower rate of event in the test arm, in the case group. Subgroup analysis and sensitivity analysis can be used to explore possible sources of heterogeneity. So coming to the result for fixed effect model, we consider it, we start the observed effect size and go backwards to estimate the pooled effect size. To minimize the variance of the estimate, we use weighted mean, which is the inverse of the individual study variance. The pooled effects are estimated by using Mandel, as I already mentioned. So consider a 2x2 table. Exposed, here diabetes, unexposed is no diabetes. Disease is here either pancreatic cancer or liver cancer or colorectal cancer. So consider a 2x2 table like this. And this is the formula for the Mandel-Haensel method, pooled risk estimation. ORMH is for case control studies. And the variance, this is the way to calculate the variance, and this is the way to calculate the 95% confidence interval. So Peto's method is, in fact, here summary odds ratio is here, in fact, ORMH instead of here in the previous, we use this weighted WI and ORI. OR means odds ratio, the risk of each study. Here we use the variance and observed and expected number of cases, and this is the log OR. And taking the exponent of that, we get a pooled OR and 95% confidence interval. So in the random effect model, within and between, there exists two types of variations, within and between study, between the study group. Then in this model also, larger studies will have higher weights. However, smaller studies have relatively larger weights than fixed effect model. I have already mentioned Desimonian and layer method is the most frequently used method for obtaining pooled estimate in random effect model. So this is the formula for the Desimonian and layered method. So then heterogeneity in meta-analysis. When different studies with the same research questions are brought together, there exists variability between studies. Variability, this is termed as heterogeneity. Cochrane Q test is used for determining heterogeneity, and this is the formula for Cochrane's Q test. If the Q value is higher than the critical value of a given significance level alpha, we conclude that there is statistically significant difference between study variation or heterogeneity. So accepting the null hypothesis for Q test usually leads to the choice of fixed effect model for meta-analysis. On the other hand, rejection leads to applying random effect model. So another measure is I-square index, which also measure the level of index heterogeneity, which takes values between 0 to 100%, and it is useful for identifying the model between fixed and random effect models. If I-square value is less than 25%, which corresponds to homogeneity, and between 25 to 50, low heterogeneity between studies, and if it is 50 to 75%, moderate heterogeneity, and if I-square value is more than or equal to 75%, high heterogeneity between the studies. So coming to the result diabetes, DM and pancreatic cancer. So case control studies, I have already shown different studies, and these are the number of cases which we obtained in each study, and these are the risk. OR means odds ratio, and these are the then by men and women separately. Here also adjusted OR. We have considered adjusted OR, and then by gender. In some studies, gender different, they have been reported the adjusted OR by men and women separately, only pooled risk. So we use, for the pooled risk estimation, we used 1, 2, 3, all these 5 studies, and this is the pooled odds ratio, and I-square value is this. And then here also on the basis of the we considered fixed effect and random effect, and if I-square value is here, it is heterogeneous in nature. So then in fact to consider fixed effect model gives better since that assumption gives a better pooled odds ratio. So if there here 1 or 2 studies, when we exclude one study and then again we check the I-square value, and in such situation we may get a fixed effect model. That is another way we choose if there are heterogeneity. So then diabetes, then this is the same value. This is for the cohort study, case control studies for pancreatic cancer, and this is for colorectal case control studies by gender for colorectal cancer, and slightly here the value is 2.8, here slightly less 1.343, and then for case liver cancer the value is here it is slightly highest value obtained for liver cancer. Then the similar results based on cohort studies. In fact, cohort studies, among the observational studies, we can consider cohort studies as the gold standard method. So the results based on cohort studies will be more reliable than case control studies. So here also we have obtained almost similar results for pancreatic cancer. Then for colorectal cancer, here higher than pancreatic cancer, and then for liver cancer is 1.7. Whereas for case control studies, we have obtained the highest result for liver cancer. In fact, not much difference. It varies from 1.7 to 3. So this is the association. Then now, whether the duration of diabetes, is there any? So overall, we have observed a relation between diabetes and various gastrointestinal cancers. Then here we have separately analyzed the data using the duration of diabetes, less than 5 years versus more than or equal to 5 years. Here also pooled less than 5 years for pancreatic cancer results are the risk is very high, whereas for duration, once the duration increases, the risk is smaller. That is what in the pooled risk we have obtained, and this is for case control studies, and cohort studies also similar obtained. So consistent findings have been observed for pancreatic cancers. Initially, duration of diabetes, initial period, the risk for pancreatic cancer is higher than once once they have stabilized. I mean the duration increased, the risk is less. And this is for colorectal. The similar kind of observation have not been observed. So less than 5 years, 1.56. Here more than 5 years, it is 1.32. And here not that much, that kind of consistent results obtained for colorectal cancers according to the duration of diabetes. For liver cancer also, we have here duration increased, the risk is 5.14, whereas with less than 5 years, it is 2.08. And then in all these pooled risk, we have observed statistically significant results. I mean, these confidence intervals, the null hypothesis 1 is not included in any of the pooled risk. Whereas if you see this Lee et al. In this study 0.73, this study is not shown a significant result, whereas these two studies showed a significant result. So when we pooled these three studies, it showed a significant result. So 95%, the null value 1 is not included in this interval. So it showed significance. And then similarly for cohort studies also, here all the 4 studies showed significance, whereas here duration, this 0.87 to 1.67, not significant. However, in the pooled studies, when we combine all the 4 studies, it showed significance. So this type of diagram is called forest plot. This is each study, you can see that a confidence interval wide. This is pooled risk. When we pool all these studies, this is the effect size or pooled risk, and the confidence interval narrow. So that is the reason meta-analysis results give more reliable results than individual studies. So association between DM and this is for pancreatic cancer, and this is for colorectal cancer. Wide variation here, whereas in pooled risk, this is the pooled value. Liver cancer also, this is the pooled risk, and these are the individual studies with the effect with the odds ratio, with the case control study odds ratio with their 95% confidence interval. So this is for cohort studies, pancreatic cancer. Again, this one value. This study was not significant, but almost all the studies except this also borderline significance. So this study is pooled risk. You can see that the confidence interval is almost similar to the effect size. This is based on a large sample size cohort study. That is the reason this confidence interval is very small. And here also colorectal cancer, very small, with the effect size, liver cancer also. All these one above, risk values are above 1, which shows compared to no diabetes, the risk for development of these cancers are much 2-fold or 3-fold higher. So by duration under 5 years, so these are the values. Even duration also, case pancreatic cancer risk I have already mentioned. Here this is under 5 years, and this is more than or equal to 5 years. So cohort study, this same tables I have already shown. I will skip these slides. So this is another diagram called the funnel plot, because the journals usually, if there are some results, I mean significance, then only most of the journals accept the paper. So if we say that diabetes has no relation with gastrointestinal cancers, it is very difficult to get acceptance in a paper, in a journal. So that so we need to assess the funnel plot, that is to assess the publication bias in meta-analysis. We have already seen that in some papers did not show any significance, but still it is published. So a type of reporting bias that can affect the validity of meta-analysis, and of course systematic reviews also. It occurs when studies with significant results are more likely to be published than those with the non-significant. So this is the way we assess this diagram shows no publication bias, whereas this diagram shows a publication bias. Relatively, this part is relatively empty, suggests that the publication bias in studies. So then in this analysis, we have the significance of this meta-analysis is we considered both case control and cohort studies, making the results more comprehensive. Then studies from all regions of the world covering multiple ethnicities were included, and we calculated summary risk ratios and odds ratios from crude data, making results across studies that considered different confounding factors. However, there are some limitations. Duration of diabetes. Many studies exactly 5 years. According to their own choice, they classified. So we have to get some compromise for choosing the duration of diabetes less than or equal to 5 years, less than 5 years versus more than or equal to 5 years. Then some studies did not provide gender-specific results. Then association between other cancers. There are, other than these pancreas, liver, and colorectal cancers, studies have shown association with the diabetes and esophageal and gastric cancer, gastric or stomach cancers, which we have been considered in this present analysis. So in conclusion, these are our for colorectal cancers. These are the various results which